The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, good morning, good afternoon. Welcome to PYRO Asia 2020. And it will, we are on the second day now. Um, so I'm hoping that all of you ready. Okay, before we start the sessions, let me quickly browse through the activities, what kind of things are there, and also introduce some of the sponsors. Okay. As you see, this event happened because of this technical advisory committee. They put together hands and they put this nice program for all of us. And very much thankful to all the committee members to showing the spirit and make this PYRO Asia in a very with a good technical program. Let me introduce, as you know, this event happened. One of the reasons also sponsors. If you have good sponsors, this event really goes well. I'm pleased to introduce, and yesterday I did introduce, as some of you have not registered yesterday. So for the sake of everyone, I'm doing it again one more time. Thanks to the Frontier Laboratories, Japan, and they are specialists on the analytical pyrolysis technology, and also CDS Analytical from USA. They are also an provider of the innovative pyrolyzer and also thermal desorber and also purge and trap concentrator for GCMS. Okay, and also Geol from Japan, and they are also specialized in the material analysis and applications, and particularly on the mass spectrometer systems. And of course, our bronze sponsor, SG Lab Forum, is a Singapore-based professional forum connecting lab professionals and for learning, knowledge, and sharing. And all these sponsors, we're thankful to them and for making this, supporting this event and making this event really a very good program. And this event is management is by the Technobase, and you've been hearing me yesterday. Technobase is an international resource center for the polymer industry and process technologies. We are based in Thailand. We have webinars, various webinars. I'm very much thankful to Dr. Karthik to get involved in this event. This is me. Okay, you may not see me, okay, but you can hear me whole day. Okay, I'm a Param Prasad Rao. I own the company called Technobase. I have 23 experience in polymers and energy environment. I have education in chemical engineering and also master's degree in environmental engineering. So I will be your event moderator for a whole day today and also tomorrow. We have this research innovation webinars, which we also Technobase organize. It's an online platform for the research innovations and commercialization. Anybody interested to work with us, you can contact me. Okay, this is basically to promote individual research from the researchers. Okay, this is a schedule. Okay, yesterday we finished already Friday, and today is 12th December, Saturday. Nice Saturday, and it starts at Singapore time at 1 o'clock and finish at 8 p.m. Singapore time. And this is for the India time. Okay. And this is for Korean time. Okay, and we're happy to say, any conference, really, you get good content. We have good quality of speakers. We have very nice plenary speakers. Okay, and keynote speakers from various parts of the world. I don't want to name them. You will hear them very often now. Okay, and we invite on some invited speakers. So this makes the high quality content, the program. Okay. And this is a schedule for the yesterday, and today is going to be like this. Session 4, applied pyrolysis biofuels, and once the session is 2 hours long, if after that we take a break, then we start another session on the biochar and biocarbon, and then we go for the analytical pyrolysis, and the last session we also have the panel discussion. So we try to finish on time, and I'm requesting all the speakers to be on time as well. This is for tomorrow. Okay, just a few tips for all of you to understand. All the delegates, if you have a questions, see, this conference program is all about, we listen to the speakers, then you had to ask questions related to the topic. And you can post your questions in the question box, and I will take these questions and put these questions in the PowerPoint so that the speaker can answer these questions. When you ask the question, please make sure you attention to whom, because there are a number of speakers. Some of them are related, and some are overlapping work expertise. So it's better that you mention to whom. If you're every speaker, just all, yeah. This way, easy for me to manage your Q&A session. Okay. During a panel session, all the panel members are required to open their webcams so that we have a fruitful discussion. And in Q&A sessions, session speakers also, they can also ask other speakers some question, not only in listening to people, audience question, but also the speakers also can ask other speakers. After plenary lecture, we will have a Q&A session. Every day we have one plenary lecture, and immediately finishing a lecture, then we will have a 5 minutes Q&A. Okay, for the benefit of all audience and the speakers, and also managing the audio and the time management, preventing any external noises. All the speakers are requested to keep the speaker mute when they're not speaking and presenting, so that you won't hear any other noise from you. Okay, only during your presentation or during you want to say something, then you open your speaker. Yeah. If any delegate is unable to hear properly, please check your audio settings and internet settings. See, it's very important. The internet stability is very important. High-speed internet is important to have a clear audio. So please check your your audio settings. If still does not work, please log off and log in again. It makes easy. Okay. And all the speakers are requested to open their PowerPoint file, get it ready to share to the audience. I will send a request to share the screen once your introduction is over. Okay, so these few tips. Okay, I think I mentioned most of the speakers are here, and all the speakers are requested to log in 15 minutes before their scheduled session. So during the break time, I can do any assistance you need for the sharing the screens, explain your things. After completion of session, you can log off this, as a panelist. You can join as a delegate if you like to listen to all other talks. Yeah. Okay, and as you know, we have a participant from different parts of the world, and it's a request. All the speakers, I request them to speak clearly for the benefit of all audience from different parts of the world. Okay, and again, request manage your time as per the slots given. Okay, and if you have extra time, we can go for it for the Q&A session or more discussion time. Okay, if you have any questions, or if you need some help on the during the sessions, you can email me. I'm online, and also my mobile number is this. I use WhatsApp as well, so you can send any message. So I try to help you as quickly as possible. Okay. This is the control panel. Okay, during the presentation, you may see what you call the the panel. So to hide the panel, you click on this arrow mark. Okay, there is arrow mark. Okay, and if you want to mute a speaker, unmute the speaker, click on this speaker. So so that everybody only hear the audio speaker presentation, not other people's noise. So please do use this click on mute and unmute when you want to speak. Okay, mute means red color, unmute means green color. Okay, yeah, so this is a basic instruction. Okay, now we are into the session 4. Okay, I think we are on time now. Now invite our the session chairman, Professor Toshiaki-san from, let me introduce him. Okay, he is a Tohoku University professor. He has expertise on the recovery of chemical materials from waste plastics, use of layered double hydroxides in wastewater and waste gas processing. Is also on the wet and dry treatment process of high impact polystyrene containing brominated flame retardants, wet dechlorination treatment of waste plastics containing chlorine, recovery of metal from waste using the chloride voltization process. Now I invite Professor Toshiaki-san to give a welcome remarks to the audience.
Thank you very much, and introduce me. And my name is Yoshioka from Tohoku University. Yeah, and I'm happy to join this PYRO ASIA together. And then following yesterday's session 2, today we are starting a session of the applied pyrolysis biofuels. And the global warming is said to be one of the cause of the dramatic change in the global environment. Japan, which has not yet become a developed country in terms of policy, has finally declared that it will aim for zero carbon dioxide emission by 2050. However, since we need resources and energy, it is difficult to achieve real zero carbon dioxide emission. Since we need resources and energy, it is difficult to achieve real zero carbon dioxide emission. And we must achieve zero emissions as a carbon cycle of the entire planet. I considered pyrolysis of carbon materials such as biomass and plastics to be a tool that can greatly contribute to solving that problems. This session is at first for presentation, but now a little bit shifted to the some focusing the lecture. And today we have a plenary lecture by Professor Jinfeng Zhou's current situation and development of the biomass pyrolysis technology and its industry in China. And other keynote lecture by Professor Su-Xiong Lam, the microwave vacuum pyrolysis conversion of biomass waste into value-added biofuel, feedstock, and product. Yeah, and they will give lecture that are very interesting and show solving the current issue and a hopeful direction for the future. Thank you very much. And now the Professor John Ming Schultz is entered in this session. I can hear your face now. And he prepared to present second generation biodiesel production from the triglycerides. And I hope to the very interesting talk in this session. Thank you very much.
Okay.
And then the microphone to send back to the Param.
Okay.
Okay.
Yes. Okay. Thank you, sir. Now we are, let me introduce the plenary lecture. The current situation and developments of biomass pyrolysis technology and its industry in China, and it's begun by Professor Ji Fengzheng, College of Energy, Xiamen University, China. Let me brief about him. He is the distinguished professor and vice dean at the College of Energy, Xiamen University, one of the top universities in China. He got the support from New Century Excellent Talents of Ministry of Education in 2009. He is the director of Fujian Provincial Technology Development Base for New Energy Industry, the executive deputy director of the National Local Joint Engineering Research Center for High Efficient Utilization Technology for Forest Biomass, Yunnan, China, and also he is the director of Yunnan Provincial International Joint Research Center for Bioenergy, Southwest Forestry University. In 2006, he received his PhD degree from Northeast Forestry University in China. He was a visiting professor from 2006 to 2007 and a postdoc from 2007 to 2010 at the Institute of Chemical Industry of Forest Products, China Academy of Forestry. He was a visiting professor at the Louisiana State University in 2009, National Renewable Energy Laboratory, USA from 2012 to 2013 and 2015 to 2016. He established the Biomass X and Carbon X group in SWFU and XMU respectively. He published more than 200 journal papers, got more than 20 awards, and also more than 10 Chinese patents. His research focused on the catalytic conversion of biomass into fuels and chemicals, converting biomass and polymer into carbon materials such as carbon fiber, carbon foam, carbon nanofiber, and etc., converting vegetable oil into the fuels, chemicals, and polymers. You can see his profile talks a lot. Okay, it shows that how much he's knowledgeable, how much experience he has on this subject. Let's welcome Professor Jifeng Zhang to make a presentation. I'm going to ask him to share his screen. Okay, here I go. Yeah.
Okay.
Yes.
Can you see my screen?
Yes, sir. It's on now. Yes, go on. Yeah.
Okay. Okay. Hello, everyone.
Okay.
It's my pleasure to have presentation here. Today, my topic is about biomass pyrolysis technology and its industry in China. So I'm from College of Energy, Xiamen University, China. So my college focus on new energy, such as biomass energy, solar energy, of course, nuclear energy, energy storage. So we did it, biomass energy, I think we did it for almost 20 years. 20 years. So we have a lot of experience, and of course, some thinking about in pyrolysis of biomass. So let's talk about this technology, its industry in China. Firstly, introduce myself. My research interest is carbon materials and energy storage. Of course, we got a lot of funding from national and provincial government. The funding is more than, I think, 30,000 yuan. 30,000 yuan. Of course, I published more than 200 publications. So of course, I got some awards. So this is my topic content. I will introduce five parts. First one, I need to introduce some the background. As we know, the renewable now is become popular, more popular and popular. This feature shows us the renewable share of total final energy consumption in 2018. The fossil fuels is occupied about 80%, but the rest is renewable or nuclear energy and renewable energy. And modern renewable energy is about 11%. So from the figure, we know renewable energy accounts for more than 20% of the global final energy consumption in 2018. And traditional biomass takes about 6.9%. But the modern biomass and solar geothermal heat is about 4.3%. This shows us the final energy consumption in 2007. And in here, modern renewable energy, of course, is not including the traditional use of biomass, accounted for as estimate about 11%. So the highest share of renewable energy use is about 26%, was in electrical uses, including heating, cooling, and transport. However, this end use accounted for only 17% of total final energy consumption in 2017. So a lot of countries have renewable energy policies and, of course, fossil fuel subsidies. But we need to get more effort to policies to support renewable energy. Like we have 143 countries with renewable energy power policies, and more than about 70 countries with renewable energy transport policies. So we hope the countries will take effort to make renewable energy regularly policies. Of course, renewable energy like champions. So from this table, we know in 2019, like China, United States, Japan, India, these countries, they did a lot in renewable energy. And the capacities, total capacities, like China is the number one, and we can get by power capacity. Number one is China, the next United States, Brazil, India, and Germany. And of course, the overuse of fossil resources has caused serious resources and environmental problems. China depends on crude oil usage more than 60% in 2018, and will exceed 75% in 2030. So these cause CO2 and SO2 pollution. So that has a serious impact on environment. Fossil resources will eventually be exhausted, and renewable carbon resources should be developed early. So China have to strictly control total energy consumption. In 2020, the energy self-sufficiency capacity will be maintained at more than 80%. And a relatively complete energy security system will be basically formed to provide energy security for build a modernly prosperous society in an all-around way as scheduled. So from 2021 to 2030, a modern energy system will be initially constructed in China, and by 2050, a modern energy system will be built in ensure modernization of China. So in 2020, the total energy consumption will be controlled within 5 billion tons of standard coal, and the number was 0.86 billion tons, with increasing 60.3% in 2019. So we have been controlled within 6 billion tons of standard coal from 2020 until 2030. And with the effort, the total energy consumption will be stable, with non-fossil energy accounting for more than half in 2050. So this is the situation of renewable energy in China. In 2020, the total energy production is 3.97 billion TCS, standard coal. Total consumption of 4.86 billion TCE. And of course, we are glad the coal consumption occupied below 60%. just 47.7%. So it's decreased year by year. Consumption of security energy is about 23.4%, and non-fossil energy is 15.3%. And from 2015, renewable energy installed capacity increased 12% everywhere. So we have a lot of policy to encourage to have renewable energy. The renewable proportion of new installed capacity is still 50%. So the total renewable energy installed capacities increase steadily. And the power generation, the renewable energy power generation in China, most of them are wind power and solar power. So wind power and solar power, these new energy are developing rapidly and become the more main body of renewable energy development. From 2015, new energy accounted for more than 80% of the annual installed capacity of renewable energy. In 2019, the new energy installed capacity of 43.8 million. So occupied of the 50.2% of the total renewable energy installed capacity of China. So in 2019, China annual renewable energy power generation is about 2,000 billion kilowatts, with a year-on-year increase of 9.5%. So it's account for 27.9% of total power generation. So of course, the first one is hydropower, but the new energy is about 10%. In this new energy, biomass power generation is about 1.1 million kilowatt. It's about 1.5% of total generation. So it's not so high. And installed capacity by the end of the 2019, China's total installed capacity of renewable energy power generation was about 80 million, with a year-on-year increase of about 8.6%. So the power installed per capacity is about 40%. So occupied the new added installed capacity of 57.4%. So of course, biomass resources are rich. A larger number of agricultural or forestry, lignin, cellulosic biomass is produced every year in China. It's about like agricultural straw is 900 million tons, and forestry is 110 million tons, and forestry processing residue is about 200 million tons. So the total amount is more than 1.1 billion tons, and about 500 million tons a year can be used for energy and materials. So we need to use biomass resources. All these is about 5 million tons. Of course, the production of biomass for products that we think about is resource utilization. But for protect environment, we need to the energy substitutions. from initial utilization, we use like just firewood, but from 2020, like biogas and gasification was used in China. This like is a commercial utilization, and of course we have an energy concept about residential energy from 1949, like household biogas was used. And from 1978 to 2003, household biogas and firewood saving stoves were used. These are in rural energy. Of course, from 2015, we have energy products like electricity, gasification, pyrolysis, modeling, ethanol, and biodiesel. So from 2016, we have a commercial energy company. Of course, we have a lot of commercial companies like thermal electricity, ethanol, biodiesel. So the current situation of China's biomass energy industry and the gap between the medium and long-term development program is about like biogas. In 2012, it's about 15 billion cubic meters. But in 2020, we need to 50 billion, and liquid fuel from 2.1 million tons to 9 million tons, and densified fuels from 3.5 million to 10 million tons. But now we almost 30 million tons. 30 million tons. That's our target. And power generation is from 29 billion to 200 billion. So we have almost all this target will be achieved. And of course, the installed biomass power generation is increased. The scale of installed biomass power generation in China have achieved more than 23 million kilowatt before 2019. That is about 1.2% of total power generation, and significantly enhance the generation capacity. Biomass is 1.1 billion kilowatt, about 1.5% of total generation capacity. So it was increased by 22.6 million that at 2018. And technology of biogas nation gas biogas industrialization have become mature. 14 biogas industrial projects have conducted, which can produce 127 million cubic meters. And of course, at the same time, we can 1 million tons of the organic fertilizers. And another heating supply system by biofuels was increased. It's realized 18 million tons each year. Of course, the liquid fuel will about 4 million tons each year. This is the electricity of biomass in China. Of course, most of the new projects related to biomass power generation are in the northwest, while the number of new projects in southeast decreased. So biomass garbage classification brings new opportunities for domestic waste combustion power generation. Domestic waste incineration power generation is increased by about 2 million kW in 2019, accounting for the largest share in biomass power generation industry for 3 consecutive years. So let's come to the pyrolysis. Let's come to the pyrolysis. For the pyrolysis, sometimes we use organic compounds under the heat, absent oxygen to get gas products, liquid products, and solid products. So for gas products like hydrogen and liquid products like the tar or solvent oil or solid products like carbon black or coke, This is the cellulose of pyrolysis that we can get like water, this is tar, CO2, and hydrogen and carbon, of course. So when you use the pyrolysis technology, the organic matter in solid waste can be converted into energy for storage, mainly composed of fuel gas, fuel oil, and carbon black. Because the anoxic decomposition and less exhaustive, it is conducive to reduce the secondary pollution to the environment. Most of our harmful components of like sulfur and heavy metals are fixed in carbon black. So Q3 will not be converted to 6 because of the reduction condition. Of course, less NOx is produced. So pyrolysis can be used in biomass conversion into fuels and carbons materials. So the main organic components like the biomass is like protein, starch, or cellulose, lignin, hemicellulose. So solid charcoal and fuel oil and fuel gas, of course, the HV is lower than 5,000 kJ, so can be obtained after pyrolysis. But this biomass can include firewood, corn cob, peanut, and sawdust, and rice husk are pure. All of these biomass can be used the feedstock of pyrolysis. And let's compare the pyrolysis and combustion for biomass or practice and rubbers, etc. For combustion, we need oxygen demand. Energy, of course, is exothermic, and for pyrolysis is endothermic. And the products for combustion is CO2 and water, but for pyrolysis is gas, oil, and carbon black. It can be used as energy feedstock. So the utilization, of course, the combustion like is a local utilization, and pyrolysis, when we get some products, it can be storage and long-term distance transportation. So, of course, the secondary pollution for combustion is serious and pyrolysis is less. So, for the, of course, we have different pyrolysis process, like different heating mode. We have directly and indirectly. For the temperature, we have high is more than 700, and middle and lower. Of course, the furnace structure, we have fixed bed, moving bed, and fluidized bed rotary furnace. And physical morphology is like gas, liquid, and carbon. And of course, we have the single tower, double tower. For the slag, of course, we have slag forming and non-slag forming. Let's the typical pyrolysis technology here. This one is the direct heating. It's the internal thermal pyrolysis. And let's just a single tower, a single reactor. And interthermal pyrolysis is also known as the partial combustion thermal decomposition. The combustible biomass or partial pyrolysis products in the reactor and are burned to make a biomass thermal decomposition by combustion heat. Generally, the lower grade fuel gas is obtained. Because oxygen is needed for combustion, so the inner gas like CO2 or water will be produced. Of course, which will dilute the combustible gas and reduce the value of the pyrolysis gas. And of course, the increment is simply and high temperature can be used. Its treatment capacity and gas production are also very high, but the gas value, caloric value, is not high. As a single fuel, direct utilization is not enough, and the control noise generation by high temperature pyrolysis should be seriously considered. So another one is indirect heating. Let's record it external thermal pyrolysis. This is a fluidized furnace with external heated double tower. We have a double tower. The external thermal pyrolysis is to put the biomass in a closed container. Under the adiabatic condition, the heat is transported from outside of the reaction vessel through the wall of the reactor, and the biomass is indirectly heated and decomposed. So because without combustion reaction, so the high calorific value fuel gas can be obtained. So it's stable in operation and easy to control, but it needs a large power and complex structure to have pyrolysis biomass. So now we have some technologies pyrolysis like the occidental system, land guard system, pillar system, Nippon steel system, and fluidized bed system, and gallery system. And in United States, as a representative, this technology is aimed to recovery storage energy, and another is like Japan, is aimed to reduce the secondary pollution. So it's different. And in China, most of we use like fish bed pyrolysis reactor like this. The fish bed structure is relatively simple, so the gas heat loss is small. And the system thermal efficiency is higher, but the gas is easy to carry some volatile substances, such as tar, steam, and so on. So the calorific value is not high. But for the second one is we use a fluidized bed pyrolysis reactor. The gas flow rate is high enough, and the salt material is always suspended. So it has an advantage of good reaction performance, high decomposition efficiency, of course, the small size, and large heat loss, and poor cleanliness. So we need to avoid ash agglomeration and suitable for feedstock with high water content. And now we have the rotary kiln. The biomass goes through the rotary kiln, and we can get the recycled fuel gas and burn it. That we can get the hot water, the heating from the boiler. So for the products, we can get a lot of products from pyrolysis of biomass. Like pyrolysis, for the summer conversion of biomass, we have different technology like pyrolysis, gasification, liquefaction, combustion, or combustion and retorting. Of course, for pyrolysis, we can get gas, liquid, and solid. But for pyrolysis, we need to get gas and solid. For this gas, we can get some chemicals, carbon, and fuels. Of course, we can get some electricity and heat. So next, I will talk about some products from pyrolysis and how about the industry in China. First one, like Barchar and activated carbon. In China, we have a lot of active carbon. This active carbon classification, is from different raw materials. Most of the raw material is biomass and coal. Of course, we have some raw materials is from polymer, and some from pitch. So one part is classified according to the main materials. So the biomass-based active carbon, most of course the raw material is from biomass, like coconut shell. So we developed activated carbon production from pyrolysis of biomass. We have long history. Like this, in 2049, the Shenyang Northeast Pharmaceutical General Factory multi-tube furnace was put into operation. Like we got charcoal raw materials. In 1951, the stirring furnace of the Qingdao Dongfeng chemical plant was put into operation. In 1957, the Shanghai New China chemical plant built a factory. In 2096, the furnace was built in Taiyuan, now it factory. That was the largest professional factory for national key daily active carbon at that time. And in 1965, Qingdao Dongfeng chemical plant built an intermediate boiling furnace production workshop. And 1966, Heilongjiang tailing retorting plant has built a rotary furnace method active carbon workshop. In 1970, Beijing Guanghua Timber Factory, they have a sandal furnace. So before 1975, China's active carbon industry had no competent units responsible for coordinated development, and the output had been virtually below 10,000 tons. Of course, especially after 2000, active carbon industry in China developed very well, and now there are more than 2 million tons per year and 300,000 tons biomass-based active carbon, and of course more than 600,000 tons coal-based active carbon in China now. So I think it's the largest active carbon in China. Of course, we have a lot of companies do business to import and export active carbon. Due to the environmental protection, so active carbon now is used widely in China. So for the production of active carbon, so we need to control technology of pyrolysis and gasification, self-sufficiency of thermal energy in process of carbon and active carbon production from biomass has realized the cogeneration of heating, power generation, Barchar active carbon materials. So now we have the cogeneration of cooperation together. So we have the policy in 2017, the Department of Energy of China, and of course we have the policy to encourage pilot projects to jointly produce char and carry out research on utilization of carbon-based fertilizers in the field. Activity carbon treat and utilization of soil and water bodies and other downstream industry. So at present, China's active carbon industry is showing a trend of industry clusters. At present, the main domestic-based active carbon companies include Ningxia, Huaxin, Huahui active carbon, and Shanxi, Xinhua, and Shanxi Huaqin active carbon. Of course, main wooden active carbon companies is like Fujian Yunli. So it's the biggest biomass-based active carbon company in China. So and Fujian Zixin carbon industry. So Fujian province is the largest biomass-based active carbon production in China. It's occupied more than 50% of active carbon China. So Xiamen University is located in Fujian, in Xiamen, Fujian. So we have a lot of cooperation with these companies. So most of the pyrolysis technology is from Xiamen, and we have a good cooperation with them. At present, there are more than 300 companies engaged in active carbon productions and sales in country, but only a few have a production capacity of 10,000 tons. So most companies can only produce low or mid-end activity carbon, which makes the markets divided into low-end and high-end markets. So the biggest company now he has 110,000 tons in China every year. So it's a huge. So of course he produce active carbon from coconut shell to the supercapacitor for energy storage. So it's a huge, also a huge one. So of course, for the co-production, like gas, carbon, heat, electricity, especially in north of China, this Huajin active carbon company, it uses apricot shell as a raw materials, and they produce gas, carbon, heat, electricity together. So just a few days ago, I visited the company. They did very well, and they have a new technology to to get the heat, the electricity, of course the active carbon. So of course in China we have another high value products from activity carbon. We call it active carbon handicraft. This picture shows us a sign of the handicraft made of active carbon. This is the biggest one. There are a lot of Chinese dragon on the active carbon handicraft, and all these are from the biomass materials. So I think China is a net exporter of active carbon, but the import value of wooden active carbon accounts for nearly half. Very high quality wooden active carbon for high-end applications. So these two pictures show us the imports of active carbon from other countries. Of course, now is the price of active carbon is increased a lot because the COVID-19 20, and like the Yunli company, they said they earned a lot of money this year. So it's good news for Chinese company. They did very well. So if we using 30% of the China's store each year for biochar industry, can form a biochar-based fertilizer or soil amendment industry with a scale of more than 250 billion yuan. Of course, which we can bring about 100,000 jobs and direct increase farmers' incomes by 58 billion yuan each year. So this is a very huge industry in China. So it can solve the environmental problems, and of course it can increase farmers' incomes. So it has a lot of advantage to do that. Of course, we have another microwave pyrolysis technology. This technology we have devices. This technology is investigated by Xiamen State University and our cooperation company. We established the pilot. This pilot is about every year we can produce about 3,000 tons carbon materials.
Professor Zhang, can you please conclude?
Okay.
Yeah, thank you.
Okay. Just 1 minute.
Sure.
So of course we have another gasification and electric generation for biomass. Let's just go through the slides. Gasification, of course, now we can combine heat, power, and mixed combustion application and synthetic fuels. That's electric combustion, the schematic with all components. And of course, we set up some power generation plant. Of course, a couple coal-fired boilers. Of course, this is the first pilot plant of biomass gasifier will be built in Sennan Eco Group, Henan. And this is Xiamen University's technology. So Guangzhou Energy Research Institute is a leading level in China in terms of the gasification. They set up a lot of the generation system in China. And this is the cost variation.
Professor James, and please Please conclude just 1 or 2 minutes.
Just 150. Okay. Okay. Let's generation, electric generation. Of course, the densified fuels and heating supplies. This is a lot of huge industry now in China. So it's developed very well and very fast. Of course, this is a heating process like industry parts. We have the 20 steam tons per hour in Moreland, and the pollution emission need to reach the level of natural gas. So we have the annual utilization biomass densified fuel will be 30 million tons in 2020. So that's all. Of course, we have some difficult, but we have a bright future. We still need to work hard. We create technology to make biomass pyrolysis industrialization possible. Thank you. Thank you for your attention.
Thank you, Professor Zheng. Guys, now it's a time to ask questions. You can post your questions in the question box. Okay. Professor Yoshiyaka-san, would you like to ask few comments on this presentation?
Yeah, and just 1 question, okay?
Sure.
Okay, thank you.
Yeah, and a very short question. And you focus to the production of the activated carbon from the biochar, and then how the demand of the activated carbon in China, and then if we use the activated carbon, and then we need to the treatment as a final of the activated carbon. How do the possibility of the pyrolysis technique for the treatment of the secondary treatment of the activated carbon as a secondary biomass resources?
Okay. Now for activated carbon production, we pay a lot of attention to solve the environmental problems, right? So we have some technology to make sure we can get the high value or high value the carbon products. So in China we have two technology to do that. One is the physical activation method. We use the water steam, high temperature water steam to produce. Another one is the phosphoric acid and CnCl2, the chemical method. So the treated of the biomass or biochar is necessary to produce the activity carbon. So we have the technology to make products have a good performance.
Okay, and I received another question.
Okay, here I open it.
Yeah, and is the pyrolysis of the biomass done as a receipt, or are there any pretreatment method prior to pyrolysis? And just 1 question. And the other question is, what are the parameters that affect the product's distribution, the profile of a pyrolysis of a biomass?
Okay, you mean a pretreated method has a effect on the active carbon and the pyrolysis, right? Yes, the pretreatment method mostly the process we just like to in China for active carbon for power generation. So it's different. It's different for the wood. For the forestry, like lignite cellulose biomass, like wood pellet, is very easy to do that. But for the agricultural biomass, like straw, I think it's difficult to do that. So of course now we develop some like some new pyrolysis equipment to do that.
Okay, thank you. And other question, maybe the next question is very related to the next presentation of the Professor Soram. And if you have some simple answer, please reply to our questions. One is how is the stability of the microwave during microwave pyrolysis? And the other one, how do you think about the possibility of the microwave pyrolysis for the conversion of waste plastic, such as polyethylene and polypropylene? Maybe the next presenter also can answer this question. But just how about do you think about this question of the Professor Chen?
Yes, we set up a pilot microwave pyrolysis equipment and factory, but the setup is very easier. It's like I don't know how to say that, but when you operate the microwave pyrolysis, you need to spend a lot of the electricity to do that. So we hope if we use the microwave pyrolysis technology, you have to produce more valuable carbon or more valuable products.
Okay, yeah, maybe the I hope the next question, this answer is including the next presentation. Maybe.
Okay,
how much completing the biomass to electricity process compared to conventional coal-based cogenerations?
The biomass, okay. In China, we have at least most of the coal power generation is about 58% in China, and the biomass just I think it's just 1.5%. So it's very not at the same scale to compare that. But Chinese government have a lot of policy to encourage to use biomass to power to produce generation.
Okay. Okay, and then what is the scale at which this activated carbon produced in this processing, and how the cost under this processing, and other case in the can it be used waste treatment application?
And
the
cost of
the scale and the cost and the next application using the water. Just 3 questions, finally.
The cost, of course, because the biomass in China is cheap, but the worker cost is increased. So I think so now we have the auto control. Most of the company there, we have use some auto control technology to increase the worker.
Maybe that depend on the mass volume and depend on the locality maybe.
Yes, yes, yes.
Demand and
Yeah.
volume, maybe. Yeah. Okay.
Yeah, yeah, yes, yes. Okay. Yeah.
Okay,
And it's okay.
Yeah.
Yes. Okay. And thank you very much for your presentations.
Thank you. Thank you very much.
Thank you very much.
Okay, we go to the next presentation now. It's a keynote lecture focusing on the topic is on the microwave vacuum pyrolysis conversion of biomass waste into value-added biofuel, feedstock, and products. The presentation will be given by Professor Shu-Xiang Lam, is from the University Malaysia Terengganu, from Malaysia. Let me brief about him. He holds a PhD in chemical engineering from Cambridge University and is currently an associate professor and a deputy director of International Center of University Malaysia Terengganu. He leads a research group working mainly on chemical and environmental engineering, focusing on waste and biomass utilization, thermal process like pyrolysis, gasification, microwave heating, clean technology. Lam is active in research on the application of pyrolysis and microwave heating in transforming waste and biomass into energy, green chemicals, value-added products applicable to industry and environment protection. He has secured 23 research grants, both international and in Malaysia, publishing about 160 articles in journals, one published by Nature on a sustainable recycling plan, 3 published in Science in 2020 on environmental protection. He filed a patent and also commercialized inventions from his research team. Let's welcome Dr. Lam to make a presentation. Please allow me to send him a request.
Thank you. Thank you, Kadik. First of all, can you listen to my voice, if I may check?
Okay.
All right. Just checking, Katik. Paran, can you see my slides and also listen to my voice?
All perfect. Go ahead, sir.
Okay, lovely. Okay, thank you. Thank you. First of all, I would like to express my gratitude to PYRO Asia and also the organizers for inviting me to give this talk. So I'll just try to make it short because I know I have limited time, like about 20 minutes. So today I'm very happy to share with you about and how to use basically microwave pyrolysis to produce some interesting products from biomass waste. And I'm Lam, by the way. First of all, let me introduce where I come from. I come from a university called University Malaysia Terengganu, and we advocate sustainability. Yeah, and this is Malaysia. As you can see, University Malaysia Terengganu is located in the east coast of Malaysia, and we are very near to the coastline. And this is our campus, not too big and not too small, but the buildings are within the walking facilities, so it's quite friendly. And yeah, we are famous for having research stations in different places. Like we have research stations in Ireland, we have research stations in wetlands, and also we have research stations in hills and also beaches and also lakes. So it's quite environmental friendly, I would say. So please I welcome you all to visit University Malaysia Terengganu. Yes, and yeah, I come from a group called Pyrolysis Technology Research Groups, and we've been working with, still collaborating with where I graduated my PhD from. It's been 12 years now. Yes, this is just a brief background of me. So I've been working with University Malaysia Terengganu, and also I have some appointments in China. Basically, is to help the universities and also, let's say, Henan province to develop solutions to convert their biomass or their agricultural waste into value-added or useful materials. Yes, at the same time, I also have some experience in some journals, handling journals. So I'm involved in some journals as editors, associate editors, editorial board members, and also have experience in editing some special issues as well. And here I would like to share one special issues on environmental pollution. So to those of you, if you have suitable articles to submit to these special issues, please, you're welcome to submit. And yes, and hopefully you can consider this journal as well. So, and also we have another one from Journal of Hazardous Materials. So and the title is Global Environmental Hazard and Mitigations. So it's going to be open in March. So if you really like to submit and you have suitable articles, you are welcome. Right, I don't work alone, so I have a team of postdocs, PhDs, and master students to all work together on pyrolysis projects. So at the moment, this is my research teams, and I really would like to acknowledge their efforts and contributions to the pyrolysis works. Yes, and yes, to be honest, I mean, we are so lucky. Our group is that we have collaborators. We have collaborations with universities in different countries and helping in different parts of their, of their studies towards, knowledge advancements, and also especially on pyrolysis. Yes, and that's also being a chemical engineer, so we also work with the industries. Like in Malaysia, we are working with some companies to develop solutions for waste treatments and also biomass recovery. So these are my industrial partners that we are working closely with. And yes, over the years, we were quite lucky that we managed to get enough fundings to do our research and also to really, come up with some solutions that hopefully is useful with respect to the field of waste recovery and biomass recovery. Yes, so these are, here I show some biomass and waste resources. So just to give a quick introduction that my team, my research group have been working on all of these waste presented in these slides. So we've been trying to pyrolyze it, we've been trying to gasify it, so and hopefully to convert that into some useful products. And yes, one of our research focus would be microwave pyrolysis, because we really like this process. It has many advantages that we think. So to be quick, because just now Professor Chang has explained on pyrolysis. So basically it's very simple. Microwave pyrolysis, basically you use microwave heating to generate the pyrolysis process, and then you try to produce 3 types of main products from the waste and biomass. So you can produce char, you can produce gases, and also liquid oil. And I show a simple diagram here. If you want to, simplify these things, is you put the biomass and waste, and then we put into the microwave ovens. Of course, it's not that simple, but basically you are using, microwave ovens, and then you produce these 3 types of products. Right, and yes, we do have labs, quite some labs, units in lab skills, and we also develop a pilot skills for microwave pyrolysis. Yes, and why we do want to use microwave pyrolysis, why we want to use microwave heatings, because we think that microwave has always its advantages, which is quick. It can provide a fast heatings. Other than that, it has some other advantages, like it can also provide uniform heatings, and also in particular is quite good if you are using it to pyrolyze or to treat materials that contains a lot of polar compounds. So what we are very interested in is because it is, if you use microwave, it can be a fast way of processing your waste. So we always aim to improve the process features and also the quantity and also the quality and the characteristics of the products that we obtain from the pyrolysis. So these are some of our targets when we develop and also research on our process. Right. So we didn't actually work on microwave pyrolysis at the beginning. Initially, we start with conventional pyrolysis. So we start to use conventional ovens or furnace to heat to generate the pyrolysis process. And yes, from those research, we proved that yes, pyrolysis is an interesting method, that you can use it to produce char, biochar, bio-oil, and also gas products. But during these these experiments, we found that using furnace or oven is quite slow. One experiment, sometimes it can take a few days to complete just one cycle. So we are thinking, as a chemical engineer, we are thinking, how can we do and what can we do to improve this process? Then we think of using microwave pyrolysis, because we think, hey, if I want to cook my food, I want to cook it fast. I will just put in the microwave oven. So why don't we use a microwave oven to try to pyrolyze something? And so we tested it, and it works. I initiate this work back in Cambridge University when I was doing my PhD. So we do a microwave pyrolysis in batch mode, where we put a batch of waste, like in this case, waste engine oil, into the microwave ovens, and then we try to heat it, and it works. You can convert and produce some useful liquid oil products from the pyrolysis process. Then we think that if you just do it in a batch operations, it might not be attractive for the industry, because for industry, or if you want to scale it up, it's always good if you can do it in a continuous operations. So we tested it. We try whether we can do it in a continuous operations, and it also works if you want to do it in a continuous operations. And the yield and the compositions of the liquid oil products that we can produce is, it also is quite acceptable, the quality and the yield. Then after that, we also, along the process, we always keep on optimizing the process parameters, like the heating time, the microwave powers, and also, the flow rates, everything, and trying to optimize the yield and the quality of the products that we obtain. And we publish some papers as well. Then when we think that we are ready, we did approach some of our industrial partners, asking them whether they think pyrolysis can be a process, can be scaled up, and also used for industrial applications. But what they say to us, right? LUM, they call me LUM. LUM, if you can, yes, your process may be good, but you can only deal with only one type of waste. So in reality, now when you deal with a waste material, you always have a mixture of several types of waste. So it's not that practical to us from the industrial point of view. So I went back and I come up with this, co-pyrolysis. I tried to pyrolyze several types of waste. In this case, use waste cooking oil and the plastic waste together, and to see whether it works. And it did work, okay? And it actually, we actually produce a better yield and the quality of the liquid products that we obtain, okay? And yes, after that, we also work on a catalytic pyrolysis. We try to add catalysis into the pyrolysis process, into microwave pyrolysis. And it did have some interesting chemistry coming out from there, and we published a paper from there. So from here, we proved that adding catalyst can have some promising effects in microwave pyrolysis. And our latest solutions or approach would be to use vacuum pyrolysis. Because in pyrolysis process, normally if you do this research in the lab scales, you always have to use the inert gas like nitrogen gas or helium gas. That is really costly if you want to really commercialize and use it in industrial process. So we are thinking of a solutions like how can we cut down the processing cost or the operating cost of not using the inert gas, the nitrogen gas. So instead we use a vacuum pump, to suck the gas out from there. So, and it's quite interesting and it produce some interesting results. So here I show a simple, video to show like, okay, first we put the waste into our microwave reactors. We have magnetrons to channel the radiations into the waste. So it got pyrolyzed, heated, and decomposed into pyrolysis vapors or volatiles. So some of the volatiles can be condensed to form a liquid oil, while some of the non-volatiles, non-condensable products, it can be collected. And we found that it contains a lot of syngas. That can be used as a gaseous fuel as well. And the other focus of this is we can also get a very nice activated carbon from there. See, this is also another of our main products, which is activated carbons. So basically, we just now, I think there's a questions on pretreatment. Yes, you always need to have some procedures to pretreat your feedstocks. In this case, for lab scales, we will always cut the waste into smaller pieces and put in the pyrolysis reactors. So this is what happened during microwave vacuum pyrolysis. If you look at the video, you will see when you put the waste into a microwave ovens, you will get pyrolyzed, and this is the pyrolysis vapors that you will get, and you will get the oil products here. So this is the oil product that we get. So you can see this is the one of the main products, liquid oil products that we get. And yes, these are the liquid oil products that we get. Okay, a yellowish kind of things. So our findings so far is that using a microwave magnetron is very interesting because it can provide a fast heating rate. And when you can provide a fast heating rate, relatively you can get a short, you can achieve it or perform it at a shorter process times. When you perform at shorter process times, it's, in a way, it reduces the energy consumptions as well. So in a way, we claim that it's quite energy efficient. And also the advantage of using a vacuum condition is these are some of the key findings that we have. It can lower the boiling point of the products, of the feedstocks, the waste, and we can also use it to control the residence times of the feedstock and also the gases in the reactors. And most importantly, you don't need to use nitrogen or helium gas as a carrier gas. So these actually lowers the production cost. So these are our findings so far. So these are the beneficial features that we can get from microwave vacuum pyrolysis, and that provides us the motivations to develop further. So we have tried to scale it up into a larger scales to be tested with our industrial partners. Okay, and yes, it has been covered in the media in Malaysia recently. And yes, we have found patents and trademarks for that technologies. And we have licensed it to one company, and also we have demand. Companies and also some research institutes approaching us, asking us to develop prototypes for them, and we have made some income from that. So that provides us more motivations to continue this further. Yes, and talking about the products of the, when we do this kind of research, we always characterize or determine the properties of the waste and the biomass that we do. So we got some paper published. And also when we talk about producing the products like biochar, oil, and also gases from the pyrolysis process, we also test whether these products can actually be used. Okay, so in this case, for the biochar, we actually use in cultivating or growing oyster mushrooms, and the result is quite promising. It did actually help in improving the growth and also the collecting cycles of the mushroom. And yes, with respect to the oil and the biofuel that we obtain, we check the properties and also apply it. We found that it's quite similar to diesel. Okay. And yes, it has some desirable properties, relatively greener because if I'm not mistaken, the sulfur and the nitrogen content are quite low, right? And we have some videos here just to show that this is the oil product that is produced from our process. So, we call it as a pyrofuel. So this is when the pyrolysis process is going on. You put your waste inside and it's undergoing pyrolysis, and it will turn into pyrolysis gases, and this is where you will get the oil products. Okay, so and once we get the oil products, we check the properties. It's quite similar to diesel, and these are some of the properties we find it. We find it has a low nitrogen and sulfur, so in a way we can say it's quite clean. And to simplify it, we try to light it up and see whether it can be burned, because if you say you want to use it as a fuel, you have to test it. So yeah, this is one of the simple tests we check. And you can see when we burn it, right, the gases are actually not that, there's no black smoke coming out, so it's quite clean, right? And yeah, one of our recent application would be using the liquid oil products from the microwave pyrolysis, and then we use it to add it up into bacterial fermentations, and in the end is to produce bioplastics. Yeah, and we did produce about 40% yield of bioplastics from using the liquid pyrolysis oil as a feedstock. So out of the 1 kilogram of plastic waste, if we put into this integrated approach, we can get about 256 grams of bioplastics. We have been helping some hospitals in Malaysia to convert some of their medical plastic waste into bioplastics, right? And with respect to the char products, so we produce activated carbon from there. And yes, we use it as a catalyst support. We can use the activated carbon as a catalyst support to grow mushroom and also in water treatment. So there's also another video showing this. So we call our, I'm from University of Malaysia Terengganu. Just give me a second. So we call it as a pyrolite. We try to use it to grow mushroom, as I said. So we use microwave pyrolysis to produce this pyrolite. And these are the properties. We found that it has some interesting properties. The pores are a lot. So when you have a lot of pores in there, so it has these advantages. And so a lot of nutrients can be attached to the biochar. So it can use it to grow mushrooms. So, improve the yield of the mushroom actually, yeah. So these are our findings so far. So when you talk about using microwave vacuum pyrolysis, you can produce liquid bio oil. It's quite similar to diesel, and we can say it's quite green because of these properties. And the energy content is about 42 to 49 megajoule per kilogram. And we can produce char as well. So if you want to use the char as a solid fuel, it's okay, right? And you can upgrade to perform activated carbon. So these are the properties. Our technology, our approach can produce a quite good activated carbon with a BET surface areas of approaching about 1,200 meters square per gram. So when you have a lot of BET surface areas and also a lot of pores, you can use it in adsorbent or a filter in wastewater treatments or as a biofertilizer or even in soil remediations. Okay, yeah, and this is the platform technology that we are still developing and keep on researching. So we use, in terms of the technology itself, we also apply microwave heating in other applications like desalinations and also keep on improving the process itself. And with respect to the products, these are the products that we obtain. So we always try and see whether we can use these products as a different products. We keep on trying. We just like to keep on trying. And yes, here I report some of my, our research output. So yeah, we have microwave vacuum pyrolysis. We use it to treat plastic waste and cooking oil. And we do some techno-economic analysis as well. And we have checked that, doing it in a vacuum environment has some promising features compared to doing in a conventional nitrogen atmospheres. And yes, we published in Energies and saying that the liquid fuel has some good properties for if you co-pyrolyze used cooking oil and plastic waste. Like I say, using waste palm oil, you can produce a diesel-like fuel. Okay, and yes, with respect to the char that we obtain, we can use it to treat industrial effluents. There are some interesting results. Okay, and yes, we also use it to treat. We found out that we can produce a type of activated carbon that contains micropores and mesopores. And when you have a combination of these kind of pores, you can use it to treat industrial textile dye wastewater. Okay, and yes, we also develop another types of microwave pyrolysis technologies because we call it self-purging. So rather than using a vacuum pump, we also we also use the gases, the pyrolysis gases produced from the pyrolysis itself as as a gas to maintain the inert environment for pyrolysis. Yes, and we also combine microwave pyrolysis with steam activations into producing activated carbons that we use it to remove herbicides in agricultural waters. And yes, we try to, we keep on improving the quality and the properties of the products that we obtain. And yes, we also try to use it in sludge treatments using, now we also, not only we are using microwave pyrolysis, we add CO2. Carbon dioxide as slightly reactive gases and see that if there's some interesting chemistry coming up from there, and it's quite interesting. Yes, and yes, applying the pyrolysis
Dr. Lam, can you conclude it, please? Yeah, thank you.
Yeah, sure. So we use it in different applications in aquaponics and in leachate treatments and also in mushroom cultivations and combining CO2 and steam pyrolysis. And then yes, we've been writing a couple of pyrolysis review articles. So we publish in some interesting journals, if you can have a look at it. Yes, and also, yeah, we still keep on applying grants. And yes, I welcome you all if you would like to collaborate with us in these fields: waste and biomass recovery, techniques, and application of microheating. That's all from my sharing today. Thank you very much.
Okay, thank you, Dr. Lam. Guys, it's a very interesting person. A lot of useful information. I wish that we have more time for him. Okay, let's if you have questions, so please post your questions in the question box, and then with attention to Dr. Lam, so we will address it in the Q&A session. Thank you, sir. Let me take over my screen.
You.
Just hang on just a second. Let me take over my screen for a minute. Okay. Okay, the next presentation, keynote lecture, is on the second generation biodiesel production from triglycerides. A presentation will be done by Professor Junming Zhu. Is from the China Academy of Forest, China. Let me brief about him. This is Professor Junming Zhu. He works at the Institute of Chemical Industry of Forest Products, the Chinese Academy of Forestry. His research is focused on the thermochemical conversion of lignocellulosic and triglyceride biomass for production of liquid high-grade fuels. His research interest also includes fundamental mechanism exploration during thermochemical conversion process. He undertakes a national key R&D projects. He has finished the National Science Fund for excellent young scholars. He has published over 100 papers. He was awarded the 14th China Youth Science and Technology Award, 13th Forest Youth Science and Technology Award. He was selected as a top-notch youth talents in the 10,000 people plan of Central Group of China. He won National Science and Technology Progress Award for one time and a provincial ministerial level Science and Technology Progress Award for 4 times. He has excellent track record. I'm sure you find this presentation very useful. Let me ask him to share his screen. Professor Junming. Okay. Yes, okay, you're on. Okay. Hang on just a second, please. Okay, can you unmute your speaker, sir? Professor Junming, can you please unmute your speaker? Okay, yeah.
Can you hear me?
Yes, I can hear
Chairman,
you.
can you hear me?
Yes. Yeah.
Can you see the slides?
Yes. Can you go back to the first slide again? Yes. Okay, good.
Okay, thank you. Okay, so thank you, Chairman. And I'm very glad to here to share our observations regarding our research regarding the second generation biodiesel production from the triglycerides, mostly from the natural plant oils. And my content will be divided into 5 sections. And the introduction of green diesel, and the second is non-catalytics, the thermal cracking process for production of the second generation biodiesel. And the third part is catalytic cracking process that can be used to produce a second generation biodiesel. And the fourth part and the fifth part is the hydrogenation process to produce the second generation biodiesel. First, let me introduce our institute. My institute located in China, the southeast of China, is Nanjing City, and our institute was very close to the Xuanwu Lake, and is a very beautiful city. And we also have the pilot place of our institute that can do much more pilot experiment more than the lab scales. And this is the institute of our institute, and we have the have 3 buildings that can all the staffs working there, and we have almost 200 staffs working in our institute. And this is the National Forest Blue Pilot Study site that are located in north of the Changjiang River, that can be used to do some large-scale experiment. And our institute was founded in 1960, and have the 60-year-long histories. We focused on the chemical processing and the utilization of wood and non-wood products that most from the forest resources that can be generate the liquid fuels, the gas fuels, and also the carbon materials. And my institute have the 10 research directions, and including the biomass energy, chemical, some biomass new materials, and natural products. We also have the wood pulping, resin chemical, the activated carbon, and more some research fields. And first, I want to introduce the green biodiesels. The biodiesel include one generation biodiesel and the second generation. And the first generation biodiesel was contained FAME, the fat acid ester methanol esters, and the global production of the biodiesel, including the first generation and the second generation, is about 40 million tons. And most of the biodiesel were produced by European and American countries. Another 2 concern is that the global production of the second generation biodiesel is over 5 million tons, and I think it will be more and more in the near future. And then it is the synthesized pathway of the biodiesel, that is the natural triglycerides. Most is the plant oil, like the palm oils, rapeseed oils, soybean oils, that can be used to produce the first generation biodiesel through the trans-esterification method. And today that we can use these materials through thermochemical and the catalytic cracking process and the hydrogenation process to generate second generation biodiesels. The main ingredients in the first generation biodiesel is fat acid, methanol esters, and the second generation biodiesel is hydrocarbons. Is a long-term alkanes, have the similar properties with fossil fuels. This is the conventional technologies that can generate first generation biodiesels through the trans-esterification conversions. That the plant oils can be reacted with methanol under the catalyst of the basic catalyst to generate the biodiesel, and we also get the glycerol as a byproduct. And the second technology is the thermochemical conversions to produce the green biodiesel. In this method, hydrogen is not necessary in this process. Thus, plant oils can be converted to hydrocarbon through the oxygenation reactions. They can convert it by heat without catalyst, or can be catalyzed by basic catalyst or mocclusive catalyst without hydrogen. And the third pathway, that is the hydrogenation conversions. Usually, this kind of reactions can be divided into three pathways. First pathway is decarbonylation to remove the carbon dioxide from the plant oils to generate alkanes. And the second pathway is removal of carbon monoxide. And there is the third reaction pathway, that is react with hydrogen and the oxygenation to form the water and form the alkaline products. This is the non-catalyst conversion process. So far as I know, in World War II, there is the process that can produce the hydrocarbon fuels to the motor fuels in China in 1947. That is the non-catalyst thermal conversion of the tone oils. So far, we know that there is a pathway, the technology can convert the plant oils to hydrocarbon oils, but we don't know how to change the reaction pathways, and we don't know much more about the reactions. So we have some model compounds to determine which pathways can which reaction pathways is mainly that can deoxygenation through the different process to generate the products. And we studied the deoxygenation mechanism by Gaussian software. The carbon monoxide and the carbon dioxide can be carbon monoxide and the carbon dioxide can be generated to realize the deoxygenation reactions and to form the alkaline products from the plant oils. We also calculate the activated energies during the pyrolysis, the whole process. We found the pyrotic temperature is about 573 kelvins, and we also use TG and IR analysis to check the changes of component during the pyrolysis without any catalyst. during the reaction, and we recorded the carbon monoxide and the carbon dioxide. That is the product that that is represent different reaction categories. And this is alkyl radicals. Because we check the terminal alkynes, alpha alkynes in the product. We also investigate the alkyl radicals during the. We also calculate the reaction rate constant during the reactions. And the third part is catalytic correcting of the catalytic correcting of plant oil to generate the hydrocarbon fuels. In this part, several catalysts, such as the mantle catalyst and the mocclusive catalyst, will be used to catalyze the triglycerides to produce the hydrocarbon fuels that can be used in motorcycle and other and used as transportation fuels. First, we checked the several catalysts that we use in the catalytic cracking process, but we find something different from the thermochemical conversions, because some catalysts present have the higher liquid production during the low temperatures, and we find using different mantle catalysts, they have different activation energy. That means some reaction pathways can be different by using different mantle catalyst, and the active energy is different. So if we find some efficient catalyst in low temperature, that we can save a lot of energy during the pilot experiment, even the industrial scales, even in the industry. So we also study the mechanisms of the catalytic cracking of plant oils. We find a very important intermediate, that is carbon chain free radicals, which can be used to form the offerings in the products, which is very important to upgrading the products, because the offerings can be further converted to to form the branched alkynes, branched hydrocarbons, which can decrease the which can improve the cold flow properties that can be used in cold area. And this is the upgrading of the products. We using the pyrotic oils catalyzed by mocclusive and followed with hydrogenation process. When we get the jet fuels and diesel fuels, two kinds of upgraded fuels. According to our analysis, the physical and chemical properties of the biofuels that can meet the requirements of the jet fuel and the transportation fuels. And the fourth part is the hydrogenation of the fat acids to produce green biodiesel. During the refinery process of the plant oils, I think in the whole world, there is an acidified acid is a byproduct can be made in this process. Further, this acidified oil can to generate the fat acid oils. This kind of materials is cheap enough to produce the hydrocarbon fuels in China. So we first studied the hydrogenation of the fat acids over different catalysts, and we found the nickel and this kind of two metal and oxidized catalyst is effective catalyst. And we also study the support and the atom ratio of the two metal atoms of the catalyst, and we get the most effective the catalyst during the production. And the reaction temperatures and the various different kind of materials is also be used during the process. We also analyze the catalyst, different crystalline phase, and the interactions between the two metals. We also checked during the characteristics, and we also using SEM images, TM images to check their the active site of the catalyst and the reaction pathways of these reactions. And the possible reaction pathway is the fatty acids can be decarboxylations to form the carbon dioxide. But the most reaction pathways is dehydrogenation of the fatty acids to form the long-chain alcohol, and first and followed to dehydrogenation to form the alkanes. This is a mechanical studies of the second generation productions. We think the fatty acids will first connect with the mental site of the through the hydrogen bond, and the second, the hydrogen was divided into two the hydrogen atoms in the surface of the metal, and the hydrogen atoms were transferred to the fatty acids and form the hydrocarbons. And the fifth part is the fatty acid ester. That is the first generation of the biodiesel can be converted to second generation biodiesel through two metal catalyst. And this is the catalyst characterization of the catalyst by different catalyst And we also studied over different the catalyst, and we found the nickel and the aluminum oxide is the most effective catalyst, and the aluminum atoms is very important in the supporter because they have a very important function that can connect with the fat acid. And we also compared the catalytic activities and with the conventional catalyst, and we found that the catalyst we prepared is an effective catalyst. And we also studied the reaction parameters using different materials and compared with commercial catalyst.
Professor Xu, can you please conclude? Thank you.
Okay. And this is the mechanical studies that we found the aluminum atoms is very important during the reactions. So they can connect with the reactor and transfers hydrogen to form the to the carbonyl groups and form the final products. And we also studied the reusability of the catalyst, and the catalyst can be used for 5 times, I think, 5 times. And this is a brief introduction of our research teams. And in China, over the past 30 years, we studied the thermochemical conversions of the biomass in China, and our technologies have been applied to all over the China, and some of the technologies were exported to the 12 countries. And we also get the rewards from Chinese government, and many papers have been published, and the patent also. Thank you for your attention. That's all my presentation. Thank you.
Thank you very much, Professor Xu. Guys, and now it's open for the Q&A session for both speakers, Professor Lam and Professor Xu. I received a couple of questions already. Please post your questions in the question box. Just let you know that there will be no break with the next session because we are behind the schedule, but I like to have these questions to be answered so that some of you benefit from this discussion. So once the discussion is over, we start next session immediately. Okay. So, but I like to let the question and answers just to be started. Just give me a second. Let me take over my screen. Okay.
How many? I'm sorry. How many questions you received?
We have 1, 2, 3, 4, 5, around 10. Let's let 10. Yeah. Okay. I request both of you to. I know, Dr. Professor Xu. Maybe some more people make questions. Only one question so far for Professor Xu, but mostly questions are addressed to Professor Lam, and let's see any other people asking Professor Xu. But both of you try to be as brief as focused to answer it. Yeah. Thank you. Let me. Yes. Here is a go, Professor Lam.
Yeah.
Okay.
Oh, okay. Can you all hear me?
Yeah, all good.
Yes, no problem.
Yes.
All right. I'll just go straight. I can see the question here. I'll just answer straight away then, if that's okay.
Sure.
Right. The first one, how many types of feedstock we can mix? Oh, so far we have tried mixing 3 types of feedstocks. But of course, first you need to check the properties of the feedstocks. But so far, we have been trying maximum 3 feedstock at one time. But more normally, good results will be from mixing 2 types of feedstocks. And we have waste, plastics, and also cooking oil. Okay. And what are the oxygenates present in? There are quite a couple of different oxygenated compounds in biofuels. But I mean, to name it out one by one, it will be quite tedious. I can roughly say about the percentage of the oxygenates present in biofuel. We can control it in, between 10 to 20%. So if 10 to 20%, of course, it depends on the initial oxygenates present in the feedstock as well. And how to reduce the water content in the final liquid fuel. Okay, yes. Initially, we will try to do pretreatment on the feedstock before we subject it to pyrolysis process. So normally, of course, you will remove the water by heating and vaporize the water away first. Okay, so when you actually get the final liquid oil, our water content is actually not that much. I think it's less than 10%, if I'm not mistaken. And because you got a lot of oil, and even if you have water, it has a very clear 2 layers, so it's very easy to separate. And including further cleaning steps after pyrolysis starts to optimize. Yes, you need to have some additional steps if you are talking about pyrolysis sewage sludge. But of course, first you need to ask yourself, are you targeting to produce liquid oil from the pyrolysis of sludge, or are you targeting to produce a char product or gas products? So if you are talking about the liquid fractions, yes, the kind of the liquid oil that we obtain from the pyrolysis of sludge is, it's a bit viscous. So you need to have another steps to dilute it. To dilute the viscosity of the liquid oil. So yes, you need to have some additional steps. I didn't explain further here, but definitely you need to do that. And yes, next questions I can't see here. Pram, yeah. Oh, how to publish paper in Science? It's not. This depends on how to say that. It depends on, first, of course, networking. You cannot work alone. You need to really work with some experts. And when you work with experts who are very active and knowledgeable and also have experience in publishing in Science, that can be an advantage. And also, when you work with these kind of experts, who have published in Science, so they have knowledge, they will guide you. And of course, they will keep your momentum on. So that's what I can share. And how about the continuous running? Okay, pyrolysis, if it's okay if you want to do it in continuous operations. As you can see in China, I think China is a country that works a lot and develops a lot of technology on microwave pyrolysis, and they have been doing this in continuous operations. So it's not a question of whether we can do it. It's people are already doing it. How competitive the bio oil produced by you can't compare the bio oil with conventional fossil fuel. Of course, it's 2 of them. They are all fuel products. Okay, so you can't say, oh, this bio oil is better than fossil fuel, and then you use the bio oil and then you don't use the fossil fuel. They are both important to me. So there's no competitiveness. But so far, if you talk about really the costings of producing bio oil, of course, is still higher compared to conventional fossil fuel. But I'm sure we are moving towards that directions in reducing the operating costs and the processing costs of the bio oil so that it can be used in more applications. I'm wondering the uniform of reactions during, especially okay, yes. You are this is right. With respect to maintaining the uniformity of the reactions or in microwave pyrolysis, yes, you need to have some techniques as well. it's not about the uniformity of reaction, it's about maintaining uniform heatings, meaning that you have a well distributed of heat on, towards, the waste and also the feedstock in the reactor. So to do that, you have some techniques to do that. Of course, you can use a stirrer, or you can use we call it a microwave propeller. You can install something in the microwave reactors to make sure the microwave radiations is channeled evenly to the microwave reactors. That can be a way. And also the other thing is, if you want to maintain uniformity of the heatings, you can also add some microwave absorbents into the reactors, and in that case you stir it with the microwave absorbent, you will have a uniform heating, and that will produce better results. And yes, microwave is sensitive to the composition of raw materials. As I say, microwave can be good to heat some materials, and can be for some materials you can't heat it at all. So for those that are non-polar compounds, normally they cannot be heated by microwave. You need to add microwave adsorbent. That's one of our approach. Okay, and the limitations of the microwave penetration depth, optimal design. Oh, if you want to optimal design, okay, I can share two things. One is you can't use microwave oven. You need to use microwave magnetrons. Okay, meaning just take out the microwave magnetron and then plug it to your reactors. And you have to use multi-mode and not single mode. If you are talking about the technicality of scaling up the process, it's better to use multi-node. I think that's all I would like to share. Thank you. Pram, yeah, I think I've answered that. Prof. Shi, your turn.
Okay, what is the oxygen content in second generation biodiesel? I think the second generation biodiesel that generated by the pyrolysis or by the catalytic cracking or the hydrogenation process, they generated the product is alkanes. The alkanes they have the same the same molecular with fossil biodiesels. So they have the same molecular with the fossil diesel. So that the oxygen content can be controlled by the process. Usually that can be nearly zero. So they have the second generation biodiesel have the high heating value. They can blend with traditional diesel with any proportions.
Okay.
So I think.
Go on.
Okay. So, and what are the oxygen molecules identified in second generation? Okay. So the oxygenated molecules we can identify is long-term alcohols. Maybe that is a small amount of the long-term alcohols in the second generation biodiesel. But the content can be also controlled by the process. If we intensify, we have the more hydrogen and the higher pressure during the process. That's the oxygen content, including these molecules, oxygenated molecules, can be eliminated. And that's my reply. Thank you.
Okay, thank you, Professor Xu. Professor Yoshaka, you want to ask some questions? We have some time left. Or would you like to conclude the session?
Yeah. I have no questions, and thank you very much for your interesting talk. And yeah, and this session is applied pyrolysis, and especially the focus on the biofuels now, and especially the production of the biofuels from biomass. In the this content is a very focusing, and then all people's idea fix of this processing to make biofuels for biomass, because due to the environmental global warming issues and the plastic issue also. And especially the Asian area is good and resources of the biomaterials. And we want to, and we like to continue to discuss with these topics. And today, we and all of the participants could give useful information from this presenter. Thank you very much for your very interesting presentation. Thank you very much.
Thank you. Thank you all. Thank you, the speakers and this Professor Yoshaka-san for taking care of this session. I was thinking of maybe I don't have the break time, but I think we still have some break time now. So we start in 10 minutes time. Okay, let's next session starts in 10 minutes. Please take a break and go to the toilets or to get some coffee or tea or have a quick lunch, whichever it is. We start in next 10 minutes. So session 5. Yeah. Thank you. Bye-bye.
Thank you.
Thank you very much, Dr. Su and Professor Su and Professor Shu. Thank you very much.
Thank you.
Bhavya, are you there?
Yes, sir.
Okay. Did you practice before, right? The session, the how to share the
Yes,
screen?
sir. Yes, sir.
Know about
Yes,
it.
sir.
Okay, fine. Okay. And next is Saurav. Saurav,
Wise.
Saurav is not here yet.
没有，我在
Dr.
想，
Omraj. Dr. Omraj.
Yes, hello.
Hi there. Can you can you quickly I'll let you share the screen.
Okay.
Yeah.
Yeah.
Let me send you the. Yeah. Okay. Can you please share the screen?
Yeah. Okay. Let's see. Can you see that now?
Yes. Okay. I see the desktop. You get it ready. Your the presentation file. Okay. When I.
Okay, I need. No, I have the presentation on my other screen. So can I switch from one screen to another? Is that possible?
I think so. Yeah.
Right. I need to find out how. Or I'll just let me move that to the other screen. That might be easier. Let's see.
Okay, now I see your PowerPoint. Okay, okay.
Yeah, can you see the proper slide, or is it the presenter view that you are seeing?
I think what I see is a presenter view. You need to remove it. That one. Yes.
Yeah. Okay. So now I really need to find a way how to switch the display because that's the way it's presenting.
The next one. You know, on the menu, on the second middle one. I think you can find it. Middle one on the menu.
Yeah. Change presenter. No. Show screen. Okay.
No,
this one. Okay.
Display. You see the display. No, sorry. Yeah. Okay. This is good. Yeah, this is good. Yeah.
It's good now.
Yeah. It's
okay.
Good. Yeah. Okay. Okay. I know. So now you know how to. Yeah.
Yes.
Thank you.
Yeah. Okay. Thank you.
Let me take over my screen. Yeah. Okay. Dr. Chong, you are there? Dr. Cheng.
Yes, I'm here.
Okay,
Yes, I'm here.
so you know the ritual, right? How to get to the trans file, yeah? Yeah?
Yep.
Okay, cool, man. Cool. Okay, Ulash, are you there? Ulash. Ulash is not here. There are two disappeared. Guys, anyone know Dr. Arshad Salema? He's not logged in yet. If you know him, please ask him to log in. I could not reach him out. Appreciate the help. Okay, Ulas, are you there?
Hello.
Hi, Ulas. Can you hear me?
Hi. Am I audible now?
Yes, it's clear. Yeah.
Okay.
Thank you. Please stand by. Yeah.
Yeah, sure.
Okay, guys, welcome back. We are on the session 5 now. I hope you guys have a quick break with coffees or go to the natural calls. Okay. Okay. The next session is focusing on the session 5, the day 2, focusing on applied pyrolysis, biochar, and biocarbon. This session is supposed to be chaired by Dr. Arshad Salema. Is a part of the technical committee as well. There are some internet issues. He was unable to join, but at least I'd like to brief him about him. Hopefully he can catch up in the later on. He's based in Monash University from Malaysian campus. Dr. Arshad is a senior lecturer and a course coordinator of mechanical discipline in the School of Engineering. He is very much passionate on the clean energy, fuel, and chemical research area, especially is working in renewable energy process design and development of thermochemical reactor, microwave reactor, and processing, product analysis, energy efficiency, and sustainability. He did his PhD in mechanical engineering from the University of Technology Malaysia in 2012, and he did a master's in also from same university and a degree in chemical engineering from University of Pune in India, 2002. Well, he's not here right now, so let I take over for the time being on this session. Okay, today's this session is focusing on, we have one keynote lecture and the other one is an invited lecture, and we have four oral presentations. So the way we present is first let's finish the presentation, all the presentation, then we go for Q&A session. All the speakers are requested to be online so that you can answer the questions at the end. Okay, so let me get to the keynote lecture. Okay, and this is on engineered biochar for sequential biochar user system. And it is presented by the Dr. Ondrej Masek. Is based from the UK Biochar Research Centre, University of Edinburgh, UK. Let me brief him about him. He obtained his PhD in material engineering from Hokkaido University, Japan in 2007. After working on carbon capture technology at Cranfield University in 2019, Dr. Masek joined the University of Edinburgh as a co-founder of the UK Biochar Research Center. At the center, he has established a range of pyrolysis facilities, leads a group of focused thermochemical conversion of biomass and waste. The key areas of research include biochar engineering and matching to different agriculture, environmental, material, and construction application. I'm sure you find his presentation is very useful. Let me, welcome Dr. Ondrej Masek to make a presentation. Yeah. Okay, let me share the screen for him. Yeah, there we go. Okay, Dr. Masek, are yours now?
Thank you. So I'll just make sure that my screen is visible.
Yes.
Can you see my slides?
Yes, all good, yeah.
Excellent, very good. Okay, so well, thank you very much for the introduction, and also I'd like to thank the organizers for giving me the opportunity to present here. As already said, the title for my presentation is Engineered Biochar for Sequential Biochar Uses, and this builds on the work that we have been doing over the past number of years, and represents work done by a number of people in my group, but most of the work presented today here has been done by my PhD student, Christian Wurzer, who is the co-author on the presentation as well. So let me just move. Okay, yes. So I'm talking to you today from the beautiful city of Edinburgh in the north of the UK, in Scotland. We are moving from autumn towards winter, so losing the beautiful colors you can see on the pictures here, and moving to sort of a more the dark period. So it's still dark outside as I speak to you now. The city of Edinburgh is home to the University of Edinburgh, which is an old university. It's quite a large university with very intensive research, both in the past and present. And you can see here some famous alumni associated with the university. As mentioned in the introduction, I moved to the University of Edinburgh back in 2009 as a co-founder of the UK Biochar Research Centre. The UK Biochar Research Centre is a multidisciplinary centre that's focused on a lot of different aspects of biochar. As you would all appreciate, biochar is quite a complex area. It involves engineering, it involves agriculture, it involves environmental sciences, biological sciences, and so on. And so what we have from the very start tried to do in the center is to bring in all that expertise under one roof so that we can maximize and benefit from the synergies that this offers. So rather than having a center that covers one particular aspect, what we have tried to cover, not of course all, but as many as possible within the center, and then the rest through widespread collaborations with colleagues around the world. So the areas we do cover in the center are the engineering, so the technology for biochar production, development of the processes and the characterization of the materials we obtain, but also soil science and environmental science, so looking at the applications of biochar in those different areas, and also bioenergy, so looking at how do we use the co-products, so the gases and the liquids from pyrolysis in the most efficient way. And that can be either for heat or electricity production, or preferably for higher value products such as different type of chemicals. In the center, we have a range of facilities for biochar production, ranging from very small scale. So here we have a thermogravimetric analyzer on the bottom end here, and all the way to pilot scale facility shown in the upper corner. So that's capable of processing up to about 50 kilos of biomass per hour, producing tens of kilos of biochar, depending on the feedstock and the processing conditions. So quite a significant range of capabilities here in terms of production of biochar on a laboratory scale for characterization purposes and testing, and all the way to scale up to semi-commercial scale, where we can, and we often do, work with industries to test their materials or to develop biochar or carbon-based products for their applications on a scale that's not too far from what they would require in their operations. These production facilities are complemented by extensive range of state-of-the-art analytical facilities, both within our school, but also across the campus, so the whole university, and in laboratories of our collaborators. So we can do extensive analysis and characterization of all the different products. So not only the solid, the biochar, but also the liquids and the gases, which then help us to best identify the potential applications. We used these facilities also to develop the so-called UK Biochar Research Centre standard biochar set. You can see it on the picture here. That's a set of 12 biochar materials produced from 6 different feedstock under 2 different temperatures. And this has been used extensively by the global research community. So to date, we've provided the samples to over 130 research groups worldwide, a lot in Europe, but elsewhere around the world as well. And this has been really an exciting project or an activity where we've tried to develop a standardized material that's reproducible and very well characterized, that can be used by anyone doing research on any aspects of biochar as a comparison material that then allows comparing results from different research projects that used this as well as other types of biochar. And this has been really great. And here you can see some of the applications that the standard biochars have been used in. I'm not going to go through all of them in detail, but you can see it's not by any means limited to one type of, let's say, soil applications. There are applications here in sensors and construction materials and so on. So a lot of different applications, and all of this using the same material. So it becomes really interesting to compare the results that people got in very different applications using the same material. So regarding biochar applications, as you all know, there are a lot of different applications. Some of them have been shown on the previous slide, and there are many more listed on the slide here. And there are different areas, and within each of those areas, there are again different applications for biochar. So it's a very rich field in terms of the number of applications and the type of research that's going on, and that also justifies the huge number of papers published on biochar every year. What I'll focus on here is just 3 areas and provide some examples of where biochar can be used. So one of them is for soil applications, for wastewater treatment or drinking water treatment. And okay, I received here a request for sharing my screen. Can you see my screen? Can I just check?
Can you please accept it, please?
Yeah, okay.
Thanks.
Is that working now?
Yes, fine. Yeah. Sorry for the interruption.
Okay. No, that's fine. Yes, and the third one is anaerobic digestion. So I'll just provide a few brief examples for each of these based on the research we have been doing. And also I wanted to introduce, although I'm sure many of you are familiar with the concept of engineered biochar. So here I try to schematically show the 2 different concepts. So one is a non-engineered biochar, where we have a biochar that's produced from certain feedstock in a process. It can be gasification or slow pyrolysis. And we can then apply it to anything we want. We can apply it to construction material, we can apply it to soil, without any specific modification of the biochar or matching of the biochar to what is required. So here we have the box that represents the specification, the requirements of a given application. And here we have 2 types of biochar that we obtained from our materials and processes. Now, if we try to use this biochar for the application, well, this one sort of meets the requirements to some extent, but it's not great. and the second biochar does not meet those requirements at all. So it's really not a great biochar to use for that particular application. It may be perfect for another application, but not for this one. The concept for engineered biochar is to produce a biochar that's optimized, it's tuned to have the properties required by that specific application. Whether that's agriculture, horticulture, or building materials, or anything like that, it's engineered for that. And then, unsurprisingly, we have a perfect fit. So we have a material that delivers exactly what's required from it for that specific application. It may be very bad for another application, but it's developed for this particular application. So here are the few examples I mentioned of use of biochar. So starting with the application in soil, this is a meta-analysis we've done and published looking at the effect that biochar has on water or moisture retention in soils. We are looking at the different textures of soil. So here on this example, you can see the coarse textured soils, so sandy soil, and the fine textured soils. And we can see that the biochar has a positive effect, but the effect is larger in the coarse textured soils. And it also depends on the feedstock, the particle sizes, surface areas, and so on and so on. So there is a lot of information here. This opens up the possibility of engineering biochar for this specific application. So we can, for example, see here that the higher the surface area, the better or the higher the water retention. So if water retention is what we want, we should probably aim for the biochar with higher surface area, and so on. So there is a lot of information that can be used for optimizing biochar for this application. Another application is the use of biochar as a support for microbial biofilms. That can be then used for a number of applications in water treatment. It can be used in soils as well, and so on. So depending on what we want the microbes to do. We have a project running at the moment that's using the biofilm to clean drinking water, to remove toxins from the water. So that's another potential application. And the third one and the last one for the examples I'll be giving here, there is the potential of using biochar in waste biorefineries based on aromatic digestion. There are different ways how the pyrolysis process and anaerobic digestion can be linked together, but that's for a different presentation. What I want to show here is the possibility of using the biochar, either the one produced from this residues from AD process or another biochar that's been specifically optimized to that, and we can use it in the AD process to improve the yields of methane. And here you can see some results from our work where the top curve here, so that's a product now. So this has been patented. It's called Krichar, and a spin-out company from our group, Carbogenics, is now commercializing this product. And you can see that there is a significant increase in the yield of biogas and methane. So I would say typically up to about 25% increase with a very small amount of biochar used. So this becomes a very interesting proposition for operators of biogas plants. And again, it's not all biochar that does it. So you can see some of the standard biochars here, even commercial activated carbons, and so on. They do not perform as well as the other types of biochar, so the Krichar in this case here. So there is again a lot of engineering that goes into preparation of biochar that works very well for this particular application. So back to the slide we had before. So we can have a biochar that's prepared specifically for an application, and it performs very well in that application. However, we don't have to do it only that way. So we don't have to have just one single use. We can actually identify sequences, or perhaps we can have one use followed by another, and so on. And there could be a number of different steps. So in this case here, we can have 4 different steps, or we can have 3 in another sequence, or 3 in another sequence here, and with different final destinations for the biochar. And this is the sequential use of biochar that I want to focus on in the rest of the talk. So the sequential biochar system, as schematically shown here, builds on several key properties of biochar and some key assumptions. So one is that the biochar maintains its characteristics, so it's stable. It does not change dramatically during the use. And that's one of the requirements for biochar to ultimately sequester carbon. It needs to be stable over a long period of time. If it isn't, then it doesn't count as a carbon sequestration measure. It might still do a lot good for soil, but it wouldn't count as a carbon sequestration. We also need to consider recycling of the biochar to increase its lifetime and the efficiency. And here I would like to distinguish between the terms recycling and regeneration, where regeneration would mean we regenerate the material so it can be used back in the same process. So we need to basically bring that material back to the original properties it had before we started using it. Recycling, on the other hand, means we bring it back into the cycle of the different uses. So that might be slightly confusing sometimes. We do not need to bring the material specifications back to the original ones, which can often be very difficult, if not impossible. And then, so once we've done this, we can identify different sequences of operations or applications that nicely fit together when giving us the benefits we want. And I'll provide some examples on the next few slides. So the reason why we might want to do this is really economic as well as environmental. The economic case is quite simple. The production of biochar costs money, and it can cost quite a lot depending on the feedstock we use. Often virgin biomass can be quite expensive, but also that's a very nice and easy material to use for biochar production. Waste materials can be much cheaper, but they can be more challenging to use for biochar production. So bringing the price down is important. And there is a cost of the technology, the processing, transportation, storage, and so on and so on. So there is a significant cost involved in the production. And if we have only one application that needs to pay for that, then that can become challenging, and biochar may struggle to be competitive with established, even if less sustainable processes. And what we can achieve by getting several uses out of the biochar is that we can split the initial cost into several. So each of the subsequent uses pays or contributes towards the cost. And what can then happen is that we end up in a situation where the biochar actually, the first use is the cost of the biochar is lower than what the production cost would be. So we contribute less than the original cost. So it makes it economically competitive against other options. But we are not losing any money because the subsequent uses will pay the rest of it. So we cover the full production cost. And ideally, we end up in a situation where we have decoupled the carbon sequestration. So that's the last step, what the biochar does, from carbon price, because we do not need any payment for the carbon that's been sequestered. So that's the ideal situation where we have a basically free carbon sequestration. And there are not many technologies, if any, that can offer that. So this is a concept we have been developing under the European project called Green Carbon. The project is finishing next year. And so we have been doing already 4 years of research on this, and there are several published papers and still some ongoing work and more publications in preparation. One thing I would like to highlight here is that what we want from an ideal sequential biochar system is that each sequence, rather than degrading the quality of the biochar, actually makes it better for the next step in the sequence. So that's an important point to consider. Of course, that's for an ideal case, so it not always can be achieved. So here are a few examples of what those sequences may look like. These are hypothetical at the moment, and we are working on some sequences related to this that we are actually testing in practice. One thing to say here is that each of these steps has been already shown to work, so that is not a problem. It's not that we can't one of these wouldn't work. The challenge here is make sure that it's the whole connected system that works, so that there isn't, for example, any contaminant introduced in any of the steps that makes the subsequent step perform poorly or not perform at all, and so on. So the issue is not with individual steps in any of these sequences. The challenge here is how do we make sure that it's when when they are connected, that they all work together. And I'll show a few examples of what we have been working on. The important part of these sequences is the recycling step. So that's the step that allows us to use the material in the next step. So rather than the bringing it back to the first use again, we prepare it for the next use. And what's critical here is that this step is much cheaper, or considerably cheaper than production of a new biochar. Because if that's not the case, then it makes more sense to produce a new biochar specific for the next application rather than doing the recycling here. So that's one condition. It needs to be cheaper. The recycling step also allows us to alter the properties of the biomass or the biochar material and improve its fit to the next application. Sometimes we may not have to do that if we have nicely matched the different applications, but in many cases we need to do at least some tweaking. So here is an example of a project we have been working on for the past several years. That involves engineering of a biochar mineral composite material. So this is not just a biochar produced from biomass, we actually add minerals to it. We then use it for removal of micropollutants from water. That biochar is then used for removal, for purification of biogas, before then finally used in the soil. And what we want to achieve is to have benefits in each of the steps of the process. So the first step involves the synthesis or the production of the biochar. This is where the engineering sort of the biochar comes in, and the engineered biochar concept, because we already know what we want from the application. So we prepare the biochar to have the properties we desire. So in this case here, we've used mining waste rich in iron to produce iron enriched and magnetic biochar that has a very good absorption performance, but also can be removed from the water medium that it's treating using magnetic field. So combining several important properties here. And what we then want to make sure is that this performs well in absorption of the contaminants we are after. And here we investigated or we developed biochar that was good for removal of 10 different pharmaceuticals from water. This work has been already published, and there is a link to it here. So if you are interested in more details, please feel free to have a look at the paper. It was published about a month ago or so. The next step, after we've developed this biochar and we've tested it for absorption, and we've shown that it works very well, we need to do some of this the recycling step. So we want to make sure that the pharmaceuticals that are taken up by this biochar can be safely removed, so we can use the biochar either again in the same cycle or safely use it in the next step, in the next cycle. So here we've developed a new hydrothermal treatment or hydrothermal recycling step, where using a hydrothermal process we can decompose the micropollutants that were stored by the biochar, and we have shown that this can be done very effectively. And again, the engineering step was important here. The addition of iron additive significantly improved the regeneration. So you can see here, so the 10 means we have added 10%, iron had 5%, and we have a significant reduction in the remaining contaminants in the biochar in a hydrothermal treatment at 280 degrees centigrade. So again, this modification of the biochar significantly improved its performance in the regeneration steps or the recycling step. The next step in the sequence then is the use of that biochar in purification of biogas. And here specifically we are looking at the removal of siloxane, which is a common micropollutant in biogas, and it causes a lot of problems in combustion engines when the biogas is used for electricity generation, leading to mechanical damage. To regenerate a carbon-based material that's been used for removal of siloxane is very difficult and inefficient. The efficiency is less than 50%. So what we want to wanted to look at here is the potential of recycling it so that we can use it that carbon material for something else. And so we would end up with a silicon enriched biochar. And so that's still ongoing work. So the experimental work is ongoing as we speak. And we are looking at different thermal treatments, again, using hydro treatment, but also thermal recycling at low and high temperatures to stabilize the silicon carbon bonds in the material. And we want to, the aim is to produce a silicon enriched activated biochar that can be used either for soil applications or for, as a ceramic mineral biochar composite for construction applications.
Dr. Wunter, can you conclude, please?
Yes, I'm almost at the end. And that's the final step here is the use and testing of these materials in those applications in soil and in construction. And that's my concluding slide here. In conclusion, very simple a few statements. So biochar can be engineered to perform very well in a large number of different applications. The challenge we have been tackling here is how to make sure we engineer biochar that performs well in a sequence of applications, because there are a lot of potential synergies between different applications that we can utilize to make it better. A last note of caution, there are, besides synergistic effects, there can also be antagonistic effects, and these need to be considered carefully as well when designing such applications. Thank you very much, everyone, for your attention. I'm more than happy to take questions later on.
Okay, thank you, Dr. Masek. Guys, that's very interesting presentation of applications of biochar. Okay. Let's go to the next presentation. Okay. Let me take over my screen first.
Yeah.
Okay. Okay, the next this invited lecture. The presentation is on upgrading of bio-oil from biofuel to biocarbon. The presentation will be done by Professor Xunhu, Zinan University from China. Let me introduce him to you all. Is currently a full professor in the School of Material Science and Engineering, University of Zinan. He obtained his PhD degree from Chinese Academy of Sciences in 2010. From 2010 to 2016, he worked in Fuels and Energy Technology Institute, Curtin University, as a postdoctoral research fellow under the supervision of Professor Chunju Li, and later hold a position of Curtin Research Fellow in Curtin University. Since 2016, October 16, he joined University of Zinan and established a research group. His main research interest includes conversion of biomass into functional carbon materials for the use in catalysis and energy storage, the development of heterogeneous catalysts for hydrogenation or acid catalysts. He also works on the pyrolysis, hydrolysis of biomass and the conversion of biomass to biofuels, value-added chemicals, and carbon materials. As you see, he has extensive experience and knowledge. I'm sure you find this presentation very useful to you. Let me welcome Professor Xunhu. Let me share his screen. Okay. Can you please share the screen, sir?
Oh, yes, I have accepted that.
Yeah, okay.
Can you see my screen?
Yes.
Okay. Thanks very much for the introduction. Hello, everyone. This is Xunhu from University of Jinan, China. Today, the topic I want to present is the upgrading of spare oil. But I don't want to go to the detail of a specific topic. I just want to tell you a story about my research from the upgrading of the bio oil to the biofuel, then to the biocarbon, the co-factor. So a little bit of background information. We know that biomass can be pyrolyzed to produce the bio oil and also the biochar. For the bio oil, we can do the upgrading, typically the hydrotreatment to produce the biofuel. For the biochar, you can use it for carbon material or soil fertilizer. Biomass can also be hydrolyzed or gasified to chemicals or syngas. My focus is the upgrading or application of the bio oil. Bio oil, it has some special properties, and for some undesirable ones, at least below, it's corrosive and also it's thermodynamically stable, and it has a high water and oxygen content. This is make it has the lower heating value. So for the corrosiveness of bio oil, it's mainly from the carbonic acid in the bio oil. This table is a presentation showing the carbonic acid in the bio oil produced from the pyrolysis of many leaves. So it have a lot of carbonic acid with different structures. So this makes bio oil very corrosive. If you want to tackle the corrosiveness of bio oil, the easy method, the simplest method is acidification. So it's basically a reaction of the acid, like for example, formic acid with methanol, and it can form methyl formate. Most methyl formate is not corrosive, it's neutral, and also it can be used as a fuel additive. When we do this research, we found acidification is not just one simple reaction. Because when we do the acidification of the bio oil, we found a lot of reaction take place. So when we look at the sugars, the level of glucose is anhydrous sugar of glucose. We found at low temperature, its formation continues, and at high temperature, it was converted first hydrolyzed to glucose, and then react with methanol to form this glucopyranoside. But this is the glucopyranoside with the increased temperature, it was formed. But at a very high temperature, it was also converted. We don't know the reaction pathways. So we did the model compound study. So that's the story actually started from here. So I will give you 8 examples. To tell you why first I do the upgrading of bio oil to biofuel, and then I shift to the transformation of the bio oil to the biocarbon. So I did the model compound experiment about the conversion of level glucose in water and in methanol. I found that if we do the conversion in water, we get a low yield of level acid, but if you do it in the methanol, you get a high yield of the targeting product. So when you analyze the process, we found in methanol there are much less polymer formed. So I analyzed the mechanism for the formation of the polymer. Because the level glucose can hydrolyze to produce glucose first. In water, glucose can dehydrate, produce this carbon ketone. Carbon ketone can react with another molecule of glucose to form this sugar oligomer. And also it can react with HMF, this furan is a dehydrogen product of glucose to form some cross polymer. But in methanol, glucose can react with methanol to form glucopyranoside. In this way, it will not form the sugar oligomer, so the polymerization can be stopped. Similarly, for the HMF, this is, as I said, it's a dehydrogen product from glucose. In water, it can undergo this series of transformations to form polymer. But if this compound react with methanol to form this one, we just assume the same reaction pathway, and it will not polymerize to form this phenol. So the polymerization can be stopped. Following that study, we did another study about the conversion of xylose also in methanol and in water. And the detailed reaction pathway is like this. In water, xylose can dehydrate to form fefro, and fefro and xylose together, they can polymerize. In methanol, xylose will react with methanol to form this methyl xylopyranoside, and it eventually will dehydrate and produce the acetyl of fefro, but it can still also polymerize. But we still found the methanol still have some effect on the polymerization reactions. In water, we found these sugar oligomers, but in methanol, we could not, because methanol can suppress the formation of this sugar polymer. We further do the study of the conversion of the furans or still in the water and in methanol. We found the similar conclusion. We found in methanol, the polymerization of the fefros, the furans like fefro alcohol, HMF can be suppressed, so you get high yields of the targeting product, the level limit. But for fefro, it's a special case. In water, both in water and in methanol, it shows a high tendency to polymerize. The fourth example is I did the conversion of furan. This is furan itself in water, also in methanol. We found a similar conclusion actually. In water, we found that furan can polymerize, but if we do the conversion in methanol, it will form benzene furan. So this is reaction pathway. For the benzene furan, it was formed in methanol, but with the progress of the reaction, it can still polymerize. Eventually, you will go to the polymer. Okay, you can see the coke. Another example, I do the conversion of C5 sugars directly to level-limiting acid. The background is like this. The biomass contains cellulose, and cellulose, if you do the hydrolysis, it will produce C6 sugars. Then you can do the acid catalysis. You will produce directly level-limiting acid or it's ester. But for the C5 sugars, when you do the hydrolysis, it will produce fefferol, not this compound. I want to produce level-limiting acid from both C6 sugars and C5 sugars. So I designed a reaction route to convert the C5 sugars like xylose to the level-limiting acid. It's like the fundamental is like this. First, the xylose will dehydrate to produce fefferol, and then it will react with this compound. This is dimethoxymethyl, and it will be transformed into HMF. So HMF will be further converted to level-limiting acid. In this process, I found if we use pure solvent in this compound, as both the reactant medium and also the reactant will produce low yields of level-limiting acid, just about 10%. If we use the dual solvent mixed with this solvent mixed with this dimethylmethane with water, we produce even lower yields of these compounds. But if we mix this solvent, this dimethylmethane with methanol, will produce much higher yields of level-limiting acid. However, even in methanol, we found that this is the methanol level-limited the product for the reaction, but it will continue to react with dimethylmethane. Also, it will form polymer. So another example is still I focus on the polymerization reactions of the bio oil. We did the conversion of the bio oil in methanol, also in water. Actually, we used also other alcohols. And what we found is that in water, the coke yield around 27.6%. In methanol, the coke yield can be reduced, but still 15.4% is still significant. We also did the characterization of the catalyst after the esterification of the bio oil. The catalyst we used is Amarylis 70. It's a solid acetic resin catalyst. When we did the bio oil upgrading, specifically is the esterification. We found the catalyst deactivated. So the mechanism is because the catalyst, the hydrogen ions in the catalyst can exchange with the metal ions in the bio oil, and so also can react with the nitrogen containing organics in the bio oil, so it deactivated. But we can do the regeneration of the catalyst with the concentrated sulfuric acid. But we found that we cannot completely regenerate the catalyst because you see from the SEM pictures, there are some substance sticky and like a germ, something like that. This is the polymer from the polymerization of the organics in the bio oil, so you cannot just regenerate the catalyst. So the last example is we did a hydrotreatment of bio oil. We want to produce the biofuel. So this is the experimental setup, and this is the reactor. We separated we just marked into the different sections. We want to see the coking in the different section of the catalyst bed. When we did the experiment, we found that if you increase the temperature, you will see there is a very clear pressure increase. Increase very sharp. So you so you have to stop the experiment. And we also change the reaction conditions. We still can see the temperature also increase, so the operation is not stable. Then we open the reactor. We analyzed the used catalyst. We found in almost all the sections of the catalyst bed, you can see a lot of coke formed. So this coke formed in the catalyst bed, so it can block, it actually block the catalyst bed, so the bare oil and hydrogen cannot pass through. So you can see the sharp increase of the pressure. So we did the modification of the reactor. We saw the hydrogen is too cold, and so we preheated hydrogen, and then we feed the bare oil. So we want to bio react directly with the hot hydrogen, but this did not solve the problem. We still see the sharp increase of the pressure because the build up the coke in the catalyst bed. We continue to optimize the design of the reactor. We also preheat the bare oil, like they use this design, preheat both hydrogen and the bare oil. We still found the pressure just build up, so you have to stop the experiment. So this is biofuel we produced. At the beginning, you can see the color is light, it's yellow to brown, but with the progress of the reaction, it become black. That's an indication of the deactivation of the catalyst because of the coke actually. Yeah, this is another picture of the biofuel we produced. Just the experiment cannot last long, and the catalyst deactivate very quick because of the coke formation. So this is the picture. We open the reactor. You can see, I mean, the catalyst particles stick to each other, and in between the particles, there's coke. Just coke bound together the particles. So makes the catalyst bed very dense, and the oil and hydrogen cannot just flush through. So, so this is the reason and the deactivation of the catalyst, and also for stopping of the experiment. So I give you 8 examples. I show you that the bio oil or the components in the bio oil has a very high tendency to polymerize, to produce coke upon heating at low temperature or the high temperature. So what to do next? I think this, if bio oil is so easy to polymerize, this can be an advantage to produce carbon materials from bio oil itself. So we change our concept. We don't produce biofuel from bio oil. We produce biocarbon or carbon materials from bio oil. So I designed I think it's a new process to produce carbon materials from bio oil instead of producing biofuels. So the process is like this. First, we pyrolyze the biomass. We produce bio oil and biochar, and then we mix bio oil and biochar with PYRO. PYRO, we use it as a polymerization agent. Then we mix these three together. We produce this carbon. This carbon actually is very hard, and I call it the high strength carbon materials. So another picture to show the concept. For the biomass, we do the pyrolysis first. So we produce biochar and bio oil. We also can do the hydrolysis. We produce PYRO, and for the solid residue, we can further do the pyrolysis, produce additional biochar and bio oil. Then we mix PYRO, biochar, and bio oil together. So we do the polymerization at the temperature of 250. Then we got the high yield of the biocarbon. It's around 90% of the yield. It's a high strength carbon. Then we do the carbonization. We can also get the densified carbon material. This is the yield of the biocarbon if we use different formulation of the reactant. PYRO is very effective. Also, it's not effective. You got almost above 90% of the carbon solid. So why PYRO can act as a polymerization agent? This picture is from my previous study. For the PYRO itself, it contains multiple functionalities. It can open its front ring, and it can form some very reactive intermediates. So I think this is the reason it can be possible can be used as a catalyst for the process, or as or accelerating the polymerization process. This picture is from other study. This reaction was confirmed. I mean, these compounds are typical compound in the bio oil, and I did the model compound experiment. I want to see and if these two can be polymerized together, and the result confirmed. And no matter hydroxy acetone or cyclopentone or aldehydes or furans and HMF or phenols all can react with PYRO to form some form some heavier products. So I also did some calculation about the products from the polymerization between bio-oil and PYRO. It's a dense carbon material. I mean, you can say I call this like a melting rock. This like broccoli, and I think for the bio-oil, it's a complex mixture of organics and different organics. I think can react with PYRO with the different reaction pathways. So you got a different form of the carbon material. So what's next? I mean, we produce the carbon materials, and now we are exploring its applications. Okay, okay, yeah, that's all. Thanks.
Okay, thank you, Professor Ginhu. You're on time. Thank you very much, guys. I hope you enjoyed. I hope you enjoyed the presentation. Let me take over my screen.
Okay.
Yes. Okay, now we are into the oral presentation section, and the first presentation is on the pyrolyzation of lignin obtained as a byproduct from biomass conversion processes. The presentation will be done by Dr. Bhavya Krishna. She's a senior scientist at the Indian Institute of Petroleum based in India. Let me brief you about her profile. She has a research experience of 10 years and specializes in the validation of these several biomass feedstocks such as the agriculture, forest residues, aquatic biomass, and oil cakes. Experience in the thermocatalytic methods of conversion, currently involved in the identification of locally available biomass residues and underutilized feedstocks for targeting the local requirements. And also she's several market survey studies and to understand the supply demand of the biomass derived from derived products and byproducts. Core team member in various projects sponsored by the Government of India, Indian industries, national and international funding bodies for the biomass waste utilization. She has published 28 papers in peer-reviewed international journals, 14 book chapters in books by published of international reputation, in one Indian patent, has an H index of 19 with around 1042 citation. Dr. Bhavya, you have an excellent track record. Thank you very much for being part of this forum. I'm sure your presentation will be very useful to all the audience. Let me share your screen to all. Can you turn on your webcam?
Yeah.
Okay, go ahead. Yeah, it's all yours now.
Thank you very much for the kind introduction, sir. I hope my screen is visible.
Yes, can you put on the presentation mode, please?
Yeah. Yeah. Thank you very much. Today, I will be talking about a different form of pyrolysis, which I shall introduce in some time. But thank you very much to the PYRO Asia Forum to provide me with an opportunity to present my works. I'm Dr. Bhavya B. Krishna. I work as a senior scientist and I head the Sustainability Impact Assessment area in the Material Resource Efficiency Division at the CSIR Indian Institute of Petroleum based in India. We are a group of 38 laboratories under the Council of Scientific and Industrial Research run by the Government of India. So with this introduction, I'll move into the topic. So the reason why I have chosen this topic is that ethanol is gaining importance as a renewable substitute for fuels. Like in the concluding session of the forum, Yoshioka Sensei had mentioned that renewable biofuels are gaining a lot of interest, and that's true. So as of now, all the majorly produced ethanol is derived from edible feedstocks, 1G ethanol around the world. But 2G ethanol, which is derived from lignocellulosic biomass, is slowly gathering momentum across the world. The reason that we are doing this work is that because the lignin, which is present in the lignocellulosic biomass, cannot be fermented by microorganisms, and hence it is produced in huge quantities as a byproduct of the ethanol manufacturing industries. And to make a biorefinery techno-economically viable and competitive, all these components have to be valorized in order to essentially and completely utilize the carbon content present in the lignocellulosic biomass. And second of all, the utilization near the process of generation is also extremely important. So in such a scenario, you have to develop decentralized processes which can be built up near the process of generation. Similarly to the 2G ethanol process, even the pulp and paper industry also produces huge amounts of lignin waste. Around 95% of this lignin is now burned for energy purpose, and hardly 5% commercially is now being used for any other material generation. So with this concluding statement that the lignin valorization is extremely essential to make the biorefinery economical, I will move into the work. What is the structure of lignin? So this lignin is made up of several monomeric units. But what is lignin? So where does lignin come from? So when you talk about lignocellulosic biomass, it is made up of three polymers such as cellulose, hemicellulose, and lignin. So the cellulose and the hemicellulose components, which together are also known as holocellulose, are taken away from the lignocellulosic biomass by a pretreatment technique, and then they are utilized for further fermentation to produce ethanol. This lignin, which acts as the binding material to have all these three polymers together, is now left behind. So this lignin has three monomeric units such as para-fumaryl alcohol, coniferyl alcohol, and synapyl alcohol. So when you still see the bonds that are present in the lignin, so you can see that the common linkages that are present in lignin are beta O4, beta beta, beta 5, alpha O4, and 5 bonds in lignin structure. So this bond that is available for breaking in the further process makes it the most important thing to be noticed. So an efficient pretreatment technique is essential to produce good quality lignin with bonds that can be easily broken during the next step of polymerization. So several pretreatment techniques have been studied worldwide for removing the holocellulose content and the lignin. Like you have the Kraft process, there's a hydrothermal process, there's steam explosion, ammonia fiber expansion, ammonia recycle percolation, and so on and so forth, even including the microwave pretreatment. There are so many methods that are now being studied, but each of these methods produces different kinds of lignin with different bonds that are accessible during the next steps. Similarly, when you take a particular kind of a pretreatment as well, and you change the feedstock, the effective lignin that is obtained due to the inherent characteristic of the feedstock also ends up making the structure of lignin different. So we need a sort of a optimized pretreatment technique which will produce some good quality lignin. So today I'm going to talk about hydrothermal liquefaction, which is also a kind of a pyrolysis. So in hydrothermal liquefaction, what happens is biomass is subjected to elevated temperatures and pressures in order to break down and reform the chemical building blocks into a crude oil, into a biocrude oil. So at these temperatures and pressures, the solvent which is used in the process becomes a highly reactive system and promotes the breakdown and cleavage of the chemical bonds that are present in the feedstock and allows the reformation of these biological macromolecules. So this conversion sort of mimics the natural geological processes that have happened over the past millions of years in our has led to the production of our current fossil fuel reserves and also allows for a wide range of feedstocks to be tested. So in certain cases, this process is better than pyrolysis because it eliminates the drying of the feedstock that is to be processed further, and hence it helps in saving the resource and energy intensive pre-processing steps. So this ability to cut.
Dr. Bhavya, this presentation is actually oral present 10 minutes only. You got only 4 more minutes. Okay. Yeah.
Yes, sir. So there are several other positives for this particular process. So I will move further into my results. So in this hydrothermal liquefaction, we have tested several feedstocks so far, and in this particular work, I will be talking about lignin, which has been derived from rice straw by aqueous alkali pretreatment. So we have loaded the feed into the reactor and optimized the other reaction conditions, which I shall be mentioning in the further slides. So for the first parameter, we have tried to optimize the temperature. So we have tried the experiments in a wide range of temperature, like starting from 120 to 200 degrees centigrade, and we have observed maximum bio-oil yield at 160 degrees centigrade. So the next step was to optimize the residence time, and we have studied the residence time ranging from 15, 30 and 60 and 120 minutes, and observed that the maximum bio-oil yield was obtained at 60 minutes. So the next was to understand the effect of solvent, and we have studied the experiments in using two different solvents such as ethanol and methanol. The bio-oil yield was better in methanol case than in ethanol case, and hence the optimum solvent to produce the maximum bio-oil yield is methanol. So the next was to understand the effect of catalyst in the nitrogen atmosphere. So we used a basic catalyst and an acidic catalyst and varied the ratios in which the catalysts were mixed while carrying out the experiments, and found that pure ZSM5 without the presence of MgO produced maximum bio-oil under both the atmospheres. And the bio-oil yield was better in the oxygen atmosphere than in the nitrogen atmosphere. So taking this cue, what we did next was to carry out the lignin oxidative depolymerization. So we used the H2O2, which is the hydrogen peroxide, as a oxidant. And in another case, we also used hydrogen peroxide along with ZSM5 catalyst, which was found to be better with the other reaction experiments that were carried out earlier. And we observed that the maximum bio-oil yield was obtained using ZSM5 and 1 ml H2O2, but this was under nitrogen atmosphere. Since we are using H2O2, it's not required to have an oxygen atmosphere there. So we carried out the experiment in nitrogen atmosphere, but used H2O2 as an oxidant and ZSM5 catalyst. So this was found to be the most optimum condition for this particular lignin degradation. So to give you an explanation of the products that were present in the bio-oil, we carried out the GC mass of the bio-oil that was obtained. So under the thermal reaction conditions, where we found 1 hour to be the most optimum residence time, we saw that there was a selectivity in the area percentage of 2-methoxy-4-vinyl phenol was around 66%. And similarly, when we used the ZSM5 catalyst, so in the nitrogen atmosphere, a similar amount of 2-methoxy-4-vinyl phenol was obtained, but the reaction in this case, in the second case, the bio-oil yield was reduced, though the catalyst selectivity remained the same. So when I talk about the GC mass of the bio that was obtained through oxidative depolymerization, you can see that similar amount of 2-methoxy-4-vinyl phenol was present, but the changing factor here is that when we used 1 ml H2O2 and ZSM5 catalyst, we observed a totally new different kind of a compound with a maximum area percentage, which shows that there's an increase in selectivity. So the concluding statement here is that the differences in the product portfolio clearly indicate that the reaction conditions that we use in a particular experiment affects the lignin breaking mechanism, and hence more studies are required to understand the reason as to why this is happening and how the pretreatment conditions are exposing the bonds that are present in the lignin for the further step of depolymerization. So to conclude my presentation, I would like to say that lignin is the most underused polymer in the lignocellulosic biomass matrix, and hence we have to develop more processes to make it to utilize the complex aromatic structure and produce high value chemicals from the same. The pretreatment technique followed in the present study that was used to get the lignin was found to be a good pretreatment method to retain the important bonds after separation from homocellulose. The reaction conditions are seen to play an important role in the lignin degradation mechanism. 2-methoxy-4-vinyl phenol, which is an important compound in the flavoring industry, was found to be present with maximum area percentage and selectivity. So effective separation processes need to be designed further to utilize these product streams and separate the components. And solid biochar that is obtained in the process can be targeted for high value applications due to the nature of the carbon thus obtained, and this work is under progress. Thank you so much for the opportunity. Thank you.
Thank you, Bhavya. Very good presentation. Okay, as this oral presentation is 10 minutes, I know it's very short time. I know you had to manage your time, but if we have extra time at the end of the session, I will let you all the oral presenters to make additional comments or share your experience. Okay, so please don't mind that I'm rushing you guys, but I know that 10 minutes is the time they give. Yeah. Okay. Thank you.
Thank you.
Well, let me take over the screen. Okay, guys, if you have any questions on each presentation, please post questions in the question box with attention to the speaker name so that we address these questions at the end of the session today. Okay, let's go to the next presentation. Okay, the next oral presentation is focusing on the microwave-induced pyrolysis of horse manure for waste valorization and management, production optimization, and life cycle assessment by Dr. Cheng Tung Chong. Let me brief about him. Okay, he is an associate professor at the China UK Low Carbon College at Shanghai Jiao Tong University. He holds a bachelor degree in aeronautical engineering from University Technology Malaysia and a PhD degree in the field of energy from the University of Cambridge, UK. He has participated as a PI the principal investigator in 20 research industrial projects that are related to the clean energy utilization, waste to energy, and pollution reduction. His research interests include clean energy technology, biofuel production, combustion, and thermochemical conversion process. He has published more than 110 technical papers. He was awarded the prestigious Newton Advanced Fellowship from the Royal Society and was recognized as an outstanding ASEAN science diplomat. Dr. Chong is a registered chartered engineer under UK Engineering Council and a professional engineer under the Board of Engineers Malaysia. He is the winner of a science communication competition organized by the PYRO ASIA, China. He now heads the Clean Energy and Combustion Laboratory at the China UK Low Carbon College. Dr. Chong, you have excellent great, I can say track record and experience. I'm sure this presentation is useful to all the participants today. Let me share the screen to you. Okay. Oh. Okay, do you get it?
Yep. Can you see my screen?
Super. Yes.
Thank you. Thank you very much, Baram, for the kind introductions. Can you guys hear me?
Yes, I can hear you.
See my screen?
Yes,
okay.
all good. Yeah.
Okay, so let's go. So very good evening, good morning to all the participants of PYRO Asia. First of all, I would like to thank the organizer for giving me this opportunity to present this talk. So my talk today is about microwave-induced pyrolysis of horse manure. So we have heard a lot about lignocellulose biomass for pyrolysis, but we haven't heard much about manure pyrolysis yet. So today we're going to talk about manure pyrolysis and also the LCA aspect of this. So just now, Param has done a very kind introductions about myself. My research area is mainly focusing on the clean energy technology, biofuel productions, combustions, and also thermochemical conversion methods. A bit about my institution. I'm from Shanghai Jiao Tong University. It has a long history and it is one of the oldest and top research universities in China. So traditionally, we have been very strong in power and engineering and also environmental science. To be more specific, I'm from China UK Low Carbon College. This campus, this college is newly established. It is only 3 years old. It is located at Lingang, Shanghai. And this college is a bit unique because it is jointly set up by University of Edinburgh and Shanghai Jiao Tong University. Now, this college is located in Lingang. It is a special free trade zone area in Shanghai, very accessible to the Pudong International Airport. And we have a team of pyrolysis academics who are working in the area of pyrolysis. So you guys are most welcome to visit our college someday. Now, let's get back to animal manure. Why do we do manure in the first place? Manure is the second largest biowaste after lignocellulose biomass. So globally, there are about 26.2 billion tons of animal manure produced. That is far more than what human has produced. But traditionally, manures have been used as fertilizers or through biological conversion to produce biogas. So we can see on the right-hand side, there is this AD method, anaerobic digestion, to produce biogas, and it is considered to be quite mature for this kind of technology. Or another biological method is through composting to produce fertilizers. So manure have been recognized to be treated through the biological method. So there is not much work has been done through thermochemical conversion process. And this is what our thing, this is our line of thought. Why not we pyrolyze manure and see what we get? Whether or not we can valorize animal manure and at the same time treat the manure so that we can manage them effectively to avoid environmental pollution. We have done some search. We found that there are a lot of countries or a lot of places that are spending a lot of money just to treat this manure. For example, in North America, they can pay up to $50 million per month just to get rid of horse manure. Now, here are some fun facts. Globally, the population of horse is about 58 million. Now, that is far lesser compared to 1,000 million of cattle. And every day, each of these horses, they can produce up to 17 kilograms of manure. While cattle is even more, 40 kilograms per cattle. And within this manure, about 75% of them are dry matter. That means get rid of the moisture, 75% are dry masses. So there's a lot of this manure lying around that can be reused and recycled to produce some useful product. And pyrolysis is one good way to do so. So here's our methodology. We select horse manure as our target feedstock. First, we're going to determine their pyrolysis characteristics and kinetic parameters using TGA method. Secondly, we are going to use microwave-induced pyrolysis method to produce the famous 3 end products, which is biochar, liquid, bioliquid, and also biogas. And we're going to characterize them. After that, we are going to derive, we are going to try to optimize the production process to get the optimum operating conditions using the design of experimental method. Lastly, we're going to conduct an LCA method to evaluate the overall impact of this feedstock and the process on the energy and also environmental impacts. So we have done this work. We have published them systematically in 3 journal papers. You are free to check it out. Let's move on to our microwave-induced pyrolysis method. So we have heard, like from Professor Lam, how microwave pyrolysis works, the advantage of them. Is quite similar. We are using a very simple domestic microwave to produce the electromagnetic wave to induce the pyrolysis process. So first, we collect the horse manure from UTM, horse stable, and then we are going to mix it with activated carbon. Now, the function of the activated carbon is more towards absorbing the microwave so that the temperature of the pyrolysis can be elevated. Now, here's a graph to show that without the activated carbon, the temperature can only be up to 200 to 300 degrees Celsius. But with the activated carbon, the temperature can be elevated up until 500 degrees Celsius. Then we characterize our feedstock. So carbon content wise is about 40%. Volatile matter is about 70% for the horse manure, and compared with the paper published by Nanda in 2016, they are quite comparable. The heating value of the solid bio waste of horse manure is about 70 megajoule per kilogram. And if we look closer inside the composition, it consists a lot of lignin, about 56%, hemicellulose, about 24%. Now this is understandable because they are herbivores, they eat grass. And trace element wise, potassium is quite significant inside the manure. Then we pyrolyze it for about 45 minutes per run. Let's characterize the end product. For the biochar, we can get a quite large surface. It's about 700 meters square per gram. Then the energy density wise, we found that there is an increase from 17 megajoule up until 22 to 35. So this is the biochar. And for the biogas, we found that there are a lot of CO produced. If we combine CO and H2, which is the syngas, we can get up to 73% per volume. And the heating value range from 12 to 15 megajoule per meter cube. Then for the bioliquid, we found that we can get a lot of phenolic compounds from the pyrolysis across a range of temperature. But of course, there are other compounds such as pyridine, ketones, carboxylic acids. Overall, it has high oxygen content, mostly oxygenated compounds, and the heating value is not great. It is somewhere between 6 to 15.76 megajoule per kilogram. But interestingly, phenolic compounds constitute the largest compositions in this bioliquid. So we also did the energy balance analysis. We found that if we combine all this energy content of each of these products and compare with the original horse manure, there is an energy deficit by about 5 to 10%. This is understandable because they are mixed with water, there are some coke losses, etc. So that reduced in the energy reduction in the energy profit. And for the product yield, depends on the operating conditions, we can get a range of value depending on your target. For example, if we target liquid, we can increase the activated carbon to horse manure ratio. We can reduce our nitrogen gas flow rate. We can increase our pyrolysis temperature. Then we can increase the production of the bioliquid and also biogas. So we conducted the analysis of variance, and we found that the optimum parameters for the production of bioliquid and bio-oil should be high temperature, pyrolysis temperature, high activated carbon to horse manure ratio. And this is one of the papers that we have published that elaborates all these results. Then the second portion of the talk is about the life cycle assessment. We conducted the LCA analysis based on the optimum parameters or optimum conditions to produce the optimum biogas and also bioliquid. So we, for the boundary conditions, we include the transportation, drying process, grinding, storage until pyrolysis, and also quenching. What we found that transportation has a significant impact on the environment. If we can reduce this, then we can reduce the impact of this. Yeah, global warming potential because it's a heat is a pyrolysis process, so it can incur quite a significant portion for the global warming potential. That is the CO2 emissions. So interestingly, we compare our analysis with the swine manure pyrolysis plant in Belgium. which is using roughly the same operating conditions. We found that microwave-induced heating can produce lesser CO2 emissions by a factor of 2.5. So other impact categories like acidifications, human toxicity are also significantly lesser compared to the swine manure pyrolysis plant. And this swine manure pyrolysis plant is using the conventional pyrolysis method. So this shows that the microwave pyrolysis method has the advantage. And also we compare against other manure management method, although the energy consumption is much higher, but the global and also the global warming potential is also quite high compared to AD and also incineration, but acidification and eutrophication potential are much lesser.
Dr. Chung, can you conclude?
So,
okay.
yeah. In conclusion, we shows that horse manure has very good properties to be valorized into valuable products through microwave-induced pyrolysis, and we can produce the three products, which is bioliquid, biogas, and also biochar. And LCA method shows that the pyrolysis plant for horse manure is feasible and has lesser environmental impact. So I would like to thank my team members, especially my PhD student, Goran, Dr. Mong, Johan William, and also Professor Lam from UNT, Professor Farid Nasiani, also from UTM for the guidance and also the support. So you guys are welcome to China UK Low Carbon College someday. Thank you very much.
Thank you, Dr. Chang. Guys, I'm sure that you find this presentation useful. If you have any questions, please post question in the question box. Attention to Dr. Chang. Thank you, Dr. Chang. Let me take over screen.
Thank you.
Okay. Okay, the next presentation. Presentation is on the production of pyro products from empty oil fruit bunch using azotic and R-yield reactor of Aspen Plus. The presentation will be given by Dr. Saurav Podar. I request Dr. Saurav to briefly introduce yourself, as I didn't have your profile. If you don't mind, let me give this screen to you. Okay, yeah. Okay, open the PowerPoint, please. Please open your on the speaker. You are unmuted. Please unmute it.
It's unmuted?
Yes, now it's okay. Yes. Are you going to on your video webcam?
Is it
okay?
visible?
Now, yes. Okay. Good. Okay. Good to go. Yes.
Yeah. Good afternoon, everybody. I'm Dr. Saurav Podar. I have completed my PhD from Jadavpur University. After that, I have done my chartered engineering and then professional engineering from Engineers of Institute. Then after that, I'm just worked for 1.5 hours in a private college in Calcutta. Right now, I'm working as a postdoc fellow at National Institute of Technology, Tiruchirappalli, Tamil Nadu. So right now, I'm just going to present the topic that is my present. My PowerPoint is visible to everybody, is it? Hello?
Yes, it is visible.
Hello?
Go on. Yeah, it is working. Yeah, go on.
Yeah. So my topic is production of empty, that is your pyro products from empty oil palm fruit branch using azotic reactors and R-yield reactors of Aspen Plus. So I and my guide, that is Professor J. Sarachandra Babu, was working on it, and right now I'm just presenting the whole thing. So the need for Aspen Plus is very much needed, because in today we are just having lab scale pyrolysis being developed. Everybody is talking about lab scale pyrolysis, then optimization of the pyrolysis, then life cycle of the pyrolysis. So now my point is the techno-economic aspects of the pyrolysis, how it is going to happen. So the first slide I will just try to share. That is the content that I have just presented, or just I'm going to show you in my presentation. That is the need for this research. Now the pyrolysis conditions that has been used. Next one is the computer-aided stimulator results, conclusions, and then thanking you or any suggestions that might be helpful for me in the near future. So right now, what I have just observed that various persons are working on the lab scale pyrolysis. So with that, I just tried to work out with the whole thing. So I just, I meant to say I'm also very thankful to Dr. R. Vinu of IIT Madras, because I've just observed one of his article and I observed that it is an interesting topic to work on. So that was the MT oil palm bunches. So where it was just defined that the palm oil industry is growing in Indonesia and the production rate is around 75 million tons, and then which is accounting to, you can say, more than 75%, and India is one of the largest consumer for this one. So upon considering this facts, what we I and my guide just tried to model it down. So it is totally a modeling aspect. So we tried to model a pyrolyzer which will be workable for a small city, even it can work for a large city like metropolitan cities like Calcutta, Delhi, Chennai, Madras. So we just considered the factors that was published by Dr. R. Vinu's paper. So this is the feedstock condition, and this feedstock condition were in two ways. One was your treated, the next one is the untreated. So with this feedstock conditions, we just tried to develop a model in the pyrolyzer with various reactors that are present in the Aspen Plus. So two models have been utilized in this, and this is the whole thing, that is your ultimate analysis of the pyro products that has been shown in this slide. One is your untreated, the other one is treated. The treatment is being done, or we have considered the treatment to be using water wash. That was the whole thing that we have done it. So this is the whole Aspen modeling diagram or the schematic representation you can take. So biomass, initially we considered that it contains some kind of moisture. So if that moisture is present in that, then we will just mix it with nitrogen, and then we will just went for the drying condition. And the temperature in the dryer we just considered, or it generally happens to be around 110 degrees centigrade, and the pressure we kept around 1 bar. Then we just placed it into the reactor, that is the pyrolyzer. In pyrolyzer we varied the temperature from 400 to 700 degrees centigrade. We have used two reactors. One is the R-stoic reactor, the other one is R-yield reactor. Now I will just try to make a focus on R-stoic reactor and R-yield reactor. R-stoic reactor is basically a stoichiometry reactor. That means we have to provide only the stoichiometry and the conversion rate. So that means we are not focusing on how much amount it is forming. It will just generate us with the product that we are going to have. Now in the R-yield reactor, if we are just having any absence of any kind of a stoichiometry, we can just provide the yield of the products, and that with the help of the yield we can just generate the whole output of it. So with that we just developed the model that can run for the lab scale. The lab scale model that was done by Dr. Vinu, that was 4 gram sample was taken, and with the 4 gram sample we just ran it in the Aspen Plus. So in the Aspen Plus given us the result that was treated and untreated. It was observed the same similar results, and in case of R-stoic was the more prominent one than the R-yield, because the stoichiometry or the chemical equation was very well defined in the R-stoic reactor. And it was observed that the production of this pyrochar decreases, then the production of pyro oil generally increases, whereas this char was decreasing. Now, in case of gases, the production was increasing with that of this whole thing. So then we just tried to model this whole, this whole process to a 1.5 tons per day sample. And after doing that 1.5 tons per day sample, we just tried to do the economic aspects. So the economic aspects, after calculating, we are just going to present the net present value. So the net present value was something around, say, 8,000 here, something like that. So, and if it goes on like this way, if we just keep on varying with respect to the discount rate, or I mean to say, if we keep on change for every year, the discount, keeping the discount rate constant, the discount rate over here we observe to be 10%, and we observe that at 6.2 the discount rate, this thing was crossing the y-axis, so we can call it to be that this point to be the internal return rate for this thing. The discount rate we considered for 1.5 tons was 10% discount rate. So before going into that, I will just try to show 2 or 3 techno-economic aspects. The total economic aspects we have considered, this was the total economic cost that we have considered. Then the total economic cost plus your auxiliary equipment cost then came down into play, then total fixed cost. Then total fixed cost is the summation of this total direct cost and total indirect cost that we have taken down. And then along with this, we have to consider the working capital, and then considering the working capital, we just calculated the total fixed capital investment. After calculating the total fixed capital investment, we have to gone for the calculation of the total manufacturing cost. And we just got the total manufacturing cost, and with the help of this manufacturing cost, we just have gone for the net present value, and the net present value we just calculated the discount rate, and the payback period we just said to be 2.5 years with a discount rate of 10%, which the diagram which we haven't shown. So now in the conclusion, I would like to say that our stoic reactor will be one of the best reactor rather than our yield reactor, because our stoic reactor is basically built on the stoichiometry rather than the yield percentage of this whole thing. And then with respect to the temperature change, we can say that the char was decreasing from 24% to 21% in case of your untreated and your treated ones. And in case of oil, the percentage was increasing up to say 600 degrees centigrade. Then after that, it starts decreasing. So I just showed increasing one, that was your 26% to 36%. And in case of gases, it increases from 40 to 45%. And the net present value was calculated out, and it was shown to be, that is 86808.9. With that, if we keep the discount rate of 10%, then we're going to get a internal return rate of 6.2%, and the payback period will be 2.5 years if we have this 10% discount rate. That's all we can have to say, that if we just go on investing with this kind of a model that we have defined initially, that was shown in over here. So we can say that with a discount rate of 10%, the payback period for a pyrolyzer will be 2.5 years. That's all I have to say. That's it. Thank you.
Okay, thank you, Dr. Saro. Interesting presentation. Yeah. Thank you very much. And let me take over the screen. Guys, if you have any questions to Dr. Saro, please post your questions in the question box, and he will address them at the end of the session. Thank you. Okay, the next presentation is on the gainful reclamation of e-waste using a catalytic reactor by Mr. Ulash Krishnan. let me welcome Mr. Krishnan. I don't have his profile. I request him to brief him about his introduce himself. Ulash, here we go. Okay. Okay, please share your screen.
Yeah, is it true?
Yeah, okay. Yes, that's fine. Okay.
Hello?
Go on. Yeah. Okay, go on. Yeah.
Yeah. Myself, Ullas Krishnan Jain. I'm doing PhD in NIT, National Institute of Technology, Tiruchirappalli, under the guide Dr. J. Sharad Chandra Babu. I completed my BTech in 2008. Then I was into MTech till 2011. After that, I started my career as a guest lecturer. Then as assistant professor, I was working for 5 years. And then later, I joined NIT 4 years back for my PhD. So that's a brief introduction about myself. Currently, I'm working on catalytic reactors and producing a nanocatalyst for catalytic reactions. So coming to my presentation, today I'm here to give my oral presentation on gainful reclamation of e-waste using a catalytic reactor. So it's a joint project between my institute, National Institute of Technology, and Bharat Heavy Electrical Limited's Tiruchirappalli. So now, as we all know, like e-waste has become a major concern throughout the world because of the sheer amount of waste generated and also with the lack of recycling. So there are reports showing that like a record of 53.6 million tons of e-waste was produced globally in 2019. And also, e-waste is not only electronic waste; it comprises of electrical components. Any waste which is having a a plug or electric cord or battery, it is all coming under e-waste category. So it may only represent 2% of the solid waste, but at the same time, it has 70% of hazardous waste that ends up into landfills if it is not properly treated. So India is coming to Indian scenario. India is actually coming as the 177th amongst 180 countries on environmental environmental performance index released by World Economic Forum 2018. And also it is ranked as the 5th country in producing e-waste after USA, China, Japan, Germany. India comes as the 5th country. But when you think about the recycling part, only 2% of the e-waste is being recycled annually, and in fact, 2 million tons of e-waste is there, and even importing of e-waste from the other country is entertained by India. So now industry as well as academia has addressed this issue, and now many collaborative work between industry and research institutes are turning up. So as a part of that, we were also into this e-waste management project. And other attractive part of this e-waste thing is, other than if you don't dump and discard the landfill, do that, and if you try to take the metal parts of the e-waste, it comes up to $57 billion of gold and other important components can be reclaimed. So the objective of my this particular presentation is to showcase our suitable catalyst we have generated for cleavage of carbon-carbon bond, resulting in degradation of e-waste, and intensifying the process condition, like finding the optimum temperature, flow rates, and other conditions, so that we get more of liquid products and test in our lab demo setup. So this is our reactor with downstream points. So here we used to load our e-waste through this, and the catalyst is preloaded into the system, and the air is supplied to the bottom, and the liquid will, the gases will flow out of this and go for the condensation. So it's maintained at around 450 degrees. And our catalyst is a multi-metal catalyst which is having less than 1 micron, and we have analyzed those things in FESAM, XRD, and other characterization is done. So when the liquid comes up, we have analyzed that with NMR analysis. In that, we are getting very promising results of all the hydrocarbons and all the hydrogen and carbon content of the NMR liquid, an analysis is very promising. And we have analyzed our this thing with FTIR analysis. When you compare with the common diesel that is available in the petrol outlets, we have analyzed with our liquid product, and we are getting really a matching peaks and other things. So our liquid is actually having more of a diesel quality rather than petroleum. Petrol is also coming in line. And also the GC analysis of the liquid, all the peaks we are matching with the diesel our sample. So all the major peaks are matching. So our liquid is actually very promising. And then we did the liquid collected. We have used for this true boiling point distillation, and it has come out with components like methane, ethane, propane, isobutane, N-butane, isopentane, and N-pentane and benzene. So this is a cumulative weight percentage of all the components available. And just a second. Am I audible? Hello?
You are audible, yes.
Hello?
Yes, you are audible. Okay. Yeah, go
on. Okay. Now, to conclude our work is we have developed a multi-metal catalyst which is able to cleavage carbon dioxide like a carbon-carbon bond and come out with reduction of e-waste. And the liquid product achieved is of vary from 60 to 70% of weight, and it depends upon the metal component that is present. And the fuel quality of the condensate is very promising to that of a diesel. And metal retained in the bottom is of a high value, and that can be reclaimed by using the hydrometallurgy method. So that is our second part of our ongoing project, to come out with the metal that is been in the bottom of the reactor. And I would like to thank my guide, Dr. J. Sarachandra Babu, and the BHEL team to give us such a work. And I don't know whether this video will be properly played. Yeah, this is like the gas flow is given, and now it goes to the reactor, and the whole gas will go through the condensate, and the condensing liquid will be collected. And the secondary, the gases are again condensate, so that no other things are going out to the maximum condensation standard. So that's all. Thank you from my side.
Okay, thank you, Ulash. Appreciate the presentation. Guys, if you have any questions to Mr. Ulash, please post in the question box. Okay, and we address them at in the quick Q&A session immediately right now. Okay, that's all for the oral presentation. Now I invite our session chairman, which in the beginning I was unable to introduce him properly, Dr. Arshad Salema. Okay, let me take over my screen first. Okay. And Dr. Arshad, you'd like to say a few words to the audience? Can you unmute your speaker, please?
Yeah. Thank you very much, Piram. And I apologize all of you in my session. Internet was working very nicely until the break. And once I went for my lunch, after that, I don't know what happened. It totally break down. So I apologize to all of you for this inconvenience, and so I cannot say you any welcome note, but I came back for the at the end of the session to say you bye. So still we have some Q&A. So yeah, that's all from my side, Piram.
Okay, thanks, Dr. Arshad. Okay, let me put the questions. Okay.
Yeah, so we will start Q&A now, Pera?
Yes, that's right. Yeah, just a second. Yeah.
Perfect. Perfect.
Okay. I got the question.
So how much time is scheduled for Q&A?
We got 20 minutes left, okay, before we take a break. Okay, so we got 20 minutes to finish all these questions. Yeah. Okay, let me put on the slideshow.
Okay, so in short, I would like to welcome all of you. I would like to welcome all of you to this PYRO Asia. Dr. Ondrej, Prof. Zunhu, Dr. Bhavia, Dr. Saurav, Associate Professor Cheng Tung Chong, and Mr. Ullas Krishnan. Welcome to all of you. Thank you.
Okay, the first question is Dr. Ondrej, are you there?
Yes, I'm here.
Okay, you hit the question. Yeah, please.
Yes. Okay. So, do you want me to read the questions and then answer them, or
you rephrase the question? You understand the question? You rephrase the question, answer it.
Okay. Okay. Right. So the first one. Okay. So it's about selective adsorption or use of biochar for selective adsorption. And so, what's my opinion on that? Well, it very much depends on the nature of the biochar. Here, the question is related to biochar that contains a lot of metals on the surfaces. So it really depends on how the biochar has been produced, how it's designed, if it's activated in any way, whether in terms of surface area or functionalities on the surfaces. So there are a number of studies that have shown that the biochar can be optimized for removal of different compounds, whether it's heavy metals, it can be organic compounds. So I'm afraid it's a rather general answer to the question. I'm not sure what specifically the person asking the question wanted to focus on. The next one, after biogas filtration, the char used is used for soil. How about the gas pollutants absorbed in biochar? Okay, so this, I suppose, refers to the use that I showed in the slides where we remove siloxane using biochar. I think the question seems to be about other pollutants that may be present in the gas. That could be hydrogen sulfide and so on. Again, depends on what contamination there is present. If it's sulfur, then that's not necessarily a problem. It will be sulfur-enriched biochar that will be produced. So again, I'm afraid I can't be too specific without knowing the exact details of the question. If this is related to use of biochar in AD process itself, then the biochar actually leaves the process together with the solid digestate. So again, depending if there is a contamination with heavy metals or so, it's quite possible that the biochar would be would hold on to some of those, but it would be in the digestate in any case. So the biochar is more likely to actually stabilize these. So I hope that answers the question partially. Okay, what is the engineer, non-engineer for biochar? What is the different requirement? So I tried to show that on the simple schematic. So engineered biochar is a biochar that has been specifically selected or optimized in the production process for a given application. So let's say if we want to use a biochar for improving water retention in soil, we will want to have a biochar that has a good, that's a hydrophilic. We'll want to have a biochar that has a high surface area and high pore volumes, and so on. If we want a biochar for some electrochemical applications, we might want to have a high electric conductivity and so on. So the engineered biochar is a biochar that's optimized for a given application, rather than just taking any biochar and use it for any application. Okay. So I hope that answered those questions.
Yeah. Thank you, Dr. Ondrej. Okay, Professor Hu.
Oh, yes. So the question is, do you have any characterization for the char you get from the bioagent? It's similar with the coke during the catalytic pyrolysis process. We did some initial characterization of the actually we did not call it a char, we call it a carbon material or carbonaceous materials because it has different properties to the biochar from the pyrolysis. For the biochar, we produce it from polymerization of bio oil and PYRO. Sometimes you can also add the biochar from the pyrolysis, or just without the biochar from the pyrolysis. So it's different from the biochar from the pyrolysis. The main feature of the carbon material is that it has a higher oxygen content than the biochar from the pyrolysis, because we polymerized the bio oil and we reserve the majority of the organics, especially the oxygen containing organics in the solid product, the carbon materials. So it definitely has a much higher oxygen content than the biochar from the pyrolysis. The special thing is that if you just do the polymerization of the bio oil with the PYRO, you will get the carbon materials. We can see almost free of the metals, because bio oil contains some metals, but the amount is much lower than the biochar from the pyrolysis. So yeah, that's a difference. I mean, for what's the effect, the difference on the applications? I mean, we're still exploring this aspect, because we just did the experiments about this technical road. Okay.
Okay.
I hope I made it clear for you. Okay, thanks.
Thank you, Professor Hu. Thank you. Okay, next, Dr. Bhavya.
I would like to answer the second question first, so that I can get back to the first question. So the second question says, are you getting more oxygenated compounds such as phenols and ketone, and are those the targeted products? I mean, so yes, of course. The phenols and ketones are the compounds that will be majorly formed, because lignin as such is a polyaromatic complex polymer. So obviously when it's broken down, you will only get phenolic and ketone type compounds. And of course they are the targeted compounds, because they end up acting as several high value functional compounds rather than these straight chain hydrocarbons. So generally these chemicals are now made from fossil-based resources after several steps of functionalization. Like for example, a small phenolic compound also starts the cumene process, and then you make phenol, and then you end up functionalizing it. But when you take biomass as a feedstock or lignin as a feedstock, you end up making these products in a far more easier way and in a far more environmentally sustainable manner. So of course they are the targeted products. He's also asked, somebody's asked regarding the 4 to 5 compounds. So even we have done studies initially where when you used biomass, we used to get around 40-45 compounds. And then when you just consider just the lignin part, we've also had experiments where we got 20-25 compounds as well. And then slowly, as and when you optimize the parameters, what happens is there's selective breaking occurring. And then you end up reducing the number of compounds that are coming in the bio oil. So this has to be seen as the differences in the reaction mechanism, and hence that is the reason why we have been able to see only lower number of compounds. So I hope I've answered both the questions. Thank you.
Okay. Thank you, Bhavya. Okay, this is for Mr. Ullas.
Yeah. Actually, the FTIR is shown for different materials, but when we got the characteristics of the liquid, it was showing similar properties of the diesel. So we want to cross-check whether it is like very similar to that of diesel. So when we checked it, it was finding all the peaks and major things are coming in line with that. So that's why we didn't go for GCMS. We went for only for GC. So in the GC also, the similar peaks between this diesel as well as our fluid is coming. So that's why we were able to conclude that the e-waste crude can be as a feedstock for even producing diesel and other petrochemical products out of that. So that was the major idea. Like when we compare the commercial diesel along with our liquid, is just to get a feel of our liquid. Thank you.
Thank you, Ullas. Let me put some more questions. Please hang on. Please bear with me. I'm trying to, putting together. I guess are there. Okay, Dr. Ondrej.
Okay, so the question, as I understand it, is asking how do we ensure the pharmaceuticals taken up by the biochar are not then released again when we use it in a subsequent application. So it's a good question, and this is why we had the recycling step there. So there's the hydrothermal treatment that decomposes the pharmaceuticals. I know I had to go through the slides fairly quickly, but if you can go back to the slide that shows the hydrothermal treatment, there is a column graph that shows the nearly complete decomposition.
You want to share the screen?
I don't have this presentation on just now anymore.
Okay, fine.
Yeah, now that will take time to open it. So, but in any case, I can just say that these are decomposed during the hydrothermal step, and therefore the biochar that's then left at the end is clean and can be used either again in the same process or in a subsequent application.
Okay, thank you. Okay, Bhavya, next.
Yeah, when I meant that there were more compounds, I meant that it was initially when we didn't optimize our reactor conditions, and now as and when we've optimized our process conditions, the number of compounds have reduced to 2 and 3. So 2 or 5 in certain cases. So in that case, that's the reason why the area percentage shows as 90%. If at all there were more compounds, obviously the area percentage would have been different. But after a lot of optimizing the pre-treatment conditions and the hydrothermal liquefaction reaction parameters, we have reduced the compounds to 2 to 5 compounds. So that's the reason why such a high area percentage we've been able to observe.
Okay, thank you. Okay, Dr. Saurav. Dr. Saurav. Yeah. Okay, that's your last question.
Yeah, just a second, sir. Just hold on, just a second.
I repeat, I think they copied 2 times. There's only the one line on the top. Yeah.
Yeah, that's not an issue. The issue, I'm just searching one thing. Yeah, the question just said that it was about from 4 gram to 1 ton. Is it feasible setup? See, suppose a country like India, which produces more tons of, you can say that is more tons of waste. So with a country like India, so which is producing more tons of waste, so lab scale is going on 4 gram. So if we just can scale it up to a 1 ton, 2 ton, even 10 tons. So I don't think this large scale will just create any kind of a problem. So according to me, is I just done a you can say it's a kind of a some pilot plant feasibility has been studied. So if we just get a finding with more amount of money, we can just go ahead and we can just develop a higher scale setup. Industry kind of a setup can be set up, and it can be a part of a existing plant itself. So this is the whole thing is all about. We don't require any extra added land to set up. The land cost will be just getting reduced. So because what we generally do in case of techno-economic analysis, we take 6% of the total equipment cost in order to just or the total investment cost in order to calculate this whole thing. So we just can the setup be applied for other manure? Yeah, sure, it can be set up for other manure. That's a very good question. I will say that this model or this all this setup can be applied for all kinds of manure. But the thing is that we have to just set the process conditions. That is the main thing. Yeah.
Dr. Saurav, that question is for Dr. Chong, Associate Professor Chong.
Oh,
sorry.
Achha.
The last question, yeah.
Yeah, I thought it's mine. So my process can be applied for any kind of.
Okay.
But the thing, process condition has to be specified. That is the whole thing is all about. Thank you, everybody. I don't.
Thank you. Yeah. Okay, Dr. Chong.
Thank you, Dr. Saurav, for answering that question. It's good to know that, of course, your setup can be applied to other manures. And for my particular setup, for this microwave-induced pyrolysis, yes, it is in our plan to pyrolyze other manures, including swine manure and also poultry manure and also cattle manure. Given the different compositions in all these manures, perhaps we have to do some pre-treatment. For example, the cattle manure has really high content of moisture. So perhaps a pre-treatment of removing the moisture is needed down to a suitable level. But for microwave-induced pyrolysis, you don't have to completely remove the moisture. In fact, a certain level of moisture can help in the process, because just like cooking your food in the microwave oven, you have some moisture, it can be very efficient. So if we can just dry it to a manageable level, say let's say 10% of moisture, then your microwave pyrolysis can work. So we are planning to do that on other manures to create a database just to compare the end products. Yes, it is feasible, and also it is also feasible to scale up for this pyrolysis to treat this manure. Thank you.
Okay, thank you, Dr. Chung. Okay, that's all the questions I have for this session. Over to you, Dr. Arshad.
Yeah, thank you, Param. Thank you to all of the presentation. It was a very nice session, having a variety of different applied pyrolysis on different feedstock and products. It was really every presentation has its unique had a unique what we call as aspect, and that is very important for all of us to have this uniqueness, so that we can learn and have different types and varieties of this thing. So I would like to thank all the presenters for presenting such a nice and wonderful what we call as on different topics of this. Just I forgot to introduce myself. I am Arshad Salema from Monash University, Malaysia campus. Basically, I am also working on this biomass and pyrolysis, applied and analytical pyrolysis. And I have one or two questions. Is it okay, Param, to ask questions from my side?
Sure, sure. That's all your job, actually.
Or, no, maybe I thought the time is up now. I thought maybe.
Go on, yeah.
Okay, so I have questions to Dr. Ondrej. Dr. Ondrej, I think I saw your profile, and then you have done some real case study. I mean, you have developed some what we call as product from this biochar, or I mean, some gas or something in some developing countries. So can you just give us a very brief case study on?
Okay, good question. So you mean some actual sort of a production facility, or what do you mean regarding case study? So we've done a number of different projects. Yeah, actual product. Okay, so something that's on the market. Okay, so we are not sort of at that point. So well, so if you consider the spin-out company from my group, so Carbogenics, that is actual commercial product. That's at the moment not internationally sort of available yet. That's still in the UK. It's an emerging market for these products, and there is still a lot of development needed on that. But yeah, there are already first commercial sort of companies interested in that material and actually buying it. But at the moment, that's limited to UK. And that's as far as commercial products go, the only one so far from our research. The standard biochar I mentioned, that's not a commercial product, that's a research material that's provided to researchers globally, really usually just for the cost of postage and packaging. It's to promote research rather than to make commercial gains.
Perfect. Thank you very much, Dr. Ondrej. And hopefully, I think you can expand your actual product market outside UK. So
thank you.
Okay. Yeah. Next question to Prof. Zunho. Prof. Zunho, are you there?
Yes, I'm here. I'm online.
Prof. Zun, are you there? Yeah.
Oh, yes.
Yeah.
Yes.
Just a question to you about upgrading of bio oil. To what extent is your research at the level? I mean, is it already at the bench scale or pilot scale of this upgrading of bio oil?
I think it's a lab scale or it's bench. I think it's a pilot scale. Because I was working in Curtin from 2010 to 2016, and we developed the biotechnology about the use of the bio oil. We did a head treatment. First is the bench scale. We feed the bio oil at the flow rate. I remember that it's I think it's a few millimeter per hour. I think it's very slow at first, and at the end, I think it's at the end of 2016, we built up a setup. It's about 10 meters high, and the feeding rate of the bio oil is 20 liter per hour. Yeah, I think it's it's possible is close to the pilot scale. Yeah, in Curtin University.
Yeah.
Yeah.
Curtin University, you mean in Perth, Australia?
Yes. I worked there for 7 years. Yes.
Okay. I think I met that professor. I forgot his name, Professor.
Chenju or Hong Wei.
Yeah.
Okay. Yeah.
Okay. Thank you very much.
You're welcome. Okay.
So on other side, the question to Associate Professor Cheng. Okay. Professor Dr. Cheng, are you there?
Yeah, I'm here.
Yeah. So on just a question about this horse manure. Okay, if we compare pyrolysis with anaerobic digestion, so we are giving, like, if we do energy balance, let's say we do energy balance for pyrolysis and anaerobic digestion. So from your side, what would be the best option to do valorization?
Very good question. We have compared the microwave pyrolysis against anaerobic digestion from the point of view of energy balance. We found that pyrolysis is actually a more energy intensive process compared to the anaerobic digestions. AD process has the advantage of producing biogas, and it is quite a mature technology. But if we look at pyrolysis, it also has certain advantage. For example, the pyrolysis can produce bio oil or bioliquid, and also biochemical. Now, from this aspect, the thermochemical process is more advantage, even though it is more energy intensive. And on top of that, from other aspects such as the duration needed for the process. Now, thermochemical process like pyrolysis is fast, is quick, compared to AD process, which is longer, which may take days or weeks for the biological conversion to happen. So even though pyrolysis is energy intensive, but from other aspects, to produce higher value goods and also the duration for the process, it can be more advantageous. So it is kind of a balance. It is kind of an offset. And what we are proposing here is that manure can be treated in an alternative way through thermochemical conversion processes. Now back to the questions of energy balance. Definitely, pyrolysis is more energy intensive, but if we can use renewable energies like solar or wind to offset part of the energy used for the heating and also drying, that could partially solve the problem.
Perfect. Excellent. Thank you very much, Dr. Cheng. It's a very nice, interesting outcome to know about this process, so that we can select the best process. Yeah, good. So I think without further delay, I think we can, of course, we can always network each other. We know who we are, from which institutions. Always we can ask questions and network with each other, which is ultimate goal of this Asian or Asia Pyro 20, forum, basically, so that we all come together and then we can exchange share our things. So that was the ultimate goal. So thank you very much again to all of you for presenting your work, sharing your outcomes with the wider community in Asia and beyond. So thank you again to Dr. Ondrej, Prof. Zoon Ho, Dr. Bhavia, Dr. Saurav, Associate Professor Cheng Tung Chong, and Mr. Ullas Krishnan. So thank you again, and have a wonderful day. So that's all from my side. So I hand over to Param for this.
Okay, thank you, Dr. Harsha. Thank you all for this. It's a good session. Thank you all. Bye bye. Yeah, okay.
Thank you, Dr. Salema. Bye bye. Have a good day.
Bye bye, all of you.
Bye.
Have an excellent day. Thank you.
Okay, it's a time to take a break. Yeah, so we have 10 minutes break. Okay, we start in 10 minutes. The session number 5. Sorry, session number 6. Yeah.
Okay.
Okay, thank you all.
Session number 6. Okay, thank you.
Yeah, thank you. Session number 6.
Thank you, Param.
Yeah.
Bye.
Guys, anybody need help on the sharing the screen? I'd like to test it. Harshal, do you want to test your screen?
Param, this is Professor Mohanty. Can you hear me?
Yes, sir. Hi. Yes. Okay.
Yeah. So we are going to start the session 6, and as it is written in the program, initially there will be 5 short presentations.
That's right. Yes.
Correct.
That's right.
Then
yeah.
we'll have a. Will there be a break? No.
No, there is no break. Continuous. We have a Q&A session.
Continuously start the panel.
After presentations of short oral presentation, there will be a quick Q&A for those presenters. Okay, and then the panel discussion. Yeah.
Okay. Fine. So all these panelists have confirmed their presentation. Professor Zhang, Toshiaki, and Professor Bhaskar.
There is no present. It's more of a discussion on the points. Okay, only unfortunately the Professor Zhang is not going to be here. He has some conflict of schedule. Okay, so only you, Professor Toshiaki, Professor Yoshiaka, okay, and Professor Bhaskar. Yeah.
Okay, so three of us.
Three of us. Yeah. Is Bhaskar on the line?
And Mohanty?
Okay.
Yes. How are you?
Yeah, you discussed for the panel discussion now. Okay, and if you have a chance to the presentation for me, and I like to the few minutes presentation for the give us some discussion point.
Correct.
It's available.
Yeah. We can do that.
Yeah.
Yes. So I can share the screen to you.
Just a few minutes, maybe a few slides.
Sure.
Yeah.
You just
five or 6 slide usage for my presentation.
The Professor Mohanty, you can instruct me when you want him, when I had to share the screen to him, so I will share the screen. Yeah. Okay. So.
Yeah.
Sure.
Okay. Harsha, you want to give a try? Check with your screen, Harsha.
Okay.
Harsha, let me. I ask you to share your screen, please. Yeah. So. Okay. Yep. Did you see the message? Click OK. You need to unmute your speaker, please. Okay, yeah, you done that. Unmute your speaker. Okay, unmute your speaker. Speak out. Okay, can you open the PowerPoint, please? Okay, all good. But I don't hear your voice. Are you speaking something? I can't hear you. Say something so that I know that you can hear me. I can hear you. Harshal, I can't hear you. You need to speak out. I can't hear you. Your speaker is on, but looks like the connections are, whether mic or speaker connections are not correct. I can't hear you, man. I can't hear you. Can you log off and log in again, please? Log off and log in again. Yep. Hi, Roger. Are you able to hear me, Roger?
I'm able to hear you. Yes.
Okay. I think did we try this sharing the screen before? Not yet, right?
Not today. Yeah, I was just wondering exactly where the sharing is.
Okay, I'm going to click it. I mean, I'm going to give a request for it, and you can accept it. It just yeah. Okay. Can you did you open any your PowerPoint file?
Yes.
Okay. Let me try. Yeah. Okay. I'll give you the kind of
show my screen.
Yeah. Okay. Super.
Yeah. There we go.
Okay. All good. Okay. So when I invite you, you immediately open your, the presentation file. Okay. It's working. Yeah. Thank you.
Okay. Okay. Good. Good. Thank you.
Yeah. Harsha, can you hear me? I can't hear you, man.
Am I audible now, sir?
Yeah, now it is okay. Yeah. Okay, good. Can you hear me? Yeah. Okay. So now I'm going to ask you to share the screen. Can you hear me?
Am I audible, sir? No?
You are audible, but do you hear me?
Yeah, yeah. Yes,
okay,
sir.
Yeah. Okay. Now I'm going to ask you to share the screen. Yeah.
Okay.
Open the PowerPoint, please.
Yeah, yeah. I'm doing it.
Keep the PowerPoint. All the guys, keep your PowerPoints open to save the time. Yeah. Okay. All good. All good, man. Okay. Thank you. Okay. You're working. Okay. Keep that way so that, when your presentation is on, you will be on. Yeah. Okay.
Yeah. Okay. Thank you, sir.
Thank you. Okay, the session chair, Professor Young Sik, okay, is not here yet. So let me get started. Okay, we're about to start. Karthik, I'm going to start the presentations. Okay, I think if the professor, okay, comes, looking for his name.
Yes, please, yeah, Param, you please get
Okay,
started.
thank you. Yeah, okay.
So if he joins, then he can help us with the.
Yeah, okay, fine. Yeah, okay. Okay, guys, welcome back. I'm hoping you got some coffee to take or drink some water. Okay, the last session for today, it's focusing again on the applied pyrolysis, with mainly focusing on the oral presentations and also the panel discussion. Okay, now Professor okay will join later, so let me get to the presentation. Okay, the first speaker, Mr. Harshal Kawale, is focusing on the comparative study on waste valorization of lignocellulosic biomass, e-waste and rubber tube waste to produce high quality bio-oil using single and co-feed pyrolysis. Let me quickly introduce Mr. Harshal. He is doing a PhD. I think it's almost finished. His PhD in chemical engineering from IIT Guwahati. Did his MTech in chemical engineering from Dr. Baba Sahib Ambedkar Technology University in Maharashtra. He is an active researcher for the last 6 years in chemical engineering with expertise on the biochemical conversion of wastewater, waste biomass into electricity and thermochemical conversion of biomass waste material to energy and valued products. Let me welcome Mr. Harshal Kawale to make a presentation. I'm going to share the screen. Asking, okay. Okay. Harshal, it's all yours now. You have 10 minutes presentation, okay?
Yeah. Okay. Thank you, sir.
Okay, go on.
Yeah. Welcome all to my presentation on waste valorization of lignocellulosic biomass, e-waste and rubber waste to produce high quality bioil using single and co-feed pyrolysis. Just wait, sir. My screen is not adjusting. Yeah, it's okay. Welcome all to my presentation on comparative study on waste validation of lignocellulosic biomass, e-waste, rubber tube waste to produce biofuels and high quality bio-oil using single and co-feed pyrolysis. So as we all, what is happening? There is some problem, sir. Hello.
From our side, it is all right. It's yeah. Your internet connection is not stable.
I don't know, sir.
Maybe
Actually, my
externally-
slides are not moving.
No, I think you can close your webcam. Maybe sometime then net connectivity is not stable.
Okay. Yeah.
The bandwidth is low. Yeah.
Okay, sir. Still, my presentation is not moving, sir.
Now we can see actually, because we can see your presentation, but you say so you can close and open again. Okay, you can close your file and open it again.
Okay, sir.
You use a drop down cursor, then drop down, move up and down.
Yes,
sign.
sir, I'm trying, but it's my actually laptop got hanged, sir. I don't know why. I'll just log out and log in again, sir. Please bear with me, please.
Okay. You don't mind? I will contact you again. Okay. Let's get to the next speaker. Yeah.
Fine,
Okay. Thank you.
Yeah. Thank you very much, sir.
Okay, we have Professor OK here. Would like to share a few words, sir, for this session. We're Professor OK.
Yes, I'm here.
Okay, we just started. We just started the session, but there is some interruption with his internet. Okay, you can introduce
Right,
it. Yeah.
Right.
Yeah.
So this session is for voluntary presentation. So I may not introduce the speakers, but speakers could introduce shortly themselves just before the presentation. And at the presentation, we could have a discussion session, right?
Yes, that's right. Yeah.
Yes. Thank you.
Thank you.
So please go ahead.
Okay, let me introduce the next speech. Mustafa, are you ready?
Yes, I am.
What is going on? Your internet is okay? Are you there?
Yeah, it's okay. Yeah, I'm there. It's okay.
Okay. The next presenter is the Mr. Mustafa Danladi Ibrahim. He is going to speak on the potential of Bambara groundnut shell, sweet sorghum stalk, and shea nut shell for bio-oil production through the intermediate pyrolysis. Let me brief about him. He is a tutor in the Department of Chemical Engineering, Faculty of Engineering Technology at Abubakar Tafawa Balewa University, Bauchi State, Nigeria, where he has been staff since 2014. Mustafa is on scholarship from the Petroleum Technology Department Fund, Nigeria, as a postgraduate researcher at the University of Nottingham. He held both his first and master's degree from the Federal University of Technology, Minna, Nigerian State, Nigeria. His main research interests are in chemical engineering, renewable energy, biomass, and also pyrolysis, gasification, process optimization, water quality analysis, and water treatment. He has several journal publication, conference papers, attended several workshops, and still counting. Let's welcome Mr. Mustafa to make a presentation. Yeah. Let me share your screen to you. There we go. Yeah, okay. Go to the first slide, please. Yeah, okay.
Okay.
All good, yeah.
Okay, good day, ladies and gentlemen. It's my pleasure to be here at the International Symposium of Analytical and Applied Pyrolysis. I'm here to present the paper titled Bambara groundnut shell, sweet sorghum stalk, shea nut shell for bio-oil production. I'll be considering these three samples. The first is the Bambara groundnut shell. It's an indigenous African crop but we have several in different countries, like we're considering that from one Nigeria, which is referred to as Executor, and with the label here as T1. And we have one from Indonesia, which is known as IPB BAM6, and one from Thailand, which is called Songkla 1. Of course, it's a nutritional food. It was discovered because it was one of the underutilized crops, and the seed, that is the nut, is what is being considered. So the pod is a waste, and that is what we are considering in this case. It was reported that along the Mediterranean Sea, where it was cultivated, they have a pod yield of about 8.5 tons per acre, which is quite enormous. The second sample is sweet sorghum. Sweet sorghum is cultivated in Africa and also part of Europe, where it is being used for ethanol production. And we deemed it fit to look into it and see what potential this stock could give. And the global marginal land for sweet sorghum stock is about 5 million acres. So we don't have any issues of struggling about where it will be cultivated. The third is the share nut. Share nut predominantly exists within the eastern part to the western part of Africa down to the Ethiopian island. It is being used for the production of shea butter, which is used in pharmaceutical industries. It's used in hair and skincare industries as well. Because of the high demand, it is actually processed in this manner, where the kernel is being collected for further processing, and the shell is now rendered waste. So we have huge amount of waste lying fallow, and that is one of the reasons why we decided to look into it to see what potential we could derive from that. This is how it looks like. It has the kernel in it, which is being processed for shea butter, and the shell, which we are considering now in this work. And it has been reported about 60,000 metric tons of this shea butter is being exported. Of course, how can you imagine the waste that will be generated, and those that are actually not exported, which are used within the country or within the continent itself. The objective of this paper is to determine the physicochemical properties of the BGS, SSS, SNS feedstocks, that is the Barchar shell, the sweet sorghum stalk, and the shea nut shell, and then to carry out an intermediate pyrolysis of these three samples. And then lastly, to find out or to evaluate the physicochemical property of the biofuel and biochar produced. The experiment was carried out in an intermediate pyrolysis system with an operation temperature of about 600, 1 atmosphere as a pressure, and 10 ml per minute of nitrogen flow. The biomass used is around 70 grams. As normal, the feed is charged into the system and then operated, and while we were able to take note of the appearance of the fume and the disappearance as well. And finally, we got the biochar being collected. The system runs around about 30 to 33 minutes, and our final products were collected. And we're able to get our biochar, and we're also able to get our biofuel, which is that we in the vertical pyrolysis reactor. When we carry out the analysis for the feedstocks, we have the G1, G4, and G5, which are all under the category of Barchar shell, and then we have SSS and SNS and SNC. We consider the activation energy for all the samples, and all of them were below 20 megajoule per kilogram. And the least was the SNC, which is very low and which is around 7.87. We also considered evaluated the moisture content, and we got the moisture content were around, the first 5 samples were around 10 to 12 weight percent, while SNC is as high as 47 weight percent. And we also did carry out the evaluation for the ash content, and they were reasonably okay, but SNC still seems higher compared to the rest of the samples. The volatile matter of all the samples were above 60 weight percent, but that of SNC still remains very low at 27.5 weight percent. And the fixed carbon, we are averagely at the lowest level. So on that note, SNC could not give us a promising biofuel characteristics from this analysis. Then we carry out the CHNS analysis, and that analysis also we're able to get the information and use to plot. I will plot it in the Barchar diagram. Hello. Hello.
Yes. Hi. Yeah.
Hello.
Can you hear me? Yeah.
Yeah, I can hear you. All right. So we now plot the CHNS value in the Barchar diagram that describes that if you have a biomass sample and your averaging carbon ratio should be less than 1.8, which conforms with what we've gotten, and the oxygen carbon ratio should be within the range of 0.4 to 1, while virtually all the samples conform to that except for SSS, which is above 1 on the x-axis. The next result here, we evaluated for the activation energy, and we got our activation energy of all the samples at around 18 kilojoule per mole Kelvin, except for SSS, which is as low as 14 kilojoule per Kelvin. Then afterwards, we carry out the analysis based on the bio-oil yield, the biochar yield, and to the corresponding high eating value. From the first product here for the bio-oil, the BGS, which is BGS G1, was the only one considered here out of the 3 BGS we had, and the yield here was about 33.89 weight percent, and the SSS was the highest with 44.16%, and then the share not shell was 39.63%. And it could, compared to some of the work that have been carried out, it's been considered reasonably well. So if we want to improve further, we will also take some necessary measures to see how we can improve on that. And then we have the biochar, which is for the breakdown of shell was as high as 45.6, 27.1 was for SSS, and 43.61 was for the SNS. I'm sorry. Then the biogas was just complementary for the 3 samples that we are actually getting, and we had it as 20.44 for the BGS, 28.7 for the SSS, and 16.74 for the SNS. And then when we carry out the high eating value for all the 3 samples, in the fourth category here, you realize that the BGS had about 22.41 megajoule per kilogram, and then the SSS had about 22.52, while the SNS had about 25.05, which is quite impressive. And then lastly, we have the biochar, which the least was 17.99, and the highest value was 24.91 for SSS. In conclusion, the physicochemical analysis of the samples that were carried out were potential feedstock for biofuel production, except SNC, that is share not chaff. And then the average activation energy were around 18 kilojoule per mole Kelvin, while except the SSS, which is 14 kilojoule per mole Kelvin. And then the oil yield are quite appreciable. None of them were less than 13 weight percent. And the high eating value were also quite very impressive. Thank you for your time.
Okay. Thank you, Mr. Mustafa. That's an interesting presentation. Okay, if you have any questions to Mustafa, please post your questions in the question box, and we'll address it after the oral presentation. Thank you. Thank you, Mustafa. Yeah. Let me take over my screen. Now I invite the next speaker. Is focusing on the co-pyrolysis of algae and plastic for a deoxygenation and a denitrification. Miss Jiyue Tang, are you there? Let me take your share. Okay, please share your screen, please. Ms. Tang, are you there? Okay.
Okay, I'm here.
Okay, please make a presentation. Yeah. Turn the presentation mode, please.
You here?
Okay, click on the presentation mode.
Okay, I will start my presentation. Good afternoon, everyone. It's a great pleasure to attend this conference. The topic of my presentation is co-pyrolysis of algae with LDPE for deoxygenation and de-electrification. My presentation is divided into the following 4 parts. Firstly, introduction. Algae, known as the third generation biofuel, is becoming one of the most promising biomass resource because of the high growth rate, high CO2 utilization, the ability to remove nitrogen and phosphorus, and high biofuel yield. But different with wood biomass, algae mainly consists of carbohydrates, proteins, and lipids, which lead to high oxygen and nitrogen contents in pyrolytic oil. They are the critical challenge for algae pyrolysis technology, which result in instability, environmentally unfriendly, and low heat value of oil. To improve the quality of co-pyrolysis is a potential method. It has been reported that wood biomass co-pyrolysis with plastics could inhibit the formation of acid, accelerate deoxygenation, and improve the hydrogen and carbon contents of the liquid products. Besides, waste plastics and the resultant pollution flow into the rivers, oceans, lands, and adversely affect the biodiversity. Therefore, can we utilize co-pyrolysis of algae with plastics to remove oxygen and nitrogen, improve hydrocarbons and the quality of oil? The experiments were performed in a fixed bed system, as shown in figure. Liquid nitrogen was used to collect liquid products. NS and LDPE were chosen. The pyrolytic temperature is 600 degrees centigrade. As shown in the table, NS mainly consists of lipids and proteins with some carbohydrates, which result high oxygen and nitrogen content, and LDPE is mainly composed of carbon and hydrogen. When algae co-pyrolysis with LDPE, the gas yield was higher than the theoretical value, and the liquid oil yield was lower than the theoretical value. It may be attributed to that co-pyrolysis promote the secondary character of heavy volatiles into light gas molecules. Besides, the interaction effect of co-pyrolysis on gas and liquid oil yields reach the strongest at 25% LDPE. Besides, co-pyrolysis promote the generation of methane, carbon 2 plus, and CO and hydrogen, especially hydrocarbon gases, but low significant effect on CO2 at low LDPE addition. For the oil, it's found that LDPE adding could effectively reduce the oxygen and nitrogen containing compounds and Aliphatic increased significantly with LDPE increasing. Besides, it's discovery that the water content is higher than the theoretic value, especially with low LDPE addition. Therefore, it may be attributed to that co-pyrolysis promoted the evolution of the oxygen-containing groups to water. Compare with that of the chart from NS pyrolysis, the hydrogen-carbon ratio of co-pyrolysis charts were significantly lower, whereas no significant change on the oxygen-carbon ratio with 25 LDP addition, which was suggested that dehydrogenation, demethylation are the main reaction. With LDPE further increasing, oxygen-carbon ratio gradually decreased, which may be due to that high LDPE addition accelerate decarbonylation. Besides, as the LDPE increasing, the relative content of pyridinical nitrogen and pyrronic nitrogen increase. Furthermore, the distribution of oxygen and nitrogen in the co-pyrolysis products declared that the oxygen in algae mainly evolved into water instead of CO2, and the nitrogen in algae gradually is transferred to gas products with LDP increasing. Finally, the conclusion is summarized as follows. Co-pyrolysis of algae and LDPE improve the gas yield, promote the generation of CO, hydrogen, methane, and carbon 2+. Oxygen and nitrogen containing compounds in oil decreased rapidly. Aliphatics increased significantly. Low LDPE addition mainly promote dehydration, and higher LDPE addition accelerate dehydration and decarboxylation. And besides, oxygen mainly involved into water and nitrogen involved into gas products. Thank you for your attention. Thank you.
Thank you, Ms. Tang. It's an interesting presentation. Let me take question. If you have any questions to Ms. Tang, please post your questions in the question box. We address them at the end. Yeah. Okay. Okay, the next presentation. The next presentation is on the debrominated liquid production from the non-metallic fractions of printed circuit boards by catalytic pyrolysis. The presentation will be done by Dr. Chong Ma. And just brief about him, he is working as a JSPS fellow in Professor Yoshioka lab at the Tohoku University. He received his PhD degree. He received his PhD degree from the Hwakjong University of Science and Technology in 2017. After graduation, he worked at the National Institute of Advanced Industrial Science and Technology in Japan for 3 years as a postdoctoral fellow. Then he was awarded with the JSPS fellowship in 2019 and started his JSPS research at the Tohoku University this year. His main research areas are development of recycling technology on solid waste and utilization of resources from the end-of-life products by chemical treatment. So far, he has published over 30 SCI papers in prestigious international journals. Dr. Ma, welcome you to this presentation, and let me take over, give you the screen. Yeah.
Okay. Okay, thank you. Can you hear me?
Yes.
Okay, I will start my presentation. Okay, yeah, my camera, okay. Okay.
You have 10 minutes, yeah?
Okay. Okay, let me. Hello everyone, my name is Chama from China. Now I'm working at Tokyo University. My topic is about debrominated liquid production from the non-mechanical fractions of printed circuit boards by catalytic pyrolysis. My topic is mainly about four parts. First is the background. It has been reported that nearly around 15 million tons of US are generated annually. As to the printed circuit boards, it takes about 3 or to 6% of the US, and it usually consists of the non-mechanical fractions and precious metals with high recycling value. Meanwhile, it also contains a lot of toxic substances, such as the heavy metals and also the halogen flame retardants. Currently, a lot of the technologies have been applied for recycling of the metals. However, as to the 17% of the non-mechanical fractions, chemical recycling has been the most promising technologies for converting the organic fractions into fuel and chemical feedstocks. Okay. As to the non-mechanical fractions, it mainly consists of the brominated epoxy resin and glass fiber. However, during the pyrolysis, a lot of the brominated compounds produced in the pyrolysis products, it cannot be used for further applications. So it is essential to remove the toxic bromine and upgrade the products during the process. Herein, a two-stage pyrolysis and debromination process of the PCBs is proposed in our work. And our main objectives focus on the recovery of the high-value products and remove the toxic bromine compounds. And also, we need considering the reuse of the low-cost catalyst. Now, here is the experiment procedure. The modern epoxy boards contain around 38% of the organic fractions and also contains around 7.6% of the bromine. Around 50 grams of the PCBs was first pyrolyzed at the bottom, and then the volatile products was reformed by the catalyst at the upstage. After reaction, the pyrolyzed products mainly classified into 6 parts. And the oil was analyzed by the GCFID mass and the ECDs. And also the gas was analyzed by the GCFID and the TCDs. Furthermore, in order to figure out the transportation of the bromine species was analyzed by the GC ECDs, and also the inorganic bromine was analyzed by the IC. Okay, here is the results. The first is about the effect of the metal and acetic catalyst. We commonly use the iron powder and also the zeolite and the nickel loading catalyst. Basically, we found that around 15% of the oil was produced from the organic fraction in PCBs. However, in the presence of the zeolite and the nickel loading catalyst, we find that the oil yield was largely reduced. But compared to these two active catalysts, we found that in iron powders, the oil was just slightly reduced. Here is the main compounds in the oil and the gas yield. We can see that in the presence of the zeolite and the nickel loading, the zeolite can largely increase the production of the single aromatics and also the phenol. And the nickel catalyst shows slightly effects on the composition of oil, and also we found that the nickel catalyst was benefit for the production of gas products like the hydrogen and the carbon monoxide. But compared to these two, we found the iron powder can reach a higher highest yield of the phenol. And also we found that there's a relative higher concentration of the hydrogen produced in the presence of iron powder. As to the bromine immigration, we found that most of the bromine was transferred into the oil and the aqueous fractions in organic form and organic form. We detect the bromine compound in the oil. We found that the diamylite and the nickel catalyst was quite active to remove the organic bromine, but still contain a lot of inorganic bromine. However, compared to these two catalysts in iron powders, we found that the iron powder was in favor of capturing the bromine compounds both in organic and organic bromides, but is still far away from our target. Okay, secondly, we conduct the steam reaction of the PCBs in the presence of iron powder. It shows that when we introduction the steam, we found that the formation of the gas and the steam was benefit for the production of the gas and the oil. And higher temperature would slightly decrease the oil products. However, compared to the presence of the steam and iron, we found that in the presence of iron, the oil was slightly decreased. And in the composition in the oil, we see that in the injection of the steam can largely increase the production of the phenol and also the aromaticals. When we add the iron powders, we found that the aromatical compounds would further increase, and as well as we keep a high concentration of the phenol. As to the gas products, we found that higher concentration of the hydrogen and the carbon monoxides produced in the presence of steam. It should be due to the steam reforming reaction and also the water-gas shift reactions. However, in the presence of iron powder, we found that more than over 20 times of hydrogen was produced compared to that without additives. But when the temperature reached to 700, we found that the produce of hydrogen was slightly decreased. Then we further investigate the bromine distribution, and it's very interesting to find that in the presence of steam, when the temperature reached up to 6 to 700, very small amount of the bromine was detected in the oil, and most of them transferred in the aqueous fractions. Furthermore, in the presence of the iron powder, we found that the bromine concentration in the oil was further decreased, and most of them was transferred into iron bromides, which exists in the inner residues. But it's interesting to find that when we increase the temperature from 500 to 700, we found that the iron bromide was largely decreased. Then we analyzed the spent iron powder by the XRD and the XRF. We also shows that with the increasing temperature, the iron oxides and the iron bromide was reduced. However, at 700, we detect the ferrous oxides. It means that the reduction reaction might happen during the pyrolysis at high temperature. The XPS result also shows that the bromine concentration in the residues was decreased with the increasing temperature, and also the ferrous iron, the ratio of the ferrous iron was increased at the 700. Okay, here I'd like to briefly discuss about the mechanism. We know that the brominated epoxy resin mainly focus on the free radical reactions, which can produce the major primary products like the bisophenol A and the brominated bisophenol A. And then through the radical depolymerization reaction, it can produce a lot of the products like the phenol, bisophenol A, and isopropyl and so on. However, in the presence of the steam, we can find that a lot of the hydrogen produced. One thing, the injection of the steam can create a more uniform reaction atmosphere for the intensive cracking of the vapor products. Meanwhile, the production of the hydrogen can benefit for the dehydroxidation of the phenol and the other compounds. At the same time, it can also convert the organobromides into inorganic form. And in the presence of the iron powder, we found that the strong steam ion reactions occurred can provide a lot of the hydrogens. They provide the hydrogens, it means it also provide a lot of the hydrogen dollar, which is benefit for the dehydroxidation and also the debromination performance. However, at higher temperature, we found that the vapor products produced from the PCBs can also show some reductive performance, can change the oxidized iron into the iron powder. Then we give this kind of concludes. We see that in the presence of iron powder, the chemical reaction and the physical absorption may be a benefit for the capture of the bromide, and the zeolite and the nickel catalysts show the active cracking performance to reduce the oil yield and increase the gas yield. However, in the presence of the steam cracking, we found that the reached hydrogen dollar was produced by the steam ion reactions, which is benefits both for the oil and the gas, and also can remove the organic bromide. Okay, here is the conclusions. The high production of phenol derivatives was obtained by the iron powders. Oxidative catalysts promote the formation of the aromatics and enhance the cracking of the organobromides. The iron powder exhibits excellent debromination performance with higher absorption abilities of inorganic bromide. The dehydrogenation and the debromination reactions of vapor products were accelerated by the steam ion reaction. Recycling of the iron powders can be achieved during the steam ion process. I'd like to thank the support for the study from JOCMEC and also the JSPS. Okay, thank you for your attention. That's all.
Thank you, Dr. Ma. Guys, it's an interesting presentation. And if you have any questions to Dr. Ma, please post in the question box and we address it in the discussion session. Thank you. Let me take over my screen. Okay, the next presentation is on the is a product presentation by CDS Analytical by Mr. Roger Tank. Let me quickly brief about him. He's a senior sales manager for CDS Analytical with a bachelor degree in analytical chemistry and mathematics from the Western Michigan University. Before joining CDS Analytical, he was a USA business development manager for the pyrolysis with the Frontier Laboratories for 3 years. Roger spent 17 years with Agilent Technologies, 15 of which were managing the Dow Chemical Company account at their headquarters in Midland, Michigan. Adding to the depth of his technical background, he also held positions in analytical instrument companies for products including GC, GCMS, GPC, LC, LCMS, LCP, ICP-MS, TOFMS, UV, IR, ICIA, electrochemistry, etc. And he worked with many of the instrument suppliers. Roger, welcome to the PYRO Asia Forum. Thank you for supporting us for this event, and let me ask you to share your screen.
So, are we all set?
All set, good.
Okay.
You got 10 minutes, please. Yeah.
Okay, great. Thank you. Yeah, first of all, I'd like to thank all the people that have put together PYRO Asia 2020. We really appreciate your time and your effort to expand the technology and the scientific studies going on, and also the fellow presenters who really spent time on their own specific scientific projects. Okay. Okay. Next is, oops, I lost the ability to change slides. Okay, there we go. Okay, basically, CDS Instrument is a company that supports the pyrolysis community. We basically provide the technology for people to be able to do their research projects. Basically, CDS launched the first commercial analytical pyrolyzer in 1969, the first to do so. We've gone through about 6 generations. The basis of our technology is proprietary energy reservoir. We can provide the highest pyrolysis temperatures. And one of the inherent advantages is the low thermal mass that we have provides for a fast temperature ramp up, 20,000 degrees centigrade per second, Celsius per second. And then also, because of that low thermal mass, a very, very rapid cool down of only 15 seconds. Basically, the idea is that the same thing like on an aircraft carrier where a plane cannot reach sufficient speed to lift off the aircraft carrier. So it uses a catapult. And so there's a high storage of energy, and then that energy is applied to the plane to get it to a much faster speed so it can take off. We use the same principle. What you see here on the right-hand side are the old probes for the technology that has been changed. We used quartz tubes with the sample packed between 2 pieces of quartz wool. That technology now has changed. And what you're seeing here is our 6th generation drop-in sample chamber. So in essence, what we have is now a quartz tube with a fixed point of sample placement. So the sample is always going to be in a narrow zone. So it's easier sample prep than dealing with quartz wool and location of a sample. It reduces the operator error, and also it is liquid sample compatible. You can put your liquid right in there. And also, and part of the reason that we did this change was the improvement of the sample positioning accuracy, so it receives the same temperature. And that really fundamentally is the key to reproducibility in pyrolysis, is that exact location so the temperature is very reproducible. Basically, we also had consistency of the algorithms so that people who've done work in the past are going to be have the same information. This is what we're talking about in terms of the enhanced reproducibility. We're able to deliver 1.5% RSD, the analysis of styrene monomer to trimer ratios. So easier sample loading. What we'll talk about a little bit more in the future here is about the modular design so that we can have really multi-technique functionality and also leak check. So when most people think of pyrolysis, what they think of is right up here on the top, just classical pyrolysis. But in modern technology, the things that we're able to do are do kinetic studies, thermal desorption, doing evolved gas analysis, dynamic headspace. In essence, EGA is also confusing for people. All this simply is most people are familiar with TGA. So basically, you take a sample, you basically heat it up, but in TGA, you're doing a weight loss. We do the same thing. We basically heat the sample up over a period of time, but now it's directly connected through just a short transfer line, through silica transfer line, directly to the mass spec. So now instead of getting weight loss, we are getting true chemical information. Okay, this is what I was talking about in terms of the 6th generation pyro probe. Here's your actual sample quartz tube. And now basically this is just simply opened up and dropped in and then closed. It can be fully automated, but the idea is to eliminate any direct contact with the coil. And once again, like we talked about the the location of the sample being critical, so it receives the same exact heat every time. These are just a few of the additional capabilities. We're going to go through that in a actual decision tree. This is where, you know, modern technology allows us to do a lot more things. This is no longer just for pyrolysis. This is really a tool set, and this tool set is designed to provide you with one instrument to provide you a wide range of functionality. Unfortunately, this was done in a different size. So what you see right up here is that would actually be the sample tube. So from here, you have a GC or GCMS. You don't really have that. You can still connect this up to an FTIR via our Brill cell. The other way is that you've got a GC GCMS. Let's say you want to do air sampling thermal desorption. So you can use standardized 3.5 inch, quarter inch by 3.5 inch stainless steel tubes that are commonly used for thermal desorption now. Basically, you can also then, if you're interested in VOCs, you can actually go ahead and use a cryo trap. The 6200 comes standard with a standardized trap, similar to what's used in thermal desorption, but for VVOCs, very volatile organic compounds, sometimes you have to get to a lower temperature, and so you can put on the optional cryo trap. This is what we were talking about, evolved gas analysis. So basically from here now, that gives you a profile of exactly what comes out as a function of time. So it depends now is that basically you're getting multiple peaks coming out. If you basically want to move irrelevant substances, you may want to go to something like heart cutting. Think of it as a thermal slicing technique. From there, if you can go actually do a multi-step analysis. So because of our rapid cooling, you can do, let's say 0 to 100 and then cool, 0 to 200 then cool, 0 to 300 then cool, 0 to 400 then cool. So it actually allows you to actually go through those steps so you don't have peaks overlapping on your chromatogram. This, what you see, 6150 is our base unit. It just basically does the most of the standard techniques. When you're talking about 6200, now that is our advanced system that has the capability of doing a lot of different additional techniques. So for example, back to multiple peaks here, if you want to do a single step pyrolysis, typically 100 to 1 split, not sensitive enough, you can decrease the split. The other thing you can do is you can actually go over here and use a different type of probe. This type of probe here allows you to do a larger, much larger sample, half-inch probe up to 350 milligrams of sample. You have to always keep in mind though is that you don't want to put too much sample on the system. You're typically running this through a GCMS system, so you don't want to overload your GCMS system. Down here is that, for example, if you're doing VOCs and you actually preparing the sample, you can actually then do those. And then if you need increased sample sensitivity, now basically you can actually go to a larger sampling device, or you could actually go to dynamic headspace. On this area here, in terms of basically now, if we're going to reactant type studies, you can do photochemistry with a technology called the photoprobe, and that gives you a lot of flexibility of mimicking what's going to happen in normal sunlight. If you actually want to do this, but you actually want to use high pressure, we have another device called 5200 HPR high pressure reactor. If you just want to do straight catalyst work under low pressures, now you have the ability to do the 6200 with low pressure catalysis. So the idea of this decision-making tree is that this is not just for one type of technology. It's not just for pyrolysis. It's a multifunction tool for quantitative and qualitative analysis. And with that, I just would like to add one last thing, is that basically one of our co-sponsors here is one of our distributors in India. They're exclusive for India. Ajit Sandakar is the CEO of that group. And like I said, he's exclusive for India for CDS. And his company is ASMI Analytical. Once again, thank you for your time and for your participation.
Okay. Thank you, Roger. I appreciate the presentation. Thank you. Okay, let me take over the screen. If you'd like to guys ask any questions to Roger, then please post questions in the question box. Thank you. Okay, let me go back to the Harsha, who has a problem. Harsha, I hope you're ready. I'm going to share the request you to share the screen.
Yes, sir.
Okay.
So am I audible, sir?
Yes, you are. Go on. Yes.
Yeah.
10 minutes, please. Yeah.
Yeah. Welcome back. So I, Harshal Dikawade, welcome you all to my presentation on comparative study on waste valorization of lignocellulosic biomass, e-waste and rubber tube waste to produce high quality bio-oil using single and co-feed pyrolysis. So as we all use non-renewable fossil fuels for our daily transportation as well as energy needs, the greenhouse gases emitted by them are causing global warming. Due to population growth, the need for energy is ever increasing. On the other hand, these fuels are depleting due to overuse. Another problem is also a waste minimization. So treat these burning issues, to overcome these burning issues, we need to develop fruitful technologies, and the thermochemical processes are quick response technologies, whereas among thermochemical technologies, pyrolysis is, has an upper hand, as it is simple and comes with easy handling. So the waste materials I have chosen are scarcely researched lignocellulosic biomass of Delonis regia, then mobile e-waste, and then rubber tube waste. So single feed and co-feed of Delonis, and then co-feed of Delonis regia with electronic waste on 1:1 basis, and Delonis regia with tube waste on 1:1 basis are conducted, and then the results are compared. So this is the pyrolysis setup which I have used in my study. It has a feed holding capacity of 300 grams. The material is fed into the reactor here, and then the nitrogen gas is passed, and the temperature is set at by the furnace, and then the pyrolytic vapors goes through the condenser, and then then condensate and non-condensable gases are separated in this gas liquid separator, and then the condensate goes down to the by the gravity settling to the bio-oil collection vessel, and the gases are taken out for the further analysis like the bio-oil. So now the experimental conditions are such as the sample of Delonis regia, single feed and co-feed, all the samples all the samples in all the cases are 300 grams. The carrier was nitrogen gas. Temperature was set at 600 degrees Celsius. The pressure was at 1 bar, and the heating rate of furnace is 12 degrees Celsius per minute, and the reaction time is of 2 hours. So this is basically a slow pyrolysis, but it has a good capacity of holding capacity of material. So moving on to the product yield distribution, the comparison between lignocellulosic biomass bio-oil and the bio-oil obtained from the co-feed pyrolysis has been presented here. So we got 29% bio-oil, weight percent bio-oil from DR biomass, whereas 17 weight percent from DR with e-waste on 1:1 basis, which is lowest among all the studied cases, and then 36.67 weight percent bio-oil is obtained from DR with tube waste on 1:1 basis. The highest amount of biochar is obtained from DR plus electronic waste on 1:1 basis. So comparing physicochemical characteristics and fuel characteristics of this particular three reactions, the pH is actually increasing. Increasing means acidity is decreasing, and pH value is showing that DR bio oil, Delignus regia bio oil, has 4 pH value, whereas it is improving for co-feed of electronic waste with DR, and again improving for tube waste with TR, and having 4.58 value. So on the contrary, the density and viscosity are decreasing, which are showing 0.94 value for DR plus tube waste, and 1.32 0.94 kg per liter density is for DR plus tube waste, and then viscosity is 1.32 millipascal second for DR plus tube waste material. So lately this HHV is also improving significantly. That Delignus regia bio oil, means bio oil obtained from DR biomass, showing 18.8 megajoule per kg of HHV, and then when we added electronic waste on 1:1 basis, then it is showing 25.4 megajoule per kg of calorific value, and then DR plus tube waste showing the highest calorific value of 32.6 megajoule per kg among all the cases. So further I have tested these bio oils on FTIR analysis. So where we found that the wave number of 3749 centimeter inverse shows OH in alcohols and phenols. Then 2923 centimeter inverse shows CS3 and CS2 in aliphatic compounds. Then 1716 wave number shows ketones, and then 1400 to 1000 it is showing aliphatic and aromatics, and from 800 to 500 they are showing benzenes. This is FTR analysis for DR plus tube waste study. Whereas we have found this bio oil obtained from DR biomass shows a very broad spectra, which is of polymeric OH, and that is due to the water content present in the bio oil, and it is showing the ketones. You can see here, as ketones are increased amount of ketones are there as compared to the COVID study. So these are the FTIR results, whereas the GCMS of DR plus tube waste study was conducted. So here this graph is showing GCMS spectra of DR plus tube waste study, and then major components are shown here, like benzene 1-ethyl 2-methyl, benzene 1,4-diethyl, next to that D-limonene, then paracresol, and naphthalene 1,6,7-trimethyl. So these are the main components obtained, and based on GCMS analysis, I have categorized these compounds, and then the list is presented here. So furans, phenols, and ketones, which are oxygenated compounds, they are less in DR plus, very less actually, in DR plus tube waste study to compare to that of Delignus regia bio oil. So the aromatics and aliphatics are also increasing with very high amount, whereas aromatic of 42.66 area percent we are getting in DR plus tube waste study, and 42.99 in aliphatics are produced in DR plus tube waste study. So basically, DR produced benzene and phenol as highest and second highest area percentage occupying compounds, whereas DR plus tube waste study shown D-limonene as highest area percentage occupying compound with 22.29 area percentage. This is quite enough. So in conclusion, for my concluding remarks, single feed pyrolysis and co-feed pyrolysis of lignocellulosic biomass, Delignus regia, and mobile e-waste with and tube waste generated high quality products, resulting waste valorization. The production of bio-oil showed that that scarcely researched lignocellulosic biomass of Delignus regia resulted in 29% of bio-oil, whereas DR plus electronic waste resulted in 17% of bio-oil, and DR with tube waste resulted in highest yield of 36.67%. The HHV of bio-oil obtained from DR has 18.8 megajoule per kg value, Then DR plus electronic waste resulted in 25.4 megajoule per kg of calorific value, and then highest HHV is obtained again from DR plus tube waste study with 32.6 megajoule per kg of calorific value. So co-feed of DR plus tube waste resulted in lowest oxygenates, promoting deoxygenation of bio-oil by in situ upgradation with addition of tube waste material. Also, the physical properties are improved. The GCMS result showed the highest area percent occupying hydrocarbon as aliphatic compound of D-limonene with 22.29 area percentage, and second highest as benzene 1,4-diol ethyl with 9.13 area percent for Delius regia with tube waste co-feed study. Overall, this study delivers waste minimization approach with energy conversion of various types of materials such as lignocellulosic biomass, mobile e-waste, and then tube waste into valuable fuels and hydrocarbons. And DR plus tube waste studies stand alone amongst all the 3 studies. So that's it. Thank you.
Thank you very much, Harshal. You managed it with your internet. Thank you. Okay, let me take over the screen now. I invite Professor OK to have a discussion on this various presentations, and in the meantime I collect the questions from the audience. Okay, just a second. Oops. Here. Okay. Share my screen. Yes. Okay. Your audio is on, sir. Yeah.
Okay. Hello, everyone. Thank you very much for your presentation. So, because the time is quite limited, though today we had a total 5 short oral presentation. So, if you have any question for the presentation, just feel free to let us know. And I would suggest for all the speaker to join the Q&A by turning on the video and audio so that we can discuss together. So could you all to join this event? Yeah. Thank you.
Mm-hmm.
I have questions.
So just wonder, could we able to get a few questions from the audience?
Yes, we have some questions. Let me pause and share the screen for you.
Okay, thank you. So we have a question to Jiu Tang. What is the main reaction pathway for the synergistic effect on the decrease of N-containing pyrogate? Is it converted to gas or char more by pyrolysis? Could you provide your short answer for the question?
I answer the question now.
Yes, you can give a short answer for the question.
Okay. When algae co-pyrolysis with LDP, the nitrogen containing melanin evaluated into gas products, and the nitrogen in char and in oil is reduced. So when during the co-pyrolysis process, the nitrogen is melanin involved into gas products.
Okay, so thank you so much. So hope it was a good answer for the question from the audience. If you have any additional question, please feel free to contact the presenter. during this PYRO Asia conference. And just before we move to the panel discussion, we have two more questions. So second question is going to Dr. Chuan Ma. Could you please let us know the analytical instrumentation and condition for the detection of HBr generated from the catalytic pyrolysis of PCB?
I think it's a very simple question because I already introduced in our experimental procedure. We use the ion chromatography to analyze the bromine, and also some HBr also mixed in the oil. So we use the liquid extraction to remove the HBr in the water solutions, and then we also move it into the ion chromatography. So it's very easy way.
Okay.
And also we give some detail in our papers. You can check it.
Yeah, thank you so much, Dr. Chun Ma. I actually enjoyed your presentation a lot, but due to time limitation, I'll skip my own question.
Okay.
And by the way, before I ask the last question, I have a short announcement. As you know, tomorrow is the end of PYRO Asia conference. Just at the end of conference, at around 7:30, in between, the organizing committee got a lot of applicants for PYRO Asia 2020 Young Scientist Award. We were able to select the best awardee for the event with a lot of committee members together. So we are pleased to announce the award, and with some cash award, some small honorarium. So we will announce it at the end of the conference, and also we will announce the next conference plan. So next year, PYRO Asia conference will be held in organized by myself, and then next one will be organized in China. So that will be also announced shortly at the end of conference. And last one, did you come across any hazard gas product in your experiment? How safety aspects are taken care?
Yeah, yes, that's a good question actually. As we use tube-based material, so it has some sulfur content, so might be there possibility of hydrogen sulfide gas. So what we did, we have collected all the gas coming out of the system in a Tedlar bag, and they are further taken for the analysis. Actually, I haven't shown any analysis. Means I haven't done that analysis part till now. But yeah, so we have taken all the gas inside the Tedlar bags. So we have taken care of that thing.
Right.
Okay.
Thank you so much. As you know, the time is already 8 p.m., but we still have panel discussions. It's quite delayed. So thank you very much for making your presentation, and we will invite the panel and continue for the panel discussion. And thank you again. So you could log out, and I'll do the same. Thank you. Bye bye.
Thank you.
Thank you all.
Thank you.
Thank you.
Thank you. Bye bye.
Okay, we are into the final part of the second day. It's a panel discussion. It's a focus on the applied pyrolysis, biomass, fuels, gasification. The moderator is Professor K. Mohanty, and we have a panelist. And Professor Ji Feng is not able to join. Professor Yoshiaka and also Professor Talada Bhaskar. That is probably not introduced yet. So let me introduce Professor Bhaskar. He is a senior principal scientist currently heading the Material Resource Division at the CSIR Indian Institute of Petroleum, Dehradun, India. He carried out postdoc research and worked as assistant professor in Wakayama University in Japan. His recent interests: heterogeneous catalysis, thermocatalytic conversion of biomass, lignin, waste plastics, and e-waste plastics conversion into value-added hydrocarbons. He has published 170 publications in many journals, and with a high H index of 48 and around 7,200 citations, and contributed 32 book chapters to renowned publishers and 14 patents to his credit, in addition to 300 national and international presentations. He is also on the editorial board of international peer review journals, editor of 6 books. He has received several prestigious awards from various countries, and is a fellow of Royal Society of Chemistry, Biotech Research Society of India, fellow of Telangana Academy of Sciences, fellow of International Society for Energy, Environment, Sustainability. Let's welcome Professor Bhaskar as well to join this panel discussion. Okay. Okay, all are in. Okay. So, Professor Mohanty, it's all yours now.
Thanks, Param, and good evening, everybody, and welcome to session 6 panel discussion on applied pyrolysis biomass. And before we move on and discuss some key issues regarding biomass pyrolysis, as you know that we have been discussing since last 2 days that biomass pyrolysis is a potentially one of the low cost, or you can say the cheapest route towards producing renewable liquid fuels. And but when you talk about commercialization, it possesses multi-scale challenges. So which starts with the very first thing, that's the feedstock, because of the different types of feedstocks that we are using or we are supposed to use for a sustainable process. So that is one of the key challenges, the heterogeneity. Then the second one, these are all we are going to discuss today. That's what I'm just very briefly briefing. And the second one is, of course, about the process, engineering aspects, design aspects, that takes into account the modeling aspects also, which of late has been done by various researchers, and excellent papers are being already there in the literature. So various types of reactors are there, and what we are going to do, how do you process optimize it? This is one another important aspect. And third, which is also a quote to me, and Professor Bhaskar will also agree, is catalyst. So catalyst is something that you need during even the pyrolysis, when you are carrying out a catalytic pyrolysis, or you need it very much to upgrade the bioil. Because you know that bioil, whatever we get, and it's of not a proper quality, so that we can directly use it in some combustion applications. So you need catalyst, but there are several challenges for the catalyst development. So these are the 3 things. See, there are many other aspects also, but since we are talking about applied biomass pyrolysis, I thought of these 3 key challenges, and let us say, or whatever you can say, that how we can work on these particular aspects, so that we can have better bioil quality. Of course, we are not talking about biochar in this particular way. We will also talk about that. So before I begin, I'll request Professor Zhang and Professor Bhaskar to share their thoughts. I'll request first Professor Zhang. Professor Zhang is not there, so Professor Toshiaki to say something about the biomass composition non-homogeneity, and how do we actually take care of this when you go for commercialization. Over to Professor Toshiaki.
Yeah, thank you very much. And now we have to discuss the very widely discussion now. Yeah.
Yeah.
And,
yes.
Yeah. And at first we have to think about pyrolysis processing to make some useful materials, such as just organic chemicals, to solve the environmental issue now. And of course, we need new material, new resources in the world. But considering the environmental issue, and we have to try to the new approach to make some products from the bioresources and organic resources. And I think the pyrolysis is one of the good solutions. And because my talk, I'd like to present my some idea, my concept using my presentation files. Is okay?
Yeah, it's okay. But please, request is that limit your presentation to few minutes so that we can discuss more, and then we'll have an open house discussion also. Please go ahead. Yeah, Param, please allow him to share his screen. Professor Toshiaki's.
I already sent a request. Yeah.
Okay, good. Yes, Professor. Go ahead, please.
Can you?
Yes, we can see. Yes. Yeah.
Can you see my slide?
Yes, yes.
Okay. Yeah, and at first, not so long presentation, and I'd like to talk about the possibility of the pyrolysis processing for solving the environmental issue, and focusing the integration of the RTR and the various industry, and the promotion of the chemical and feedstock recycling. Yeah, as you know, this slide is indicated crude oil used and the production by products type in Japan. But this structured is almost this structured ratio is the same in the world because all the production of some chemical materials is using the same processing. Ratio of the plastic is half of the naphtha, and then the half of the plastics production is half of the naphtha, and totally the plastics production is about 5 or 4% of the crude oil. Not so much considering the crude oil, but the total of the plastic is very widely. And then this is the World Economic Forum Ellen MacArthur Foundation reported that the ratio of the plastic for crude oil will increase 20% in 2015 from 6% in the 2014. This slide is a very famous slide, as you know. And the plastic share of the carbon budget will increase 14% from the 1%. And then the ratio of the plastics will be more than the fish in the ocean by weight. And considering the oil plastics share of the global oil, and in the future, and the global oil share is plastic share is a lot, like here. And then this is you know. And packaging and the buildings constructions of plastics is share is about 60%, and automobile 10%, and household and the other case, and you know this distribution to the plastics applications, you know. And this is a carbon footprint of plastics, and now the 2.8 billion tons carbon dioxide in 2015 in the future. Yeah, and this is very famous slide, and the waste plastics and the effort from all over the world to China. There is a national thought of China in 2017 as one of the recent plastic issues. This figure indicated the situation of 2016, and 123 countries export a total of the 14 million tons of the waste plastics. And China imports a total of the 7.3 about 7 million tons from 43 countries. approximately 60% of the waste plastics is in China. But now is a stop in this case, and all of the plastics stock in each countries now, and in that case, we have to treat all the waste plastics in own countries. And then this is the current status and the future of the waste plastics flow in Japan. And mechanical recycling and the feedstock recycling are carried out, but overwhelmingly the percentage of the landfilling only is increasing the energy, and energy is still high. We have to change to situation. Perhaps even though the mechanical recycling is considered a circular economy, it is at the limit, so many parts must be covered with feedstock. For example, if 2% of the crude oil can be replaced with plastics, about 3.5 million tons of waste plastics can be accepted in the oil refinery industry in case of Japan. Almost this distribution is similar in the world. And so previous recycling concept and the management have been considered only between the market and the plastic using industry. There is no real material cycle. If new technological innovation and the integration between the RTL and the various industries become stronger, a true carbon cycle will become possible. The red line is the meaning of the root of the pyrolysis can contribute, and the market to the petrochemical industry, market to petroleum industry. In this case, the pyrolysis processing is available, maybe. And then, if the change of the resources from petroleum to biomass to petroleum industry and petrochemical industry, in that case, we need a pyrolysis process, one of them, because now to make some chemical materials from biomass using the fermentations processing and enzyme reactions and glycation processes. But other case, lignocellulose and lignin is difficult to using such as fermentation processing. In that case, it's possible to use the pyrolysis processing. Now, today, there are a lot of the researchers try to the pyrolysis processing to make biofuels, and then there are some other materials, and I think the pyrolysis possibility is increasing higher year by year. Thank you very much.
Thank you, Professor Toshiaki. You can now de-share the screen, then we'll continue our discussion. I'll come back to you now. May I request Dr. Thallada Bhaskar to share his thoughts about the three aspects of the applied biomass pyrolysis that I initially shared with all of you. The feedstock variation, process engineering aspects, including the modeling one, and that's the last one is the catalyst one. So over to Dr. Bhaskar.
Bhaskar, now the mute, maybe.
Yeah.
Okay, I can hear you.
Thank you, Chairman, Professor Mohanty, and at the outset, I also thank Professor Yoshoka Sensei with the kind of the always new information, inspired thoughts, always coming from him. Ever since I had interactions from the Japan. Once again, I am very happy to share as a panelist in this PYRO Asia 2020 event. And with regard to the topics which has been posed by Professor Mohanty, as well as Yoshoka Sensei's comments and the conceptual information to identify the pyrolysis as one of the important tools or the methodologies to convert the waste biomass as well as the waste plastics is indeed highlighted. That is, I fully endorse and I agree. And when it comes to the points raised by you with regard to the composition and the feedstock availability, as Professor Yashoka already mentioned that after 2016, the export of the different waste polymeric materials sending into the China has been stopped. Under the that is also the international protocol that the waste cannot be shifted to the different transcontinents because of the environmental and hazardous regulations. In India, several ports and several places, it has been occupied a large area. That is an issue, and this is not an issue for a researchers like us. It is an opportunity to identify, optimize the different reactor configurations, processes to produce not the one product, not the energy, not the only chemical, and diversify the product required at that location to avoid the supply chain management as well as the transportation of the products to the longer distances should be coupled to calculate to assess the techno-economics as well as the environmental considerations. If we understand that one, this is an opportunity for the scientists, professors working in this area to design a different reactors. Being a scientist at the Petroleum Institute, I can confidently say that these are completely a different strategy has to be adopted. In case of the crude oil, we get from the different countries at one location, process, distribute the products to the different locations and different countries, which is not possible with the waste, whether it is a biomass or the plastics. Coming to the, this has to be localized. So for this, the knowledge base, technology experience generated around the continents and the countries has to be exchanged to apply this global problem, whether it is an energy problem or the environmental problem. Coming to the Indian scenario, as a scientist working in this bioenergy or the polymeric waste pyrolysis, I could see that one simple rice straw in North India has only 5 to 10% of the lignin. In South India, the same rice straw has 30% of the lignin. So similarly, the polyethylene or polypropylene or polystyrene or the brominated flame retardants or the electronic waste are different for the different components being used in diverse applications. So the mixing of these things also not advisable, as the science and chemistry cannot be used or be combined for a single complex mixtures. So that is one thing. When it comes to the processing of these diverse materials, the modeling, the process design and the kinetics, thermodynamics so essential. If we don't understand the properties of these individual materials, complex materials at the different locations are different. That has to be understood. Based on that, the design of the catalyst. The catalyst for the all over the globe, almost all the refineries, the conventional hydrotreatment catalyst almost same. However, that will not work for the hydrodeoxygenation of whether it is a glycerol or whether it is a biomass based oils coming from the palm oil. Just now we heard the presentation, or the another straws, or the forest residues which are available abundantly in Japan. So it is completely different because the oxygenated compounds or the halogenated compounds produced from the different feedstocks are different. The conventionally, the hydrodeoxygenation or hydrodehalogenation term is same, but the compound which are present with the sulfur or oxygen or bromine is different, chlorine is different. So hence, as a scientist, as a researchers, we have been hearing from the last 2 days, we could see the diverse feedstocks being used for the different products as per the location, as per the required strategically. The multi-products, multi-feedstocks, multiple processors need to be generated to address the utilization of the carbon resources, whether it is the plastic or biomass, to address the local problems. The underlying science, underlying reactors, underlying the capital development should be the core objective among the researchers. I think if any specific questions are there, maybe Professor and I would be happy to address with the responses.
Yeah, almost. I agree with Bhaskar Sensei's comments.
Yeah.
Maybe now the number of the kind of the plastics is now in the, about 114 resins now, and the other plasticizers number is about 200 or 300 over. And now we use some plastic and some materials, and all materials, a combination of that plastics and impurities plasticizer. And then the other case, there are many metals and inorganic materials include of that goods. In that case, it's difficult to the one processing on the two processing, and we have to make a lot of the application of pyrolysis systems. And then many industries have a lot of the processing now, and we can use the previous processings in industry to conversion to the into the useful materials from the organic materials, plastics, also the biomass materials. Yeah, and of course the location is different, and collecting the materials is different, depend on the social situation and the locations, and we have to prepare a lot of the processings. Yeah. And almost I can agree the Bhaskar Sensei's comment.
Thank you. So thank you, Dr. Bhaskar and Professor Toshiaki. Param, will you please allow me to share my screen? I want to show one slide. Is it visible to everyone?
I think you can zoom it a little bit.
Okay. Is it fine now?
Yeah, better. You still have some space.
I'm not so young. It's difficult to read this. Yes, okay.
This is better.
Is it fine now?
Yeah.
I can find. Okay. I can see.
Yes. So before we proceed and open the discussion for question and answer, this has been taken from one of the extremely nice publication in energy and environmental science in 2012, way back. So the authors have given these challenges. So complexity we have discussed. So the top 10 fundamental challenges of biomass pyrolysis for the biofuels. The first one is the multi-scale nature of biomass feedstocks and multi-phase nature of pyrolysis. Now I'll just quickly go through this, then we'll open for discussion. Challenge one: what modern techniques can reveal pyrolysis chemistry? We have been talking about this since last 2 days, and always tell that pyrolysis mechanism is too tough because so many simultaneous reactions happen. So this is one of the things. Second is that how do anhydrous sugars, pyrans and furans form from cellulose? Still, this is ill understood. Third is how do products break down within the intermediate liquid. That is also very important. Yesterday I was talking about aging of the, during my presentation, stability of the bio oil. So this also a challenge. Fourth one is how does solvation affect intermediate liquid chemistry. Again, the more chemistry part of that, understanding the mechanism. Fifth one is how do inorganic catalysts influence the condensed phase chemistry, because phase separation is an issue, and of course it's a multi-phase system, pyrolysis system. How does char form in pyrolysis? So this is we know, but still more detail has to be worked out. And how can heat transfer models be used to improve bio-oil yield and quality? More engineering aspect, of course. How are aerosols produced and how do they affect bio-oil properties during condensation and all? What experiments can validate particle pyrolysis models, and what causes particle shrinkage and how it can be predicted. So this is a very interesting review article where they posed this 10 challenges. I felt that it's apt to just show to all of you, and then we'll move ahead with our discussion. And we can go, Param, you can on this one, my screen, you can take it off so that we can go come back.
There is some comments from the audience. Would you like to take?
Yes, definitely. Yeah.
Okay, you want to share the screen on this?
Yeah. Yes. Okay. Let me read out. In case of the pyrolysis of waste plastics, the actual commercialization is still limited, mainly due to the condensation problem of heavy wax generated from PE and PP pyrolysis. Although catalytic pyrolysis is being suggested as a solution, the high cost and fast deactivation of catalyst are the limitation. Under this situation, which kinds of research must be performed to accelerate the actual commercialization? I want to know the opinion of the panelists. If there is a successful plant, please share the information if it is possible. This is the first one. Then we'll come about the local ability. I think Professor Toshiaki can comment on that.
Yeah, it's a good discussion point. No, we try to this issue.
Yes.
Yeah.
Then Dr. Bhaskar, myself.
Yeah. And I think the using the pyrolysis processing for the for waste plastics, and I think the not technical issue. I think, and almost economic issues maybe, and pyrolysis process is not so small processing to treat of the waste plastics. We need a bigger size of the plant for the pyrolysis plant. In that case, we have to get more plastics in the market, and then it's difficult to collect all the waste plastics. But that waste plastics have a lot of the impurities, and in the research stage, and we try to the experiment using the pure materials, but actually, and a lot of the impurities, including the waste materials, and then we have to consider and challenge to try to the how to the effect of the impurity of the pyrolysis processings. At first, that is a very important point, I think. And the problem of the heavy wax and generated P and PP pyrolysis, and I think that depend on the conditions. And then we need new catalytic materials to solve this material, this issue. And now there are a lot of the researchers try to make new catalytic materials. And then we try to again. And yes, and just my comment now, and maybe the Bhaskar-san, you have some answer and comment under this discussion point.
Yes, Dr. Bhaskar, please.
Yeah, I fully agree with Professor Yoshioka that the pyrolysis of polyethylene or polypropylene or polystyrene or mixed plastics, the formation of heavy wax is not the technical issue. It is the design parameters and the reaction temperatures and the heat integration of the pyrolysis reactor as well as the downstream condensation process. I think it may be misunderstanding that the catalytic pyrolysis will give the avoid the wax. No, there are certain processes use the catalyst to make the wax, because waxes are of different type and waxes are much valuable than the liquids. So without catalyst, we can make the wax-free clear oils 80% are the based on the composition. Absolutely no issue. It is the reactor issue. It is no more a technical issue. Professor Yoshioka has worked with the 1-ton plants to the 6-ton, 10-ton plants and guided several plants where I also worked with the 6-ton plant work. So this is not the technical issue. Yes, there are several models and several plants are established, and the person they can write to us so that we can discuss exactly what PE, what PP or what mixes they are doing. Or the literature is directly available to show the liquid yields without any wax.
Yes, yes. Thank you. So the next one is local availability of the biomass. I think Dr. Bhaskar has already addressed this thing during his inaugural thoughts sharing. So as he told, if you recall, that biomass is always like that. So all the biomass are not available round the year. Okay, whether it is agricultural biomass or any such forest residue, whatever it is, including even municipal solid waste, because that is a very difficult one to do pyrolysis for the segregation aspect into this one. So always it is very, there are many papers on this LCA and TEA papers. If you look into that, they always suggest that all these gasification and pyrolysis plants should be located at the source as much as possible, always not possible, so that the transportation is not becoming a big issue, because the density and all these things plays a big role when you transport the biomass. It's always a challenge. So some sort of pre-processing. So I think it is always better to have the industries located near to the source. But I would like to hear more on this from Dr. Bhaskar and even Professor Toshiaki. So Dr. Bhaskar, can you little elaborate this little more?
Yeah, actually, when it comes to the local availability, if the question is from the Indian person, I can suggest that there is a report published by us, as I am one of the co-authors in this committee. 400-page document with the satellite images. We have prepared the pan-India database about the availability quantitative data on the different parts of the country. 623 districts have been considered. So there is a TIFAC database. Simply if you Google Talada Bhaskar and our TIFAC report, it is available. It is published in the 2019. Similarly, I think Professor Yoshioka also agree with me that in the Europe as well as in Japan, the database availability is the available in the open source. So people has to find out what kind of biomass is available there, so that the process development or the R&D on that biomass may be initiated.
Yes, thank you. So any more question?
Yeah, and I don't know it's a good sample or not for the Japanese case. And focusing the plastics issue. Not biomass, but almost related to the biomass one. And last year, and the Japanese government make a strategy of the plastic material cycle. And then, of course, the recycling ratio increasing also. But as an option, one of important options, and the biomass plastics, the ratio is to increase to 2 million tons of the plastics. Almost 20% of the plastics in Japan. And biomass, the resources is increasing in the future until the 2030. And that is a very high world task. Yeah. In that case, the important point is how to collect all the biomass resources to make plastics. In that case, in case of Japan, and especially the urban, big metropolitan towns, have a lot of the biomass waste, such as the paper waste, and it's sad that and food waste also. And that is very, very important and resources of the biomass. And then we make some fuels and some chemicals from the bio waste materials, and that is very, very available in the socials. Of course, not urban towns. In that case, a lot of the agriculture's waste. That is a very good resources of the biomass, and it depend on the localizations and what is the better processing, what is the better collection systems. It depend on the localizations. And I think there are many, many possibilities and challenges for the local of the biomass resources. Yeah.
Okay. Yes. Yes. Okay. Thank you. And there is another question. In terms of energy recovery from waste, which is the best, gasification or pyrolysis? Dr. Bhaskar, can you comment quickly on this? Okay, Professor Toshiaki, please.
Yeah, of course, that depends on the materials.
Yes.
Yeah, and considering the efficiency of the energy recovery of the incineration and to make energy, and
yes.
In case of the European case, in the they consider the total as a total system of the energy efficiency. But Asian countries, there's not so total efficiencies, just localizing of the process efficiencies.
Yes.
In that case, not effective. And then considering the waste materials, and sometimes at first one of the better way to the mechanical cycling is, but the materials have a lot of the impurities. In that case, it's difficult to do the mechanical cyclings. In that case, feedstock or the energy recovery systems. And depend on the material material contents and materials morphology also forms also, and yeah, and gasification is some is available, but another case and incineration and just energy recovery is available, and depend on the materials and depend on the localizations.
Okay, thank you. So, Param, is there any more questions?
I'm sorry, I don't have any more questions. Yeah. Oh, okay.
Okay,
No,
fine. So we'll
okay.
go ahead with some. Yeah, fine. No issue. So we'll go ahead with some of our discussion for a few more minutes before we wind up. So one thing, very important issue that is keeping always propping up is the trade-off between the optimal cost and the environmental effect. So I'm talking about pyrolysis process itself. So when you talk about a refinery in a refinery prospect, and let us talk about a biorefinery prospect. I'll come to that in the second one. So anyway, let me pose this to my this one query or question, whatever it is. You can say that how does biomass pyrolysis as a whole fits into a biorefinery concept. So what must be done so that it fits to the biorefinery in a more sustainable and economical way, maybe in a circular economic way also. So because lots of things are being going on in biorefineries. Biorefinery started initially with cellulosic refinery, then lignocellulose, and so many things. Now waste biorefineries are also there in many of the European countries, and few are also coming up in India as well as our Asian countries, other Asian countries. So these two are a very important thing. One is that biorefinery as a whole, because this biomass always is an issue, the types of biomass. And second thing is this environmental concerns and the optimal cost. So we can have a quick thought sharing on this. I'll request Dr. Bhaskar to say something, then Professor Toshiaki.
Professor Mohanty, when it comes to the biorefinery concept, there are several models are there. It is not the straightforward single answer to make the economically viable or the environmentally sustainable.
Correct.
In case of the 2G ethanol, that is the fermentative route to produce the ethanol to biotechnological platform, where the all components are not utilized. Only cellulose is used. Hemicellulose lignin is not utilized in the ethanol process.
Correct.
So when we talk about the biorefinery, the value addition of the lignin as well as the hemicellulose is highly required to make it economically viable. Yes. So the demand and supply is also essential, because the government of India has a mandated to use the ethanol. So the demand for the ethanol is more. So we are bound to produce that one. At the same time, we need to find out the options or the value addition opportunities or the routes for the C5 as well as the lignin fractions. So in this case, when we calculate the entire composition of the all components of the biomass, definitely it is going to be the economically viable. That economical viable is also a limit, because the cost of the ethanol in India, that the cost of the ethanol in elsewhere is completely different. So these are all specific to the regions and the countries about the price. So the estimations of the cost, price, and the availability all depends on the estimation of the sustainability as well as the environmental benefits. The goal of the whole global community, all countries, are only intended to make sure that there should not be any CO2 emission or the global warming gases should not be left to the environment. That capture should be there. So that is why recently the CCUS technologies being explored to make sure use the carbon utilization and without any gases to the outside. So there are several models available for the several compounds. We need not say that only ethanol. There are other models where people are producing the high quality cellulose as well as the nano lignins and using the C5 for the xylitol production. So it all depends on the supply demand and the requirement of the local products.
Right. Thank you. So there are many. I hope there are. Yes, Professor Toshiaki, please go ahead. Yes.
Yeah. Now the Bhaskar Sensei, Professor Bhaskar indicated a very important point in this in that comment. And CCU process is a very useful for the considering the pyrolysis or the gasification of the biomass. And the other case, the CCU processing, and such as direct air capture processing, that is very important to the how to use the biomass resources. Yeah, and not focused just pyrolysis of the gasification from the biomass resources. And other case, we have to consider the other side of the CCU and the CCS processings. And in that case, that we have to use biomass resources in the socials. Yeah, Bhaskar Sensei indicated a very important point, I think. Thank you very much.
Yes, thank you. So since yeah, there is another. Okay, there is one more question that's coming. What about the perspectives of old biomass, so which is natural and fixed amount, and new biomass produced artificially, which will again pose threat to the production of food, as the lands are being used to produce new biomass? How to trade off between the food versus new biomass? Dr. Bhaskar, biomass.
Dr. Bhaskar is very fit.
Please go ahead, Dr. Bhaskar.
I think the misunderstanding between the biomass growth or biomass grown specifically for the energy applications, as well as the old biomass. We cannot grow any biomass artificially. Every biomass has to be produced photosynthesis on the land. Yes, there is no other artificial. I think the question, the person may be intended to ask the specific energy specific grown biomass, not rather than the artificially grown. That is one thing. Second thing is, when we are talking about the energy purpose grown, India has around 30 to 40% of land which is not used for the cultivation, and the used land for the cultivation is only used once, one crop, which is different from the other countries. So the idea of the government of India is to make use of the wastelands so that they will become fertile to use the soil, and the once you start growing anything, the unused soil or the waste soils, wastelands become fertile. That is possible with the use of the biochar, which fixes the carbon within the land soil where it is not possible to grow. And about the trade-off between food and new biomass, I think there is enough data available in the government of India as well as the global. There is no food scarcity on earth today. It is only the supply chain management, inequality distribution of the available food. The food is available for all the human beings on the earth. Even in India, we have more than 60 lakh tons of the foods available and which are not used, just dumped or the low utilization. So today we don't have any food issue. It is because only the improper distribution, execution of the systems, and the unequal distribution. So in any even in India, nobody is dying because of the food. If it is somebody is dying, it is not because of the non-availability of the food. It is only because it is not available or unequal distribution. So I think the enough data is available. Further, if it is required, I am happy to share.
Yes. Okay. So I think any biomass that we are thinking of using it for value addition, whether it is fuel or chemicals, it must be out of the feed line. So there is no question of any feed versus food problem. Sorry, food line. So I think that itself will take care. So there is one more question: at what about mild pyrolysis torrefaction? Yeah.
Yeah, all our discussions of the Pyro Asia 1 or Pyro Asia 2, We are all talking about the residual waste biomass rather than the food biomass. Because food are the grain. We are not working on, anyone is working on the edible biomass. We are all working on the non-edible fraction of lignocellulosic biomass or the plant biomass and the residues of the industrial process. So there is no issue between the trade. And what about mild pyrolysis torrefaction? Yes, the torrefaction is itself is a mild pyrolysis.
Yes. No, what is the question? I do not understand. So anyway, fine. So I think time is approaching. So before we finally close, I'll just request Professor Toshiaki to share, because there are many students and these students keeps on asking that, including my students also, and they'll be very happy to know the thoughts of both of you, that how do they carry out LCA and PA analysis. Some thoughts. The life cycle assessment of the process they carry out, including waste biomass, waste plastics, pyrolysis or co-pyrolysis, and the techno-economical evaluation. How do they do? Some methodology, if you can suggest quickly, then I think it will be nice for all the students.
Yeah, me?
Yes, sir.
Yeah. Okay.
Yeah.
Yeah, and today I hear some LCA analysis in the presentation from the young scientist. Yeah.
Yes.
And in the future, now is also a very important academic area to consider how to the useful processing, which processing is useful to make some achievement of the processing, and but considering the LCA research, and at first we can get real data also, and then through the experiment. And then if we can get some useful data, and then how to upgrade and grade up of that data, that's that important point. And just considering the LCA processing in the very narrow discussion, but actually considering the LCA analysis is we have to consider the widely. And not only the development of the processing, but also the LCA analysis is very useful for the development of the some processing and some to make a new academic area. That is just my comments.
Yeah, thank you. Dr. Bhaskar, would you like to add something about LCA and TA?
Yeah, I agree.
For the students.
Yeah, Professor Yoshoka. And when it comes to the students, we even in our lab also we are using some software tools,
right?
And we are revising, we are modifying those softwares to calculate the techno-economics, and we are working for industries also. When it comes to the life cycle analysis, as Professor Yoshoka mentioned, that the fundamental data which is not available in any of the resources, and which we cannot take directly from the literature to calculate the analysis data. So we need to generate our data, then we can calculate. Yes. Otherwise, there are a lot of deviations, errors, without which, without our original data, we cannot come to the conclusions.
Yes. Thank you. Thank you. So I think we are approaching our deadline time. So if both of you agree, I'll just say something concluding, then we'll wind up. Will that be fine?
Yeah, please.
Yeah. Okay. So I think we discussed certain issues, and I would like to thank my colleagues on the panel, Professor Yoshoka Toshiaki and Professor Thalada Bhaskar for their time and insightful thoughts. So as we have discussed that there are various types of reactors, Dr. Bhaskar has already told, and there are so many upgrading technologies under development. The knowledge transfer and closing the gap between theory and applications, of course, requires model development. So this is one of the very much important engineering aspects. So in-depth understanding of the reaction mechanisms, the more chemistry part and the kinetics should also be combined with the knowledge of multi-scale transport phenomena to enable so that it can help us design optimization and control of the complex pyrolysis reactor. Process control, very important factor when you go for industrial scale. So finally, when we talk about pyrolysis, this one, so under pinning the economical and as well as the environmental impacts, as Professor Toshiaki has already presented during his initial presentation. So that impacts the biofuel production, that requires expanding the system boundaries to include the overall process, as well as Dr. Bhaskar whatever told about the supply chain management system. So I thank you very much, Dr. Bhaskar, Professor Toshiaki, and we will conclude this. And thank you, Param, for managing PYRO ASIA Symposium so beautifully, on time always. That's a great thing actually. And thanks to Karthik also, and thanks to all of you, all the delegates and the listeners. Thank you very much. Thank you. Over from our side.
Okay, thank you, Professor Mohanty.
Thank
That's
you,
a very nice.
and Mohanty, thank you.
Thank you very much. Okay, we're end of second day. Thank you all the sponsors, panelists, okay, delegates, and organizers. Of course, I had to thank myself and also as a part of the team. And it's very interesting. Yeah. I'm sure that you find this, last 2 days is very informative, and you learn a lot of, useful points for your work and for your education and professional research point of view. So let's wrap up the day today for the end of the day today, and let's meet again tomorrow at 1 p.m. Singapore time. Thank you all. Have a good evening. Good night. Bye-bye.
Bye-bye.
Thank you.
Bye-bye. Yeah, see you tomorrow.
See you tomorrow, Sensei.
Bhaskar-san. Long time no see you.
Yes, Sensei. Sensei is busy. I am always okay.
Okay, I'm ending the webinar. Yeah. Okay, bye-bye.
Thank you very much. Bye-bye.
Bye-bye. Bye-bye.